Should we wait for a couple of minutes because there are still people connecting?
Yes, why not?
Alessandro, I will give you a warning after 12 minutes. Is it okay? Or
Okay, okay. Is it a waving, a beeping?
yeah, I think you can start sharing the screen.
Okay, let's start to share it. Okay. So this should be the presentation.
Perfect.
Tell me when I can start.
Okay, let's wait 1 minute of courtesy.
Okay.
Okay, I think we should start.
Okay.
Hello, everybody. Welcome to this session 13 on laboratory and field experiments. Our first speaker is Alessandro Marazzu, that he will present cosmic dust investigation of optical tweezers for space exploration. So please go ahead.
Okay, so hello to everybody, and thanks to the organizer for the opportunity of being here to present my job. So let me start to tell you why it's so important to study cosmic dust. Well, cosmic dust play a dominant role in the universe, in particular in the formation of stars, planets, and minor bodies such as comets and asteroids. And it also plays a role in the formation of molecular hydrogen by catalytic reactions. Furthermore, the dust surface is the benchmark where molecules and simple organic compounds such as carbon monoxide and ammonia are produced. Cosmic dust is composed by small solid particles of silicon, iron, oxygen, and magnesium in the sizes ranging from microns to millimeters. It can be found on the outer space, where it can be collected by spacecraft, in the Earth's stratosphere, where it can be collected by balloon-borne collectors, or it can be extracted from meteorites found on the surface of our planet. Once cosmic dust is collected, it's characterized at large facilities by means of advanced analytical techniques, providing important information to understand processes occurring in different astrophysical environments, including the origins of life. The collected samples are usually deposited on a substrate, giving rise to shielding effects by the substrate itself or by other particles. To overcome this unwanted effect, we use standard Raman tweezers, which represents a contactless and non-destructive tools to isolate a single dust particle, to characterize their response to the optical forces, providing more accurate information to the theoretical models for the calculation of the radiation pressure on cosmic dust, and to identify their mineral and organic composition, and to search for biogenetic signatures. We investigate single dust grains provided by University of Pisa, and these samples came in a powder, and we disperse them in a liquid solution, which is located in a cavity glass slide, sealed by a cover glass. And by an high-focused laser beam, we optically trap one single dust grain, and the scattered light is collected to a quantum photodiode, which provides electric signals proportional to the displacement of the particle. And from this signal, we are able to calculate the response of a single dust grain to optical forces. In particular, we use some terrestrial and extraterrestrial mineral grains as standards to test our setup, similar to the grains used to calibrate the dust analyzer JADA on board of the Rosetta space mission. Our standards grain are a quartz arenite sample from Camil crater in Egypt, and awaite sample from Etna volcano in Italy, and a carbonaceous chondrite from a land meteorite found in Mexico. We optically trapped these samples by linear polarized light, and here we present a video showing a dust grain of awaite trapped at low power. And here the same grain trapped at high power, where in the first case the particle is more free to move within the trap, while for high power the particle is not moving at all. And here we can see how the trap stiffness is increasing linearly with the power of the trapping beam for 3 different components of the optical force. We can also observe that due to the shape of the particle, light can exert a mechanical torque on the particle, inducing rotation, where as we can see in this video, for low power. While for high power, we can see that rotational frequency increases. And here we report the rotational frequency for 3 different samples. So in this case, we can see how the rotational is increasing with the power of the light. If we use circular polarized light, we can also observe an angular momentum transfer from the light to the particle. And in this video, we can see how a grain of awaite is optically trapped by a left circular polarized light. And we can notice that the particle is rotating slowly. Then, always for the same trapped grain, we change the polarization of the light to linear, from left to linear. And we can see how the particles start to rotate faster. And then we change the polarization to right circular polarized. And we can see how the particle is rotating even faster. So we can use optical tweezer also for photonic microscope torque to quantify this rotation by calculating the differential cross-correlation function of the particle trajectory that is represented by these black circles. And we can fit this experimental function by a fitting function, a sinusoidal fitting function that will give us as a fitting parameter the rotational frequency of our particle. And we can see how the light can induce and tune rotations and how these rotations can, the rotational frequency increase with the polarization from left to right. And the change of the rotational frequency of our particle is due to the sum of 2 contributes, the mechanical torque and the transfer of the spin angular momentum. The mechanical torque depends on the shape of the particle, while the transfer of spin angular momentum depends on the absorption properties of the particle. And so the optomechanical interaction depends on both the particle shape and on the polarization of the laser beam. By Raman tweezer, the backscattered light from a single dust grain can be analyzed by a Raman spectrometer, providing information on its composition. And this is the case of an optically trapped grain from the sample of Camil crater, which according to the literature is supposed mainly by quartz. And here we report the Raman spectrum of a single trapped grain of our sample. And in red, we present the reference spectrum of the quartz. Similarly, we trapped other 2 mineral grains from Etna and from a land meteorite, which according to the literature, they should contain olivine. And here we report our experimental spectra of our trapped grain. And in red, we report the reference spectrum of the olivine, showing a good agreement with the reference spectrum. After trapping standard grains, we started to investigate dust grains from a lunar meteorite found in Antarctica, which according to the literature present among its constituents pyroxene, and this is That's one of the spectrum that we found for our trapped particle, which match the reference spectrum of pyroxene, that here is reported in blue. And according to the literature, this meteorite contains also plagioclase, olivine, and ilmenite. And here we report another spectrum of a trapped grain, where in this spectrum we can recognize the reference spectrum of the plagioclase, the olivine, and of the ilmenite. After trapping more than 17 grades, we could estimate a percentage of the composition of the lunar meteorite sample, which shows a good agreement with the reference found in literature, showing how optical tweezer and Raman tweezer can be a powerful and reliable tool for the characterization of cosmic dust. In conclusion, we believe that optical tweezer can play a key role in the cosmic dust investigation. What I presented today are just preliminary results, and soon we are going to build an optical tweezer in air and another in a vacuum to recreate an active environment that is closer to the one of the cosmic dust. And we aim that optical trapping techniques, thanks to their contactless ability, can be implemented in extraterrestrial curation facilities, where extraterrestrial samples are processed in order to prevent sample contamination, and even more important, to prevent the biohazard for our planets. And as a futuristic outlook, I would like to show you a possible application of optical tweezer, where the samples, instead of being collected on an asteroid, like in the case of Bennu asteroid as shown in this video, and then they are brought back to our planet, they are just investigated directly on their native environment without any physical contact. And finally, I would like to acknowledge all my group members at CNR IPCF Messina, Luigi Folco for providing the dust samples, and all the collaborators of the Space Tweezer project, and the financial support from the Active Matter and Space Tweezer project, and the National Museum of Antarctica for the donation of the lunar meteorite. And thanks to all of you for the attention.
Thank you. Very interesting talk.
Yeah.
And perfectly in time.
Yeah.
Okay, the talk is open for discussion. Do you have any questions? Okay, Jerome?
Hi, I may have just missed it, but could you remind me what the size scale of the particles you're trapping is?
It goes from, we trap samples that are in the range of a fraction of a micron to a couple of microns.
Thank you.
Yeah.
Any other question? Okay, I have one. You mentioned that you can levitate one single particle.
Yeah, we can trap. We trap in.
You can trap it. Yeah, sorry.
Yes.
Will it be possible to levitate several several particles forming an aggregate? Or
Yes, we can trap in liquid. Yeah, we can also trap different particles together just to see how they can interact with each other.
So they will be. They have to be diluted in a liquid or something, or.
We can trap. I did in liquid with other particles, not with cosmic dust.
Mm-hmm.
But I'm not so sure if also you can levitate multiple particles with multiple beams in a vacuum or in air.
Okay. Just last question, is it more difficult to trap small or large particles? Because I think at the beginning you said that you could trap millimeter sized, or did I get it wrong?
Let's say the cosmic dust is in the range
Sorry,
from micron to millimeter.
Yeah.
With optical tweezer, we can trap in the range of a micron, but we are also implementing a setup with acoustic tweezer. So basically, we trap by acoustic waves. And in that case, we can trap also particle in the range of millimeters.
Okay, thank you. Any other question? Okay. Then thank you very much. And I think we should just move on to this next speaker.
Okay, I will stop sharing my screen.
Yeah, please.
Okay.
So next speaker, Cremonesi, is there.
Oh, can you hear me all right?
Yeah.
No, nice. So
Can you share the screen?
yes, of course. And now I can. Yep. There you go.
Okay.
Yeah, I should.
Yeah, putting
Bear
in
with me for a while.
presentation.
Computer is a bit, yeah. It's a bit slow. Anyway, thank you for the presentation. I am ready.
Can you put it in the presentation form?
Yeah.
F5 or?
Yeah. I did. It's just loading.
Okay, it's taking
Sorry.
time. Okay, we can just go on. Okay, our next speaker will talk about measuring the contribution of a structure to light extinction by aggregate. Let's see if you can put it in the presentation.
I'm terribly sorry.
No, it's okay.
It's going on. Yeah, maybe. You know, if you wish, we can swap the speakers, since PowerPoint decided just to drop in this very moment. I'm sorry.
Oh, I don't know, Alexei, what should we do?
Sorry.
Should we switch speakers, or well, we are still in time? So if you want to try again.
Okay. Then I'll give it another try.
Yeah. So could you try one more time, or?
Yes. I'm launching PowerPoint again. Yep. Not responding again. I'm sorry.
Oh.
Nearly there.
Okay.
Yeah.
Connecting.
So is this going now? Yeah. Sorry.
Okay, it's back. If you cannot put it in the presentation mode, it's okay. Just
okay.
At least we can see it.
I hit F5, but then
okay, then it crashed. Okay, so please go ahead.
Yep. So well, my presentation should be dealing with measuring the contribution of structure of.
I'm sorry. Could you speak a bit louder, because it's very hard to hear you.
Oh, sorry. Well, I keep my microphone closer. No? Can you hear me all right?
A bit better now. Yeah.
Yeah. Well done. Thank you for the presentation. The presentation. I'm sorry for the technical issues. Anyway, good morning or good afternoon, depending on your local time. My presentation will deal with some experimental results that highlight the contribution of structure factor in aggregate particles and the contribution to their extinction cross-section. Now, the interest for aggregate particles stems from their ubiquity. As we have seen in many presentations previously, some beautiful examples are common among aerosols and interplanetary dust. On a larger scale, we could mention also microplastics that are attracting much attention of the scientific community. Relevant subgroup of particles are particles whose structure can be described as fractal. This extremely widespread growth process is found in a variety of systems, such as colloidal suspensions, oxides, and metal nanoparticles, as well as black carbon and brown carbon soot. They can include several thousand particles bound together and are often investigated with optical techniques, especially if the main subject of interest are indeed their optical properties. So in spite of their complexity, the morphology of fractal aggregates can be conveniently described with a few parameters. Some other speakers have already covered this topic, so I will be brief on this, but I just mentioned the main quantities that we need later on. So first, their size is generally defined as the root mean square distance of their constituents from the center of mass. And this is Rg. And then the number of particles, they include scales with the, follows a power law that depends on a scaling prefactor, and the exponent is the fractal dimension. Now, similarly, the structure factor is quite simple and depends on two parameters, Rg and df. We see that for large scale, for large scattering vector Q, it follows a very simple power law that we can see in the plot on the right. Here we compare some rotationally averaged DDA calculations, and different models are available. For example, the Debye formula, or other more complicated formulae based on hypergeometric functions, but they all agree fairly well. The two features that are important here is the slope, which is given by the fractal dimension, and here the roll-off that is due to the finite size of the particle. So basic scattering theory and diffraction theory suggests that this simple trend in the reciprocal space is due to the presence of small and large scale features in the particle. So if we devise a basic experimental setup, we would have a laser and a sensor that integrates the amount of light scattered over a given solid angle. Far away from the particle, the scatter field depends on the scattering amplitude, which is a complex matrix, and is affected by many morphological features of the scatter, such as size, polarizability, the polarization of the incoming light, etc., and internal and surface roughness. So the key point here is that on the forward direction, when theta equals 0, this quantity is related to the total amount of light which is removed by the particle from the incoming light. And this is the extinction cross-section. The extinction cross-section is given then by the scattering and possibly absorption depending on the nature of the particle. Here we will be dealing with particles that have this matrix, which is to very good approximation diagonal, and the elements on the diagonal are equal. So we can treat S0 as a complex scalar quantity in practice. So suppose we have collected some data, then we need to solve the inverse scattering problem. We consider an aggregate with the primary particles, which are very small, so much smaller than the wavelength. And this means that they can be treated with the Rayleigh scattering regime, specifically with the Lorentz formula. However, the aggregate as a whole does not simply act as the sum of its smaller blocks. And as a first step, we can approximate this complex particle, considering a composite particle and replacing it with a homogeneous one using the mean field approximation, for example, to define an effective polarizability. With this model, we can then draw from Mie theory or anomalous diffraction, as in Van de Hulst, to calculate the scattering quantities. The morphology is, of course, drastically simplified, and many authors studied the applicability of these approximations. And indeed, there are some settings where they fall short in predicting experimental observations. But still, they are a very simple way to tackle the inverse scattering problem anyway. So we can use them as a benchmark. The optical construction of fractals are normally described in terms of the Rayleigh-Debye-Ganz theory, but we need a model for S0. So we opted for another model that we developed, which is based on molecular optics and is a second-order perturbative model for the forward scattering. We followed in terms of alpha. Sorry. The parameters C1 and C2 are the ones that are given by the morphological feature of the particles. So it is also successfully covering the case of Mie theory and Rayleigh scattering as well. So it is a good way to check its accuracy to compare it to other theories, well-established theories. We can now move on to the experimental part of the presentation. The data was collected with single particle extinction and scattering method, which was presented earlier in this conference. Very briefly, this method expands a laser beam and then is tightly focusing the laser on a flow of particles which cross the beam in its beam waist. And then in the front, we have a 4-quadrant photodiode which collects the photo scattering and gives us a means to measure the real and imaginary part of this scattering matrix at theta equals 0. On the right, we can see the output for homogeneous particles of different materials, and we see that particles of different refractive index lay on curves which are separate on this plane and do not intercept. And here we can see the data relating to fractal aggregates of dielectric spheres, which are calibrated polystyrene particles. The elongation of the plots, the data is shown in green in the two-dimensional diagrams, two-dimensional histograms. The data is elongated due to the size polydispersity. And we compare the data to the molecular optics model for the fractal case and the effective medium approximation in blue. Now, interestingly, the trend of the plot has a slope of 1, and the fractal dimension should be 2 in order to fit with the effective medium approximation model. But we can measure the fractal dimension independently, so this is not a free parameter actually. What we can fit is the prefactor K0. We can fine tune it, but still the slope is always almost 1. We can take a closer look at this fractal dimension and slope relationship, and we see on the left that effective medium approximation, as expected by anomalous diffraction theory, gives a unitary slope for df equal 2, while indeed there is a very mild dependence on df of the slope. So on the right, we see the comparison of different curves relating to different fractal dimensions, and all of them are almost horizontal, unless for the more complex structures below. And this is what is reflected by our data that we collected from aggregates of different size, carbon aggregates, and iron oxides as well. So we can compare our data to simulations and taking a more thorough comparison, the model and simulations as well. Yeah. So we generated fractal aggregates, homogeneous spheres, and correlated non-overlapping monomers as an intermediate step between them. So we then calculated their respective scattering amplitude with DDA. The results are shown as dots of the corresponding color here in the plot, and we see that they compare quite nicely with the model. The model is always the same, is the molecular optics model, where we computed the two parameters C1 and C2 with the corresponding scattering, with the corresponding structure factor. Sorry. So it is interesting to note that the imaginary part of these particles is dominated by, dominates as 0 and is essentially proportional to the number of monomers. So all the models then shift horizontally because what differentiates them is the real part of the scattering amplitude, which is, in the case of aggregates, given essentially by the Rayleigh-Gunn-Debye limit, since computing C1 is equivalent to computing the scattering cross-section. But even without absorption, we can see that the spectral trend of the extinction is different for the three models. And there is a contribution of the shape in the spectral dependence. Moreover, we need to normalize the models, in green the clusters, and in blue the homogeneous spheres. The normalizing factors should be different in order to fit the experimental data, which is shown in black here in the plot. And to conclude, we can take a quick look to more general cases. On the right, we have black carbon aggregates. which are very well described by all the three models. Here we see simulations, and the correspondence with the model of these simulations is actually pointwise, but then we plotted the solid lines to be for simplicity, for practicality. But we actually see that if we increase the imaginary part of the refractive index, here I'm sorry I cannot show you the animation, but the curves which were separated in the previous slide then collapse onto one curve, and we cannot distinguish the models between each other. And this is probably due to the fact that since correlations affect mainly scattering, absorption is mostly proportional to the volume, and here's the extinction is mainly giving up to 80–90% by absorption. So the contribution of scattering here is negligible. And to finish, on the right, we have isometric mineral dust particles, which are very well described by effective medium approximations when we take into account that since they are not compatible with any refractive index for compact spheres in here, shown below in gray, we can interpret them as void spheres with a certain fraction of voids, and our model predicts about 35% of voids, either with simulations or effective mean approximations, be it the Maxwell-Garnett formula or the Brueggemann formulation, it's the same. So I would like to conclude
left.
Here.
Okay.
2 minutes.
Perfect.
Well,
perfect.
we
perfect.
Just have
well, 1 minute and a half.
yeah, well,
okay, perfect.
So yeah, a bit of some main points to conclude that for dielectric particles, we have the imaginary part of the scattering amplitude, which dominates and is much larger than the real part. This imaginary part is almost n times the Rayleigh term, so it's very simple to model, and is proportional to the mass of the aggregate. However, the real part commonly is mainly affected by correlations, hence extinction is. On the other hand, absorbing particles show that the imaginary part and the real part of S0 are of the same order of magnitude, so they cannot distinguish them, but they are no longer trivial to separate with Rayleigh-Gunst-Debye theory and to infer from the scattering cross-section, for example. Other examples in which effective mean approximations are effective are surprisingly very dense aggregates of mineral dust particles and highly absorbing fractal aggregates. So yeah, I would like to thank all my colleagues and the organizing committee of the conference, and I'm open to questions if we have time.
Okay, we have time for a quick question. Maxime, please.
Well, I have a technical question. On one of the first slides, you showed add the results with some error bars. So can you elaborate what it is?
Oh, yeah, thank you. That's the error bar we get from the rotational average. We didn't compute an infinite amount of simulations, but we are still close to the predictions. Yeah.
Okay, I see. Thank you.
Thank you.
Okay, I think we should move on. Any other question can be done by the chat.
Thanks.
So
I'll share my screen.
Yes, please. So Vanessa, can you share your presentation?
Yes. Well, it will be like this. And then it's better if I put it like this. And then, wait, sorry, I don't see the, this one. Yep.
Perfect. Okay. Yeah, our next speaker is Vanessa Tobón Valencia, and she will present laboratory microwave analog measurements and simulations of dust in planet-forming disks. So please go ahead.
Yeah, so hello everyone, I'm Vanessa Tobón Valencia, and today I'm going to present you some results of scattering properties of protoplanetary dust analogs using the microwave analogy. So I'm going to start to describing what is the problem that we have with this dust and protoplanetary disks, how we can solve it with the microwave analogy. how we produce our analogs, it means aggregates or rough surfaces, the measurement setup, and the results in terms of phase function and degree of linear polarization, and at the end, some work in progress. So the problem we have nowadays with this dust that it's found in protoplanetary disks is that actually we don't know the whole process of accretion. There's still some missing information to understand the growth process. So based on the core accretion model, if we suppose that this dust is completely spherical, compact, then we are going to have two problems. The first one is the radial drift barrier, which means this dust is not going to have enough time to aggregate. And the second one is the fragmentation barrier, which means this dust, it's going to have a high velocity toward the star. So actually they're going to explode and not to aggregate. So because of these two problems, there were some propositions last years that actually maybe the structure is not completely spherical or compact, but maybe we can find other kinds of structures like aggregates or irregular grains. And so here I show you an example of the stratosphere dust taken by NASA, and next to it, the objects we want to produce and measure. And so if we use astronomical observations, we can calculate the phase function and the degree of linear polarization. And so with this, we cannot control neither the structure, neither the material of this dust, which is normal because actually we are doing observation of nature. But because we want to understand more these scattering properties, we would like to control these two characteristics and how we are going to make it with laboratory measurements. So these laboratory measurements are done in an anechoic chamber, and we do these measurements with using the microwave analogy. So this microwave analogy proposed to respect two properties. The first one is the size parameter, which is the proportion between the radius of the dust divided by the incident wavelength. And the second one is the refractive index. So we are going to suppose that at this protoplanetary disk, we have just silicates without inclusions of minerals or carbon, which means we have silica. So the refractive index of our interest is 1.5, 1.7, and a small imaginary part. So it's the most simple scenario. And so if we start with the interstellar medium, the radius of this dust is going to be around 0.1 micrometers. Then we are going to have the whole accretion process, and we are going to arrive to planetesimal sizes, which are 1,000 kilometers. So we are interested in pebbles, which means millimetric, centimetric dust particles. And so knowing that we do these observations with the millimetric infrared wavelengths, then the size parameter of our interest is between 1/2 to 10. So now that we decide the two characteristics that we must respect to do this microwave analogy, how we are going to produce our analogs. So our analogs are rough surfaces and aggregates. So for the aggregates, we are going to use a GLA software to generate them. And so we choose to have 74 monomers based on the fractal equation. And each monomer is going to have a radius of 2.25 millimeters. And so the fractal dimension, it's supposed to be in this protoplanetary disk between 3 to 1.5. So we decided to choose 5 fractal dimensions from 2.8 to 1.5. And then for the rough surfaces, all of them, they are going to have an envelope sphere, a representative envelope sphere, which is around 60.25 millimeters. And so now that we know what is the size of each analog, and knowing that at the anechoic chamber we use incident wavelengths between 100 millimeters to 60 millimeters, then we can calculate the size parameter. So the size parameter for the aggregates are between 0.6 to 12, and for the rough surfaces between 1 to 6. And so then we decided to make a 3D printed of these analogs using stereolithography. And the material we decided to use, it has a refractive index of 1.7 plus 0.03. So it's going to have this refractive index at this measuring wavelengths. So now, how we do measurements? So we are going to have 2 antennas. The first one, it's the source, which is always fixed at the same position. And the second one is the receptor, which is going to measure all around the azimuthal plane. And so the object is going to be found here, located at the polystyrene mast. And so with the object, we are going to measure a total transmission, and without the object, we are going to measure an incident transmission. So then we do exactly the same measurement with the sphere, which is the calibration, and then we can talk in terms of field, a total field or an incident field. And then we make a complex subtraction to obtain the scattered field. And so with all the objects, so they are going to be positioned here, and the receptor is going to move all around these scattering angles. And so then the polyester mass is going to turn 10 degrees, and the receptor is going to remeasure all around these angles. And so at the end, we have 36 different measurements for each object. And based on the paper we published this year, we know how many minimal measurements we need to mimic randomness. So what I mean with this is that we mimic randomness by one object with multiple orientations. So here I present you this average of intensity, for example, with all black lines, which are all measurements, and then we do the average of all of them. And so for the aggregates, we need between 70 to 100 measurements, and for the rough surfaces, between 30 to 70. So now, with this scattered field, we can obtain the phase function and the degree of linear polarization. And so with the observation, we also can obtain these two properties. So at the end, the goal is to compare these laboratory measurements with these observations. And so I'm going to present you the aggregates. So here you have 5 different aggregates printed with 5 different fractal dimensions. And so I'm going to present you here the phase function with 2 types of lines, the continuous one, which is the measurement, the dashed one, which is the simulation, at 4 different colors representing 4 different wavelengths. And so I'm going to present just the smallest fractal dimension and the biggest fractal dimension, but actually we have all of the measurements. And so for the biggest fractal dimension, you can see the first lobe well-defined and the second lobes also well-defined. But if we look at the smallest fractal dimension, you're going to see that we have the first lobe and then the secondary lobes just disappear. Now, if we take a look to the degree of linear polarization for the smallest fractal dimension, we are going to see this bell shape, which is a Rayleigh behavior. But if we look at the biggest fractal dimension, you are going to have this bell shape just at 60 millimeters. And for the other 3 wavelengths, we are going to have these oscillations, which was predicted because actually this is almost like in a sphere. The sphere is fractal dimension 3. So it's normal that we have these mini oscillations. Now, the second track we wanted to investigate was the rough surfaces. So here I present you the rough surfaces, 5 different rough surfaces. So for the most rough surface and for the less rough surface in terms of the phase function and at the same for different wavelengths, you see the behavior, it's almost the same. So here I just present measurements, simulations are not still done. And so for this, you see that behavior, it's almost the same. There's just a little difference in terms of the levels. But if we take a look to the degree of linear polarization, you see that there's the biggest difference. So for the most rough surface, you are going to see oscillations between 0.5 to -0.5, while for the less rough surface, you are going to see oscillations that are a little bit bigger, which is almost a sphere, and oscillations are going to be between 1 to -1. So what we have been doing until here, it's searching the different behaviors of each object, of each analog, looking if there's a difference between the phase function, degree of linear polarization, and as you see, so there's actually a difference. So each object has a different signature, and this is essentially at the moment of the comparison with the laboratory measurements with the astronomical observations. And so another property that we can actually look at when we have the aggregates is the fractal dimension. So theory tells us that if we put the structural factor or intensity, which is observable in terms of Q, and we look at the fractal domain, we are going to have a slope which give us a fractal dimension. So we have here just an example, but actually we would do it with all the aggregates. So here we have an example of a fractal aggregate of 1.7, and actually the slope we obtained was 2, which is actually not the value that we wanted to obtain. So that is why nowadays we are trying to develop other ways to obtain this fractal dimension. And so to conclude, we know how to generate, produce these aggregates and rough surfaces, controlling the size parameter, refractive index, geometry, and orientation. Our simulations and measurements are coherent between them, and there's still some work in terms of the fractal dimension. And as perspective, we would like to analyze these two scattering properties with different size distributions. Actually, we do multi-frequential measurements, so we have the same object at different sizes. So we would like to mix up this to see what is the answer. And then the second perspective, it's like compare these laboratory measurements with observations. Thank you.
Okay, thank you very much for interesting talk. We have several questions. Yuris, can you?
Yes. Now you showed graphs with phase function being negative. It was denoted as S11. Usually S11 is amplitude function. Amplitude function, of course, can be negative, but if it is phase function, it is something very strange.
You're saying, wait, here, for example?
Yes, exactly. S11, negative.
Well, actually, for the ones that are near 60 millimeters, those are the hardest measurements. So maybe we are still working in calibration with the sphere, so maybe that is why. Yeah, but actually this is a log, it's logarithmic of S11 and logarithmic of the logarithm of S11. So actually it's normal.
Yeah. Yeah, it's supposed to be a logarithmic scale.
Yeah, I didn't put it, but yeah, it's logarithmic. This one and also the polarizations.
Okay.
Yeah.
Juris, any other question or? Okay.
Excuse me, just very brief comment on this negative value. It is yellow color, which corresponds to 60 millimeters, which is biggest. It should be on top. But in if you will show that figure again with intensity profile.
Yeah.
See, yellow color corresponds to 60 millimeters. Is it wavelength? Okay, wavelengths. Yeah,
That's
this is
wavelength.
Yeah, yeah. Then it makes sense.
Not the size of the particle. Yeah.
Yeah, the size of the particle. It's here, for example, X intermediate. It's 6, and X of the monomer. It's 0.3.
Yeah. It does make sense.
Okay, Maxime.
So my question is, you mentioned that you have disagreement between theory and experiment in some of the graphs. So what is your opinion? Why is it happening? Is it due to like theoretical errors or experimental or maybe morphology errors?
With that I have disagreement between measurements and simulations?
Yes.
No, at all. Actually, it's pretty, where did you see that? Because actually I didn't say that.
Well, you said like the first lobe is okay, and then the second it doesn't match at all. In some of the, I think maybe these.
Maybe I didn't say it correctly.
I think the upper the upper graph red line in the top plot here.
Here.
Yeah. So
this little difference you said.
Well, yeah, I mean, you just mentioned it, that there is some difference, that basically your minima and maxima are completely off.
Oh, I just said that actually I compare with the biggest fractal dimension, and actually I just said that compared with this fractal dimension, the secondary lobes disappear. Here we have secondary lobes, while here we don't have them. So it was a comparison with the fractal dimension, but not with the simulation. Actually, we think that simulations are really close. It's a finite element method, and so it's really close to what we are looking at the laboratory. So.
Okay, so, and one other short question, if I may. So have you tried simulations for your rough particles? Because I think they should also be quite easy to simulate.
Yeah, we still have not, there's still in progress, but yeah, we are going to do this and we are going to publish a paper about it. Yeah.
Okay, thank you.
Yeah, you're welcome.
Okay, I think we should move on. So any other questions in the chat? Let's go to this next speaker. Are you there? Are you there?
Yes, yes, I'm here.
Okay.
Yes, I'm sharing my screen. Yes.
So now, yes, next talk is on the tomography of irregular rough particles using interferometric particle imaging. So please go ahead.
Hello, everyone. I'm Barbara Delestre. I'm in PhD in Korea laboratory. So today I'm going to talk to you about tomography of irregular particles using interferometric particle imaging. We are particularly interested in Rosse irregular particles. In fact, the detection and characterization of such particles in flows is particularly important in fields such as combustion, spray, meteorology, nuclear safety, cosmetic, or even medicine. And unlike conventional microscopy, the goal is to observe particles of sizes that can vary from 10 micrometers to 1 millimeters with a wide field of about 10 centimeters square and with a working distance that can exceed 10 centimeters. A single shot technique that could tend to real-time analysis would be very attractive. Interferometric Rosse particle imaging, which consists in analyzing the speckled patterns generated by particles under laser illumination, is a promising candidate. So if we light up irregular particles, such as grains of sand or ice crystals with a laser, interferometric images are recorded, called speckle, and no model describes the scattering of light by irregular particles of any shape. The description of the shapes of ice crystals is a field of research in its own right. Now, if we illuminate a particle of this type still with a laser, we have the impression that it is full of emitters, which are distributed randomly on the particle. So from this hypothesis, we use a Fresnel formalism. So for example, if I take a particle that has a shape of a cross, I calculate its interferometric image and do its Fourier transform. And note that if I take a random distributions of the emitter on the cross, the interferometric images are always different, but the signature, the Fourier transform, is always the same. That is to say that there is a strong relation between the shape of the particle and the Fourier transform of the interferometric image. And the Fourier transform of the interferometric image is related to the 2D autocorrelation of the overall shape of the particle by the following relation. This relation has been validated experimentally in several studies, in most cases by comparing the binarized 2D autocorrelation of the in-focus image of the particle and the binarized 2D Fourier transform of the interferometric image of the same particle. It has been further reproduced with programmable particles generated with a digital micromirrors device, DMD. So here, a digital micromirrors device is schematized. The particle is composed of the micromirrors that are programmed on state that is say that reflect the laser light into the direction of an imaging system. Other micromirrors keep off state, that is say no reflection in the direction of the imaging system. Consequently, this device has become a powerful tool to test image processing algorithms in different configurations without having to wait for particles in the field of view of an interferometric particle imaging system. So here, a short video of the DMD experimental setup. So we program different shapes. So top left, a cross. Oh, yes. It's autocorrelation, its recorded interferometric image, and its Fourier transform. So another. And we managed to reproduce the simplified theory. Now we would like to return to the exact shape of our particle, knowing that from the Fourier transform of the interferometric images, we obtain the 2D autocorrelation of the shape, but it is not the shape of the particle itself. So now let's talk about tomography of irregular Rosse particle. So from the autocorrelation, we have been able to make first a family of shapes, which gives the same autocorrelation. We use the tree intersection method. We duplicate the autocorrelation twice, and we take the intersection of the tree autocorrelation as schematized here. And this can also be done with intersections in other directions. The shapes obtained have the same autocorrelation as the starting one. So we did that on experimental images. We binarized two Fourier transforms according to two views at 90 degrees to each other. We obtained 6 possible shapes for each of the views. So 36 possible particles. Their volumes are estimated with the schematized reconstruction process. And we notice that the volumes are not very far apart. And now, if we compare with the exact volume calculated with the in-focus images, we are not far from what was found. But we don't just want to be satisfied with families of particles. We were interested in 3 views configuration, and we started to work on algorithms which allow us to reconstruct from speckle no longer a family, but the exact form. So there you have different orientations of a dendrite, and at the bottom right, it's reconstruction obtained using a phase reconstruction algorithm, using the error reduction algorithm. We observe our 6 main branches rather well. So we do it on 3 views with the associated speckle, and we reconstruct the object in 3D. We do it for different orientations of the subject, and here is the result. Here, it's a comparison between the main face of the 3D reconstructed dendrite after retroprojection for 3 reconstructed views for an arbitrary orientation of the particle in the XYZ frame, first in figure A, and in figure B for an orientation of the dendrite such that its main face was in the XY plane. So this is for the tomography with 3 views, but it's still quite limited. And with the DMD, we can allow ourselves more things. So we are interested in what could result from scanner type configurations. That is to say, where there are cameras all around, we simultaneously record the interferometric images for each of the views. And once the reconstruction for each of the views have been carried out, we can do a reconstruction slice by slice, as would a scanner. To reconstruct a slice, we use the principle of filtered back projections. So we program with the digital micromirror device a particle according to 120 viewing angles separated by 3 degrees from each other. The corresponding interferometric images were recorded, and the 120 reconstructions were made with the error reduction algorithm. So we did first a 3D scanner type reconstruction using the filtered back projection with only 8 angles of view separated by 45 degrees from each other. If we look at it from an experimental point of view, it seems realistic. Knowing that we started with speckle images that seems to be noise at the start. And we did then a 3D reconstruction with 120 angles of view now. It shows what could be done if one day we are able to obtain 120 images as some scanner in medicine that use 120 views. So therefore, in progress or to come, test on real particle. So here are 3 view experimental setup in progress, actually. And also an important work of optimization of the algorithms. Thanks.
Thank you, Barbara. Very, very interesting work. Do we have any questions? Alexei?
Yes, thank you. You mentioned that you use some noise reduction algorithm. Could you comment how do you filter the noise?
How I filtered? Is the question? I do not understand. Sorry. Please.
I mean, at some point you mentioned that you use some noise reduction algorithm. Am I right to understand?
The algorithm that I used, the error reduction algorithm for the reconstruction. Sorry. For this reconstruction, for the 2-dimension reconstruction.
Yeah, and error reduction, right? Yes, how do you use error reduction?
How I use the error reduction algorithm?
Yeah, well, what is the algorithm?
It's a bit complicated to explain, but I like to reconstruct the phase of the Fourier transform of the particle. And for this, I use an iterative algorithm. And first, I start with the phase of the Fourier transform of the interferometric images. And after, with the interferometric images, which are the module of the Fourier transform, I just, I don't know how to explain.
Maybe you could give some references in the chat.
It's a FineUp algorithm, yes.
Okay.
I can answer in the chat more.
Yeah, thank you.
Okay, that would be the best. I'm afraid we should move on to the next speaker. Can you stop sharing the screen?
Yes. No, arrêté. Oh, sorry. Yes.
Okay. And Marwick is...
Oh, yes.
Hi, Dan.
I'll get this up here. So can you hear me okay? Can you see the screen?
Yep, we can see the screen, we can hear you, and you are going to talk principal components analysis for the simultaneous characterization of size and refractive index of dispersed particles in a fluid. So please go ahead.
Okay, thank you very much for having me. My name's Dan. I'm currently doing NGD research with Malvern Panalytical and University of St Andrews. It is a university industry partnership, so doing a research on an industry-focused project. So, for a bit of background, Malvern Panalytical, who I'm working with, create a range of instruments that use optical techniques to characterize particles. In particular, what I'm working with is laser diffraction. And this instrument, this technique is used in many industries, from pharmaceuticals to characterize the type of drugs, and food products to look at things like coffee and chocolate particle size. But in all these industries where it's used, it is not used by trained physicists or people who are trained in optics. And for this technique, knowledge of the refractive index of the material is key for determining particle size. As the mean scattering distributions rely on both Ri and size to calculate, and current least squares inversion methods that we use in instruments rely on knowledge of one property to actually determine the other, so we do need knowledge of Ri. So this method, which is aimed at untrained users, untrained being those not trained in optics, to get an estimate of Ri of their sample from a laser diffraction instrument to better get the size distribution that they actually want. So, going over to the instrument. So, the laser diffraction instrument, Master 3000, has 58 photodetectors, all in this scattering plane, using 2 instant wavelengths, a helium neon laser, which is picked up by all of the detectors, and it is a highly converging beam coming through this flow cell. It's dumped into the photon detector array, and roughly 1% of the light is then scattered and measured. However, the blue laser is only used on the detector modules on the outside. Typically, the blue light laser is used to improve the accuracy of smaller particles, and it's not necessarily needed in the photon detector array. So from these 50 red measurements and 11 blue measurements, we've got 61 virtual detectors there. Now, the instrument itself is used to get size distributions from 10 nanometers up to 3.5 millimeters. But this study is focusing on Ri, looking at diameters of less than 10 microns. Any much larger than this, then go into the geometric optics regime, where Ri is less important. So this started with creating a scattering model of the instrument, including internal optics to model the scattering distributions picked up by the instrument, and it was then validated against measurements. But as you can see on this bottom graph here, the detector numbers increasing with angle, that often the measurements, shown in green, have significant noise and look quite a lot different from the theory, which does interfere with the characterization. So that was one of the challenges here, both to get size and Ri quickly for the user and to overcome this noise problem. So to do this, we're looking at principal component analysis. that has a dimension reduction, which means that you can reduce the data set down to fewer dimensions to improve the speed of your regression, and feature extraction as well, which we're hoping would be able to extract the scattering information without the noise that's imposed on top. So what it can be used for is defining a new orthogonal basis, which analyzes data sets, and each principal components shown on the right here are orthogonal and show a different aspect of variation in each data set. These first few have the greatest variation, and using only 10 PCs, you can describe over 99% of the size and Ri variation. And each measurement you make, or each modeled scattering pattern you create, can be described as a linear combination of both the mean scattering pattern and a weighted sum of these PCs. Now, using principal components, we can see that the first couple of PCs do show strong variation with particle diameter and refractive index. Look at the first one here is a strong increase with the projected coefficient of the scattering patterns onto this first PC, although they are local minima, which would prohibit efficient searching through a scattering matrix. Ri is less a clean relation, but they do show strong variation. So with using many of the first few components, then you can hopefully get a good fit of size and Ri. So the way it's characterized is creating a modeled set of scattering patterns, a library or scattering matrix. Then these are then projected onto the PCs to reduce it down from 60 odd detectors down to just 10 PCs. Scattering measurements are then projected onto the PCs, and then the libraries are then compared. All the results here presented using nearest neighbor interpolation have looked at other regression methods, but the nearest neighbor seems to be the most efficient and no real sort of gain in accuracy from other methods we've tried. So initial tests, just using model data, of a set of modeled training and modeled testing data. So training data, looking at 1,000 sizes logarithmically spaced, as there is a wide size range from 10 nanometers to 10 microns, and 250 Ri values. The range 1.5 to 2.5, I'm told, is the typical sort of application space used for instruments. And testing, to look at sort of low and high size ranges within this range, 100 sizes from 10 nanometers up to a micron, showing this lower graph here, and larger sizes 100 nanometers to 10 microns. With the larger particles, we are seeing much more accurate characterization. A first pass here can get a good accurate estimation of Ri and a reasonable estimation of size as well. However, with the smaller particles shown down in figure 8, you can see that for smaller particles, as the scattering becomes more isotropic, approaching the Rayleigh range, estimates of Ri do become less accurate. But this is all after as an estimate for a user who does not know their Ri of their sample. So this sort of range is acceptable. Then this is then expanded further, opening up to complex Ri, such a third dimension of the scattering library, with size, Ri, and the matching component. It's tested against some model data, showing gold, silver, and latex here. Now, adding more complexity to the scattering matrix does show some erroneous results, some sort of local negatives being caught. You can see for the smaller particles of the gold and silver, you are seeing increasing errors of size and Ri here. And with latex even, you are seeing the odd outlier for which you might overestimate size and underestimate Ri, being a local minimum. So this could be improved by better implementation of the scattering matrix, but it does show feasibility of the method. And one last thing to include is size distribution, which is necessary for many samples. Not all samples can be monodisperse, and often they are not. And if polydispersity is not included in the scattering matrix you're comparing against, then you can get quite large errors in the return size and Ri. So in order to characterize samples with that distribution, you have to include it in your scattering matrix. That's what I'm showing here, results for, again, still model data, for how accurate size and Ri can be returned for polydispersed samples. The standard deviation I'm showing along this axis is the standard deviation for a log normal distribution, which is, again, is typical for many customer samples. In this case, a 40% corresponds to what we call a decade, one that expands a whole order of magnitude from 1 micron to 10 microns. So the fact that we can get accurate size and RI back for under 60% is a very good sign, at least for the size. However, for RI, for the small particles, we are running into the issue where we are finding local minima that are quite separated from what we're looking for. RI errors of 25% are quite unacceptable. So that restricts the range of usefulness of this method. In the end, what we want to do is to characterize measured data with data measured instrument with noise. So first of all, we looked at a data set measured with the mass slicer itself. This is just using polystyrene lattices for 8 different sizes, specifying in water, from 60 nanometers up to 9 microns. And from this, we created a scattering matrix using only these data sets and looked at the principal components of this data set. Now, unlike the model data sets, you see the first 2 coefficients here don't show a strong separation with size. There's a lot of overlap between these histograms. So that indicates that the variation being captured here by these first couple of PCs is not the slight information we're wanting. On the other hand, you look at in the higher order of coefficients, we're seeing more separation. So it seems that the size information has been captured at these 3rd and 4th PCs, which indicates there's quite a difference in structure in the model data set. And although this seems to be capturing not size information, it's possibly noise being captured here. We found that it wasn't possible to reconstruct scattering patterns without these components. So it wasn't possible to denoise in this way, although some denoising was achieved by cutting off the high order components beyond the 10th. To have a quick check to see how accurate this can be, we have to leave one out validation. This is where we would take one measurement out of the data sets and attempt to classify it using the other scattering patterns in the scattering matrix, and then see the accuracy of how this can determine the size of the particles in the sample. Now, for most of the size range, 200 nanometers up to 9 microns, we are seeing accurate characterization, which is good given these large steps involved. We expect a good characterization, but unfortunately, in the smaller region below 150, we're seeing much less accurate return of size. Seems there's a lot of confusion around the size at this range. We are using very close sizes here relative to the rest of the data sets. But it seems like the noise in data sets is shifting the measured scattering pattern enough that appears to have the features of different size. But still 80% and 7% accuracy, which is supposed to get a good estimate. So moving on to the general methods, which was to characterize particles in the measured data sets using a previous modeled scattering matrix. But the results of this side here, which shows that this method is not entirely accurate. We have compared this against a simple regression method, just regressing the scattering patterns against themselves to show the accuracy.
Sorry, Dan, 3 minutes left.
Oh, that's fine. I'm coming towards the end anyway. Thank you. So yes, it's the larger particles. We are returning good size estimates and good RI estimates. There's quite a lot of variation here. We've shown this error bars as the repeatability or standard deviation. And it was quite wide error bars here. Typically, if there's a diffraction, customers want very narrow repeatability, even if the accuracy is slightly off. But as we are seeing with the leave one out, there is a lot of errors and a lot of variation with these in the size errors and the RI errors for these small particles. And although one point to note out here is that although PCA is appearing to be more accurate than the direct regression for RI, all that's happening here is a tendency for one method to go to the small RI end of the scattering library, the other method to sort of tend towards the the larger end of the scattering library. In practice, they're both are poor estimates of RI at this size range. So it seems that scattering noise is still an obstacle. And just to bring us to a conclusion, so demonstrating the use of PCA as a tool for characterizing laser diffraction measurements, we are seeing the dimensionality reduction in calculation time regressing over only 10 dimensions rather than all 68 dimensions, reduces the time by a factor of 3. But the feature extraction nature of PCA is not sufficient to overcome instrument noise as it is in other applications. So next steps to improve the methods. I'm currently working on incorporating noise into model training sets. I've done a lot of work in accurately characterizing the noise within the instrument. Thanks to some good talks here, I've seen some whole literature review in terms of including prior information. There's definitely a couple of things that can be included here in terms of non-zero scattering peak and in terms of the back scattering ratio, the ratio of the forward to backward scattering intensities that can be used to improve accuracy of small particles. And of course, if these can get around the noise issue, can then expand this with optimization of scattering database to narrow down the errors in the size and RI that are returned. But the big underlying takeaway is that accurate accounting for instrument noise is necessary if you want to characterize the size and RI of these particles. And that's what I've got for today. Thank you very much.
Okay, thank you. Alexei, we have time for a quick question.
Thanks. I wonder first, is there a way to relate the principal components with physical quantities? And the second short question, if you face particles of complex shape, do you expect that the required training sets would increase significantly?
So for your first question, I have looked into this and I don't believe there's a direct relation between the PCs and any sort of physical quantities. They are a mathematical construct related to the data sets. It doesn't matter. I think there's no physical quantity I can see that relates to these PCs. I can skip back to show you what the PCs look like for the modelled sets. And I can't see any sort of physical quantity that would relate these to anything I can see. But in terms of including complex shape, then yes, I do believe that more complex shapes would have to be included in the training sets, based on my experience with including polydispersity. If you attempt to characterize more complex particles without in these training sets, then you would get errors in size and RI on top of what the method already gives.
Okay, I think we have to move on to the next speaker. Thank you, Dan, for your talk.
Thank you very much.
Prakash, yeah. Can you put it in presentation mode? Yeah, perfect. Okay, next speaker is Prakash Gautam. He will talk about design of a multi-angle light scattering setup covering the whole scattering angle range and interpretation of light scattering data under request-based analysis. So please go ahead. Oh, sorry. Please go ahead. I was talking. Prakash, your microphone is off.
Okay, now hearing?
Now it's working. Okay, please go ahead.
Thank you for the information. And welcome everyone. So as it shows, I'm going to talk about design of a multi-angle light scattering setup covering the whole scattering angle range from 0.32 degree to 177.6 degree and interpretation of light scattering data under Q-space analysis. So, importance of this setup. This setup is able to measure light scattering from extremely small angles to a very large angles. The light scattering data from extreme forward and back direction is important to understand scattering due to aerosol particles. From extreme, one can determine size of particles through Guiner analysis, and from back direction, and the data are important for remote sensing measurement, and the backscattering is very sensitive to the refractive index and size of the scatter. Many experiments were built in the past, but none covered the whole angular range like this experiment, especially missing the extreme forward scattering angles. Here is the setup. So here we have using a 532 nanometer laser light, and we are using two multi-channel detector. This detector is for forward, and this detector is used for side scattering and back scattering. So, and here you can see a scattering volume, and we calibrate the forward scattering by using a single slit and we put the single slit here, and then the scatterer light is measured from 0.3 degree to 9 degree from forward detector. And for the side scattering, we used a custom elliptical mirror with scattering volume at the near focal point of the elliptical mirror and iris at the farther focal point of the elliptical mirror that block the stray light, and we use the collimating light to collimate the scatter light. And for the back direction, back scattering, we use a parabolic mirror through holes, and this parabolic mirror collect the scatter light from 158 degree to 177.6 degree. Here we have been using two mirror we have been using here two mirror to reduce the width of the beam. Here the beam width is 22 mm, but our detector width is 11 mm, around 11 mm. So we need to reduce the beam width. That's why we use two lenses as a Keplerian formation configuration, so that we reduce the beam width 22 mm to 11 mm that match with the detector channel. Here from these two detector, we have been able to measure the scattering from 0.3 degree to 177.6 degree. Instead of detectors, this detector, we can use another detector directly here as well. But right now we are using the same detector for side scattering and back scattering. And to connect these two detector 1 and detector 2 has a different sensitivity. That's why we use this setup to calibrate to connect the forward detector to the side detector. For this, we have used two mirror to change the direction of the incident light by 6 degree, to offset the incident direction by 6 degree, so that the 15 degree on the 15 degree of the side detector will be reduced by 6 degree to become 9.3 degree. This 9.3 degree of the side scattering detector correspond to this region in the forward detector. With this, we can able to get the calibration factor to connect forward detector to the side detector. And here is the view of real experimental setup. This is the laser, and here is the parabolic mirror. This one is elliptical mirror, and Fourier lens beam stop is used to block the direct laser light, and this is detector 1 and this is detector 2. This detector is used to collect the scatter light from 15 degree to 178 degree. And here this is the side scattering, and this arrangement is side scattering arrangement, and this arrangement will give a back scattering, will collect the back scatter light. So here is the collimating lens, and two lenses are here, and mirror is used to direct the direct the scatter light from here to here, so that we will able to get, so we don't need to move the detector. So from these two detector, we can simultaneously measure the scattering from 0.3 degree to 157 from 46 different, from 31 different channels simultaneously. And here this is the scattering volume. You can see this is the aerosol tube. Aerosol is coming vertically off, and laser strike this aerosol, and you see a scattering volume, and the aerosol particles are gone through the food. here is the calibration, forward scattering calibration. For forward scattering calibration, we use a single slit for a 10 micron wide, and we diffracted the laser beam through 10 micron single slit, and you can see here the slope of -2, and the same data is plotted for the theta space and q space. Q space is depends on the q space is inverse of length scale, and here you can see a slope -2 that is uh, represent the match between theory and experiment. The same data are plotted in the theta space. You can see no quantifiable pattern here, but here you can see a pattern, -2 dimension for single slit. And alignment of side scattering. For side scattering, we use glowing capillary calibration, glowing capillary tube. For this is the scattering volume, and laser gone through this direction, and we put the glowing agent inside the capillary tube and black tape the capillary tube with this region, and this dimension is equal to the dimension of scattering volume, and the scatter light from the reflected light from this elliptical mirror is blocked by this portion, black tape capillary tube, and only you will get this light reflected from this portion, and that arrangement will collect the scatter light greater than 90°, and you reverse the position of the capillary tube and you collect the scatter light less than 90°, and by combining the intensity measure from these two arrangement, you will see a uniform intensity. Here the length scale is in a linear scale 0.9 to 1.1, and then all data are within the experimental error, like 5 to 6%, 7% variation. With this, we are able to align the side scattering. Here, alignment and calibration of back scattering. So for back scattering, we use diffuse reflector from Thorlabs, and at the scattering volume, we use this diffuse reflector and laser gone through here, and this diffuse reflector scatter light to the back, and you will see the circular shaped back scat light on a white sheet of paper. The dimension is equal to the dimension of this parabolic mirror, and by moving this sheet from near to parabolic mirror to the detector, you will see no change in the dimension of this shape, circular shape, so that align your parabolic mirror, and then you insert these two lenses as a Keplerian to reduce the diameter of the beam that match the diameter of the detector. So connecting forward scattering to side scattering, we have two different detector 1, detector 2, and they have different sensitivity, so that we have to connect the forward scattering to side scattering. Here you can see these data are the calibrated data from figure 1 and figure 2. I showed this in earlier slides, and this is the forward scattering intensity. So the intensity this intensity correspond to the same angle, that should be equal. So from here we will find the multiplication factor, and that we multiply this intensity, and you will see a calibrated scattering data. Here I'll show you data about why Q space is important in the forward scattering data analysis. So we have been scatter light from hematite, which has a very high refractive index, real and imaginary part 3 and 0.5 at studied wavelength 532 nanometer. Here you can see in ABC scanning electron microscope pictures. From here you can see the hematite are aggregated in nature, and from optical microscope you have seen the particles are bimodal in size distribution. So in order to know whether these aggregate are fractal or non-fractal, we did the ultra small angle X-ray scattering, and from here you can see the calculated structure factor and ultra small angle X-ray structure factor are matching well enough and giving a slope of -4 with the dimension -4 and -4. This dimension q value correspond to the monomer dimension and size of the monomer, and this correspond to the size of the aggregate. Both -4 indicate that the aggregate are non-fractal in nature and monomers are as well. So here this is the result. Here I am focused on forward scattering region only, and the same data plotted in Q space and theta space. In theta space, this region is 0.3 degree to 10 degree, that is measured by forward detector, and you see no descriptable pattern here. But at the same time, when you see in the Q space, you can see a extended Guinean regime having two Guinean regime, this in that region and in that region, and we can call this extended Guinean regime. And this is due to the fact that our particle size distribution are bimodal. Some are very big and many particles are smaller in size. So this region correspond to the 10 to the power 4 per cm correspond to 1 micron, and this region correspond to the 10 micron. That is well explained by the optical microscopy picture. So from here, Q space analysis indicates that from Q space analysis we got more information that do not provide by the theta space. Conclusion. We designed and built our laboratory light scattering apparatus for aerosol covering the scattering angle range 0.3 degree to 177.6 degree with notable resolution towards extreme forward scattering. Q-space analysis is found to be better method to analyze the forward scattering than plotting versus scattering angle, but at bigger angles, linear theta plot works well. Thus, application of both theta space and Q space analysis is needed to get a complete description of scattering differential cross-section. It is observed that if one is to perform a scattering experiment to study back scattering, one must use forward light scattering data to determine the size. And if the particles are in micron size range, one needs very small angles. Thank you.
Thank you, Prakash, for a very interesting talk. Congratulations for a beautiful setup. Do you plan to do, apart from intensity measurements, do you plan to measure any other elements of the scattering matrix?
Yes, I will plan to measure a whole scattering matrix degree of linear depolarization for different particles, and yeah, this is the next.
Okay. Good luck. Okay, Vanessa.
Yes, there is a diagram that you show in which your slope was -4 as fractal dimension, and I don't know if, yeah, that one. Actually, -4, isn't it for the sphere, representing the sphere?
Yeah, sphere. You can say sphere, and for a solid particles, not only sphere. For 3-dimensional solid particles, you have a surface dimension, mass scaling dimension 3, and surface scaling dimension is 2. That gives us -4.
Yeah, but you obtained that. Maybe I didn't understand. You obtained -4 for which? For the aggregate?
Yeah, for aggregate. Here,
And
our aggregate size is around 10 micron, and this length scale corresponds to the 10 micron, this region. And you see here the
you obtain -4. So yeah, because I'm also obtaining sometimes when I'm trying to define this fractal dimension between 3 to 4, even if the fractal dimension is lower. So I was asking myself, maybe it's the refractive index that it's very high, because most of the time we suppose that the material is transparent. And with that hypothesis, most of the time, this determination of the fractal dimension, it's correct. But I don't know if that's correct, the thing that I'm saying. Can you comment on that?
Oh, how can I explain this? Maybe, but refractive index obviously affect the fractal dimension, but I'm not sure right now.
Okay, well, thanks.
We can talk on the chat in other, yeah.
Okay.
I am very happy to interact with you in other way. Yeah.
Cool. Okay, thank you.
Okay, any other question, comment? Okay, then we should move on to the next talk that is supposed to be given by Yang. Is it here?
Yeah, I'll be giving his talk. I'm his
okay.
PhD advisor. Yeah.
Okay, so please share the screen.
Can you see it okay?
Yeah.
Yeah, okay, great, thanks. So my name's Chris Worth. I am Jerry Ann's PhD advisor. He's on internship right now, so he is not able to give the talk, but I'll do my best. So today I want to talk about an experiment that we're developing based on evanescent wave scattering. And the main goal, as you'll see, is to track the dynamics of anisotropic particles near a boundary. Okay. So the experiment that we do, the base experiment that we do, is something called total internal reflection microscopy, TRM. And what I'm showing here is the basic TRM experiment for a spherical particle. So if you have an incident beam at above the critical angle, you produce an evanescent wave that propagates along a substrate. The intensity of that wave decays exponentially into solution. And the decay length for our setup is typically about 100 nanometers. If you have a particle that's very near that boundary, it will scatter light with an intensity that decays exponentially into solution. And it'll depend upon the separation distance and this decay length. Okay, and this is just an experiment from our lab where we track the particle in the XY plane, but then also via collection of the intensity, we can calculate the fluctuations in height, basically the fluctuations into the board. Okay. It seems like my slides are held up a little bit. One moment. There we go. Okay. So by collecting this light intensity, we can then, like I said, calculate the height. And then assuming a Boltzmann distribution of positions as sampled by the particle, we can calculate the potential energy profile. Okay. So this basic experiment has been around now for about 30 years, and it's very useful for measuring weak colloidal forces. That's what we're interested in. I'm a colloid scientist, and we're interested in measuring things like electrostatic repulsion, van der Waals attraction, weights of particles, things like that. You can also measure non-conservative interactions, so like hydrodynamic interactions and things like that. And it's typically weaker, it's typically capable of measuring forces that are weaker than AFM and SFA, AFM being atomic force microscopy, SFA being the surface force apparatus. So this is great. Yeah, so this is just a potential energy profile. I mentioned electrostatic repulsion, particle weight. So this is great, but the thing is that most particles in the real world are not isotropic spheres. Most particles are anisotropic. In particular, I'm showing a number of particles from the natural world, right? So these are all natural colloids, biological colloids. But then, of course, you could assemble a similar kind of number of examples from industry. You know, clays and things like that are often anisotropic. And that's really kind of a big effort in our lab is applying many kind of typical colloid science experimental techniques to anisotropic particles, as I'm showing here. And there's lots of examples now in literature, especially over the last 10 years, of people who've been able to develop anisotropic, colloids, micron scale particles. So if you simply make some anisotropic colloids and then you try to do TRM with them, you'll see that it doesn't really work very well because scattering intensity depends not only on height, as I'm sure everybody listening probably would intuitively know, depends not only on height, but it also depends on the angles. Depends on the azimuthal angle and the polar angle. And this is for an anisotropic particle that's just non-spherical, right? There's also anisotropic particles that can be chemically non-uniform. They could be spherical, for example, but they could have different compositions, and that would also be an anisotropic scatterer because it's optically anisotropic. So we are working on basically utilizing TRM in a way that would be suitable for anisotropic particles, and this is essentially a map of our strategy. So rather than collecting the integrated scattering intensity, what we do now is we collect the scattering morphology. So we take images of the scattering, and then we analyze the image rather than just like integrating the total intensity. So the basic premise here is that for the ellipsoid particles, we collect the morphology, and then we parameterize that morphology by fitting a 2D Gaussian to it. And from the 2D Gaussian, we can calculate or we can measure the angle of that morphology, and we can also measure the aspect ratio of that morphology. And this is different from the spherical case, because in the spherical case, there's typically no morphology angle, and there's typically a morphology aspect ratio equal to 1, although we actually just recently published a paper showing at what conditions this is true. This is not true actually for all conditions. There's as the particle gets bigger, this becomes less true. But for the purpose of this this discussion, I'll just leave this here. So then, if you take these parameters from the ellipsoidal particle, the angle and the aspect ratio, you can then, in principle, calculate the azimuthal and polar angles from this morphology. So really the main difference, the thing that I want to impress upon you is that the main difference between conventional TRM and scattering morphology resolved TRM is that rather than just collecting this integrated intensity, we're actually going to analyze the image of scattering. Okay, so for the rest of today's talk, I'm going to be describing some experiments that we're doing that shows the relationship between particle morphology and orientation. Okay, so we make ellipsoidal particles in a pretty kind of standard way. It's been used now for 25 years, I think, where you take polystyrene spheres and you disperse them in a PVA film. You can then use a stretching apparatus to first raise the temperature of the film to above the glass transition temperature, and then you stretch it uniaxially if you want prolate ellipsoids, which I'll be talking about today. But you can also actually stretch it biaxially. That I'm showing here a biaxial stretcher to make oblate ellipsoids. So we do this, and these are just some kind of poor, actually, SEM images of our low aspect ratio and our high aspect ratio ellipsoids, and then we can characterize them and get the actual quantitative measures of the aspect ratio, which here is 1.7 and 3 for the low and the high aspect ratio ellipsoids, respectively. So then the first experiment I'm going to be talking about is where we take ensembles of these particles. So we take lots of ellipsoids and we put them in solution, suspend them. We then add a lot of salt to screen the electrostatic repulsion so that they deposit on the substrate on which the evanescent wave is propagating. And the orientations of these ellipsoids are basically totally random. So in that way, we get lots of ellipsoids at random primarily azimuthal angle orientations, but all at a single height, all at a height of 0. And then we illuminate them with the evanescent field, and we collect their scattering morphologies. Okay, so here are some experimental data. So I have the bright field images and then the TRM images side by side for low aspect ratio and high aspect ratio ellipsoids. So you can see that there is this just from the images, there is a qualitative relationship between the azimuthal angle and then the morphology angle of the scattering. And then indeed, if we do the analysis for both low and high aspect ratio ellipsoids, if we do the analysis, we see that there is this relationship with the data that I'm showing here kind of looks almost linear for both low and high. The one thing, I won't talk a lot about it, but the one kind of interesting thing about these mapping experiments is that there's kind of dark regions, which we can now explain. At the time we couldn't, but there's dark regions where the scattering is very, very low intensity, and it depends upon aspect ratio. It depends upon azimuthal angle. So for these data for the high aspect ratio ellipsoids, there's regions below 60 degrees and above about 120 degrees that we don't have data for, at least for the set. So that's a good start. So we see the morphology angle depends on azimuthal angle. So then we wanted to compare these experiments to prediction. So we worked in collaboration with the University of Bremen to utilize a simulation based on the T-matrix method. I'm not going to really talk about this at all, but the important part is that it produces an image. So it calculates the scattering field, but then it also is able to produce this image of scattering, which is based upon the basic experimental setup that we're using. So here I'm showing simulated images, again, bright field in TRM images for the low aspect ratio and the high aspect ratio ellipsoids. And then in the upper right-hand corner, I have the experimental data compared to the simulated data, and for both low and high aspect ratio ellipsoids. And then I have the error between the two shown in the bottom right. And you can see that the simulation kind of reveals that's more of a sinusoidal dependence between morphology angle and orientation. And then the kind of interesting thing here is that this error, is on the order of 5 degrees, which is about or better than the error that you would expect from just using bright field to resolve the azimuthal angle, which actually is like the easiest of the two angles to resolve for an ellipsoid. The azimuthal angle with just regular microscopy imaging, you can measure it directly, but it's really the polar angle that's difficult.
Chris,
so we wanted to check kind of what kind of dependence morphology has on the polar angle. So so here I'm showing an ellipsoid at fixed in this cartoon up here at fixed azimuthal angle, but systematic variation in polar angle, and we see that the morphology angle actually does not depend very strongly on the polar angle, but it's actually the morphology aspect ratio that depends very strongly on the polar angle. So here you can see this kind of qualitatively from the images. And then I have quantitatively up here in the right, and then the bottom right. So there's clearly an issue still with these measurements, though, because there's lots and lots of scatter. So one of the things that we've really worked on over the last year is figuring out what the origin of the scatter is. And it turns out that, and this you might have kind of intuitively kind of guessed this, is that each of these measurements is for a different ellipsoid. So each measurement comes from a different ellipsoid that has potentially different volume, different aspect ratio, also a different position within the evanescent wave. So for those of you who kind of have done the experiment, you recognize that the evanescent field does not cover your entire substrate. There's actually a decay in intensity towards the edges. so we wanted to update our experimental apparatus to eliminate this variation. So we wanted to basically do mapping on a single experiment. So my student, Jerry, this is...
Sorry, Chris, 1 minute.
Yeah. Oh, okay, I'll finish up.
Yeah.
I'll finish up, sorry about that. Okay, so we now do mapping on a single ellipsoid via this rotational mount, because we can just look at one ellipsoid and take all the measurements. And on the left here, I'm showing data from a single ellipsoid. On the right, I'm showing the original data. And you can see the noise has basically been eliminated by using this single ellipsoid rather than many. So sorry, I went kind of right up against the time limit, but hopefully you've learned something about our technique here at TRM. And we're basically, one of the things that we're really interested in now is applying this to real systems. So here I'm showing a red blood cell that's adhered to the surface, and we're starting to work on understanding how the scattering depends upon its adhesion state. So I'm happy if there's any time I can take questions, or you can email me. Thanks.
Okay, thank you. I'm afraid we have run out of time.
Okay.
So if anybody has some question, can do it by the chat, or just send an email or something. But thank you for a very interesting talk.
Sure,
so
thanks.
I think this session is finished. So thank you very much for all the speakers, and I really hope we can meet in person in St. Petersburg to have a real coffee break, some chat about the talks. So thank you, everybody.
Thank you very much. So we will continue in 5 minutes.
All right, everybody. Welcome back from the quick break. My name is Jan Virki and I'll be your chair for this session. And our first speaker will be Evelyn Hesse. And her title is entitled Physical Optics Beam Tracer Models for Smooth and Rough and Spherical Particles.
Greetings to everyone, and thank you for the introduction and for the opportunity to present at this conference. As said, the title is Physical Optics Beam Tracer Models for Smooth and Slightly Rough Particles. These are methods developed at the University of Hertfordshire. The first method, beam tracing with beam splitting, was developed by Lawrence Taylor during his PhD. And Elizabeth Martin has already presented applications of beam tracers at this conference when she looked at the interpretation of CAST-ATREX campaign data. The second model is the tracing of small triangular beams. Yes. This already gives away the motivation for this work. So in order to better understand the role of cirrus ice, detailed information regarding size and morphology is required. Optical array probes used in situ, like the cloud particle imager, capture images of ice crystal shadows, which can be used to extract morphological data. However, at small sizes, these techniques suffer from optical aberrations and constrained depth of field. This is not encountered with instruments from the small ice detector family, which capture forward scattering light in the range from 6 to 25 degrees. However, for these data, image inversion is required in order to obtain the information about particle morphology. Elizabeth Martin gave already on Wednesday a talk about the interpretation of light scattering patterns from the CAST-ATREX campaign. The method, so the phase-dependent electric field amplitude of beams on a facet is determined through the Fresnel equations and phase tracing. And for outgoing beams, the electric near field is mapped to the far field via a surface integral formulation of the vector Kirchhoff approximation. I start with the first method, beam tracing with beam splitting. An incident plane wave hits the particle. And we have here particle A, the incident light comes perpendicular to the screen and 3 facets are illuminated. In particle B, we show the beam tracing from this upper left facet. There is external reflection, which is not shown, but also transmission into the crystal. So from each of the vertices, the ray is traced into the crystal according to Snell's law, and the beam tracer algorithm will separate these hit areas to define the intersection areas at the different crystal facets, shown in C in turquoise, pink, and green. External diffraction is modeled as diffraction at the beam-facing facets based on Babinet's principle. And the total far-field amplitude matrix is obtained by combining beam tracing and external diffraction amplitude matrices. The computational cost is size independent. That's a very relevant point. and computational demands of the method are low, of the order of a minute on a standard desktop computer. First example, I want to show a comparison with DDA for a smooth hexagonal prism. We would like to thank Antti Pantila and Timo Noisiainen for the DDA computations. So we have here a hexagonal prism. Refractive index is 1.31 plus 0i. And then again, incidence perpendicular to the screen, and the particle orientation is shown in this figure. We have comparisons for size parameters 20, 40, 60, and 100. And the two left columns show us comparisons in the forward scattering hemisphere. The beam tracer results are shown left, DDA right. And we find quite good agreement for all size parameters. And it's similar in the backscattering hemisphere, which is shown in the two right columns. Here we see the azimuthally integrated signal, which is the phase function for this fixed orientation. Again, we have size parameters 20, 40, 60, and 100, and these four orientations. The beam tracer results are shown in blue and the DDA in red. So we find overall quite good agreement. On the next slide, I show a comparison for random particle orientation with data obtained from improved geometric optics, which is Ping Yang's method. And I compare with data from his 1996 paper, which are shown in the lower row here. So we have a hexagonal prism of aspect ratio L/A is 1, so it is a thick plate. Wavelength is 0.55 micron, refractive index 1.311, and we look at size parameters 20, 60, and 180. The left column shows the phase function. The top row is for the beam tracer results. So the largest size parameter has the sharpest peaks, and the features become more blurred out for smaller size parameters. Overall good agreement. In the middle column, we see the degree of linear polarization. Again, agreement is fairly good. And in the right column, we see P22 over P11, where we have slight disagreement in the close to back scattering. On the next slide, we see the rest of the phase matrix elements, P33 over P11, P minus P43 over P11, and P44 over P11. So overall good agreement. There are sort of slight discrepancies in the 120-degree region for P43 over P11, and in the backscattering for the small size for P44 over P11. Next, I want to present the tracing of small triangular beams, which is a method applicable to any particle geometry, but at a higher computational cost. So first, I want to present results for a smooth and slightly rough hexagonal prism. The incident plane wave is split into triangular beamlets as it hits the particle. The edge length is in the range between 1/4 and 1/8 of a wavelength. The three intersection points form what we call an intersection facet, for which the Fresnel amplitude reflection coefficients are computed. For the reflected beam, the far field is computed using the Kirchhoff approximation, and external diffraction is modeled as diffraction at the beam facing facets based on Price-Babinet principle. And again, the total far field amplitude matrix is obtained by combining beam tracing and external diffraction. Here we see the results for smooth hexagonal prism of refractive index 1.31 plus 0.1i, so it's strongly absorbing. again, size parameters 20, 40, 60, and 100. And the reflection peaks become more pronounced for increasing size parameter. The DDA results are shown in black here, and the original beam tracer in green. And we did some improvements in order to reduce the side scattering. So the final results are shown in red. The largest size parameter, x equals 100 plots, show also the results for classical geometric optics, which is a combination of diffraction at the projected cross-section, which gives us this baseline, and geometric optics ray tracing, which gives us the reflection peaks as delta peaks. Here are results for an absorbing prism with Gaussian random surface. The crystal model was produced by using Christopher Collier's code, which is based on a paper by Kari Manonen and Saarinen. And again, the prism has a radius of 5 micron, length 10 micron. The standard deviation is 0.1 micron, and the correlation length 0.5 micron. We see the scattering patterns on the left-hand side. So the upper row is the beam tracer, the second row is DDA for the forward scattering. So we can see good agreement even in the shape of the reflection maxima and also in the speckle pattern. Similarly, we see in the third and fourth row the backscattering hemisphere, where we see this sort of brightened area in the lower center, which is due to the reflection peak from the prism facet, so, from the basal facet. So on the right-hand side, we see the azimuthally inter-averaged signal, and red is the beam tracer, black DDA, and we saw also in gray the classical geometric optics result, which cannot give the shape of the reflection peaks, the confined shape. And also the backscattering is very low. Oh.
Please wrap up in the next minute.
Yeah, thank you. I don't know what happened here, sorry. These are results for a transparent prism with a smooth surface, size parameters 20 to 100. And we see again the beam tracer results, first column, DDA second for the forward scattering hemisphere, similar for the back scattering hemisphere. On the right-hand side, we see the integrated signal for size parameters 20, 40, 60, and 100. And we have reasonable agreement, in particular for large size parameters. Here we have transparent prisms with Gaussian random surface. I show you just one example for size parameter 60. Same roughness, and we find here that the DDA pattern gives, the beam tracer pattern gives us the reflection peaks in a proper way, and also the speckle size. However, the transmission peaks don't appear. And on the right-hand side, we see the integrated signal, which is sort of slightly higher in the middle side scattering and slightly lower in the back scattering. So this approximation at the interface needs further work. Just to summarize, I introduced two beam tracer methods. The beam tracing methods with beam splitting, which is a computational fast method, have been demonstrated for hexagonal prisms. We have shown comparisons with DDA, and the computational cost is size independent and very low. I also introduced the beam tracing of small triangular beamlets, and this has the advantage that it's applicable to particles of complex shape, but at a higher computational cost. If show,
you are out of time.
Okay. Thank you for your attention. Yeah.
So there's one question from Nancy, but maybe you can write the question in the chat. So we can answer it there. And the next speaker will be Claudia Emde, and her talk is entitled IPRT Polarized Radiative Transfer Model Intercomparison Project, 3-dimensional test cases.
Okay, do you see my screen and can you hear me?
Yes.
I will start. Yeah, my name is Claudia Emde and I'm from the Meteorological Institute in Munich in Germany. I would like to present you a polarized radiative transfer model intercomparison project. And today I would focus on 3-dimensional test cases. The main contributors to this intercomparison project were Vasilios Balakas, Céline Cornet, Frank Evans, and Zheng Wang. So our motivation for this work is that we all know that when we use polarization for remote sensing of aerosols and cloud optical and microphysical properties, this gives us better accuracy compared to using intensity alone. And there are now a number of instruments that actually measure polarization, airborne instruments and satellite instruments. I've just written down a few of them here. This image here shows an image of our airborne instrument called SpecMax. And on the left-hand side, you see an RGB image of a cloud. And you can nicely see here the cloud bow feature and also the shadow of the aircraft here. On the right-hand side, we see the corresponding degree of polarization, and we really nicely can see here the cloud bow. And from this feature, we can derive information about the size distribution of the cloud droplets with really high accuracy. The retrieval algorithms for these instruments require efficient and also accurate vector radiative transfer models. And mostly 1-dimensional plane parallel models are applied for this. However, we know that in reality, the atmosphere is not 1-dimensional. Therefore, we need 3-dimensional vector radiative transfer models at least to quantify the errors of the 1-dimensional approximation. I just want to introduce the International Working Group on Polarized Radiative Transfer, which is a working group of the International Radiation Commission. And aims of this working group are to compare and improve radiative transfer models and to provide benchmark results. And yeah, it is really important to have this benchmark results to develop for model developers so that they can check whether their new models are correct. If you need more information about this working group, you can check out this webpage mentioned here. Here, I just want to show you a list of recently published benchmark results for polarized radiative transfer. The first intercomparison done within this IPRT group was for 1-dimensional plane parallel geometry, and we have defined a large number of different test cases, including ice cloud, water cloud, surface reflection, aerosols, and yeah, all we were able to establish benchmarks using various different radiative transfer models, and these have been published in 2015. The next project was for the 3-dimensional model atmosphere, and I will show some results of this intercomparison later. And the results have already been published in 2018. I would also like to mention further intercomparison studies, one for a coupled atmosphere-ocean system. So this also considers radiative transfer underwater. And results of this intercomparison and corresponding benchmark results have been published last year by Jacek, Chode, Harry, and colleagues. And finally, I want to mention ongoing projects for spherical model geometry, because our Earth is not plane parallel, as we know. And yeah, one intercomparison have been published this year, and that focused on limb scattering geometry. And another more general for spherical geometry is currently in preparation. There was a talk about this on Wednesday in this meeting by Sergei Korkin. So here is the central equation, which we use in our radiative transfer models. So it looks somehow like this in 3 dimensions. We want to calculate the Stokes vector. You all know the definition of it, I suppose. And in 3 dimensions, it depends not only on the direction, but also on the position in 3-dimensional space, which is here noted by the vector x. Besides the Stokes vector, I will also show the degree of polarization in the following figures. So this list shows the models which participated in the project. We have 4 Monte Carlo models, 3D MC Pool, MC Skat, Mystic, and Sparta. And we have one model which is based on the spherical harmonics discrete ordinate method. So now I come to the first most simple test case, which is a 2-dimensional step cloud. We have 2 domains of different optical thickness 2 and optical thickness 18. In Y dimension, this cloud extends to infinity, and in X direction, this pattern is extended periodically. The cloud properties are calculated by Mie scattering for an effective radius of 10 micrometers. And these are the results that we get. So here, when you look at the gray dashed lines, this is what you get when you use 1-dimensional radiative transfer. And you can see that when you calculate 3D, it's quite a lot different. So this, you should also look at the spatial resolution here, it's 0.5 kilometers. So when you go to spatial resolutions lower than 1 kilometer, it is really becomes important to consider this 3D effects. So yeah, in this area, the 3D result is higher intensity at this step of the cloud, and here you have much lower values. And for Q, the 1D result is almost constant along the whole domain. And for 3D, we have a lot of variability. The gray area here shows the 2 standard deviations of the Mystic model, one here without variance reduction methods and 10⁻⁷ photons, which was the standard setup for the Monte Carlo models. And we can see here in the difference plots that all models agree within the statistical noise of the Monte Carlo method. So then the next test case is cubic cloud. We have here a domain of 7 by 7 kilometers. The surface albedo was set to 0.2, and in the center we have a small cloud cube with a size of 1 by 1 by 1 kilometer square. And the surrounding was, we had 2 cases. The first case is a vacuum surrounding, and another case is a Rayleigh scattering layer with an optical thickness of 0.5. And we did simulations for many different sensor viewing angles and positions. So for the sensor at the ground, we simulated different azimuth directions, and the zenith angle is always fixed to 40 degrees. The sun position is here. Then we had cases for downlooking, so the sensor placed at the top of the atmosphere. Here the position 5 corresponds to the nadir direction. This position 6 is the backscattering direction. This orange circle here corresponds to the cloud bow region. So these points 5 and 7 observe the cloud bow. This blue lines here correspond to a scattering angle of 90 degrees, where we would expect Rayleigh scattering to cause maximum polarization. So I will just show some examples now. So this is the result for case 5, that is the nadir direction. So that means we are in the solar principal plane, and for the upper row here is for the vacuum as surrounding, and in the lower row we have the cloud embedded in a Rayleigh layer. So what we see here first of all is that U and V, they should be 0 in the principal plane. They are 0 when we have a plane parallel model. But when we calculate for 3D radiative transfer, these are not 0 anymore. We get polarization at the cloud boundaries. Also some circular polarization. Yeah, and we see the cloud produces a negative Q. Here in the intensity, we see the cloud has the brightest reflectance, and we can also see the shadow here at the ground of the domain. For Rayleigh scattering, we get this for this result for I and Q. And for U, it is quite interesting how this polarization signal propagates through the whole domain due to the inhomogeneity at the cloud edges. And the circular polarization does not propagate through the domain because Rayleigh scattering does not cause any circular polarization. Here on the right, you see the degree of polarization, which is here in the range up to 20%. Yeah. So then the last setup is for the most realistic setup for a cumulus cloud, calculated by a large eddy simulation model. Here you see the vertically integrated optical thickness, and this plot shows the vertical cross-section through these clouds, and it shows the effective radius. So we have increasing effective radius with cloud altitude. And here you see what we used, which profiles we used for molecular scattering and molecular absorption, and for aerosol absorption and scattering. The surface albedo again was set to 0.2. And yeah, with the two different setups are here now the surrounding only molecular atmosphere, or we have molecules and aerosols in the surrounding. And these are the results that we get for a sensor at the ground. Yeah, we just can point out some features here. So you see that in the degree of polarization that we have the lowest polarization inside the cloud, because there's a lot of multiple scattering in the cloud, and the Rayleigh background has higher polarization. It's quite interesting that the Q and U have opposite signs in clouds and Rayleigh scattering for this viewing geometry. The aerosol scattering is quite, causes quite high polarization for this geometry. And then, time is over?
Yes.
Okay. Okay, then I will not explain this case. That is down-looking case, and then I come to the summary. So we have established a comprehensive set of 3D test cases, and this allowed us to study 3D effects in polarized radiative transfer. And the model intercomparison showed generally a good agreement between all the models, and this allowed us also to establish benchmark results. And these are published on the web page and can be used by other groups who develop such kind of models. yeah, and the results are published in this paper here. And I also wanted to note this paper where we have studies the errors which are induced by the neglect of polarization in three-dimensional cloudy atmospheres. Thank you for your attention.
Right. Thank you for the interesting talk. Unfortunately, there is no time for questions. So if you do have questions on this talk, please write them in the chat. And the next talk is by Alexander Konashunkin on light scattering by large non-spherical particles within the physical optics method.
Hello, everybody. Do you see my screen?
Yes, and we hear you.
Okay, thank you very much. Good day. Today I'll tell you about how to use the physical optics method to solve the light scattering problem by large non-spherical particles. So there are several methods to solve this problem. Usually we use these rigorous methods like DA, for example, but usually they don't apply it for the large particles because of the computational issues. And also we, of course, know about the geometrical optics approximation, but it's not very good for the backscattering. And nowadays we use the physical optics methods to solve the problem, especially in the backscattering direction. So the idea of this physical optics methods, we use this physical optics methods based on the beam splitting technique. So I just briefly explain. So there is a light falling on the crystal. Sometimes some of this light is reflected, some is refracted, going into the crystal and then reflected again, refracted again, and going outside. When it going outside, it goes through the diffraction. So this is the idea. So how it looks, what the advantage of this method, that we can, how to say, differentiate which part of the light, which parts of the scattered light produce from which part of the, how to say, reflected. For example, this is the zero iteration process. So the shadow beams. So we see this scattering light on the whole scattering sphere. And then we add this external reflection. So we see this external reflection here and here. Then we add one internal reflection. So we see it here. And then by then, so we go into the right solution, for example, like this. So this is the DDA solution for the same problem. So it's close to our solution. But the problem is when we starting to average over the spatial orientation. So if the particle is huge, so this is a small particle, for example, 10 microns, and when we rotate these particles, for example, around this axis, so we see that this pattern shifting. So the faster it shifts in the backscattering direction. So if, for example, we change the directions of particle for 1 degree, the pattern shifts for 2 degrees. So here, for example, the small particles, but if the particle is bigger, for example, like this, we see that the pattern becomes more complicated, but the velocity of the pattern shifts is the same. So to appropriately average the solution of the big particles, we have to rotate it very, very smoothly. So it's so the step of this rotation have to be at least twice less than this diffraction pattern, diffraction fringes. For example, like this, if we see this diffraction fringe, for example, this kind of discretization, so if we use more discretization, so we see that this pattern appears. So first, we don't only we not only have to use enough orientation steps, but we also have to discretize this scattering angle very huge number. So our estimation told us that, for example, the physics of this process is that every optical beams going through the diffractions. We can evaluate the size of the diffraction fringes. So the bigger the beam is, the smaller the diffraction fringe is. So the minimal diffraction fringe size is about the maximum diffraction, maximum beam size. So we can use this L max, so it's a maximum age of the crystal of a particle, non-spherical particles, as a reference. So this is the diffraction fringe size. So the orientation angle steps has to be twice less. So for example, for the particle of size of 100, we have to use about 100,000 orientations. So this is the convergence of the solution through the number of orientations, for example, for hexagonal column and particle of a regular shape through this number of orientations. So we see this is our estimation. This is how the process converge. This is about backscattering, but if you are talking about forward scattering, converge faster, just much faster. So the more complicated task is to calculate the backscattering. This is for intensity, and this is how this is about all this phase function. The red line is about our estimation. These different black lines is about less number of orientation. So like this. This is for a regular shape particle. The same is true for polarization elements, but polarization elements converge not so fast. Just you need a little bit more orientation to converge if you have to find out the polarization. But if you are working only with intensity, you can use a little bit less orientations. So this is the convergence of the polarization elements. So we see this negative polarization here, for example, effect. So for example, this is a minimal number of orientations. So if you are talking about size parameter of 1000, you have to use billions of orientations. If you use little, you go to wrong results. So always use enough orientation when you solve the problem for light scattering by non-spherical particle. This is the one problem. If you use enough orientation, for example, like we obtain the solution for hexagonal column. This here is the backscattering and the depolarization ratio. So we see that the solution is very good. It obeyed the geometric optics regime. I think I told. So if you solve the problem for lights for wavelengths without the absorption, so the solution is very good. It's very smooth. It's just close to linear. But if you put the absorption, you see that this solution goes from this to this. So the light's absorbed by particles, and you go to this external reflection regime. So you see that the polarization goes down, and you see that there are oscillations. These oscillations are clearly see for if you are looking for solution for hexagonal plates. This is result of interference. For example, like this, you see that for plate there is a parallel plane. So there is an interference between these outgoing beams, and this interference goes to cause these oscillations. So it's not enough to use large number of orientations for particles. Also, you have to use enough discretization of size to solve this interferential effects, for example, like this. But if you go to regular particles like this, the solution is more easy. You can obtain it more easy because there is no plane parallels planes, so there is no parallel plane effect. So it's just a little bit easy. But for example, here is a solution for up to particle for 1 millimeters. So we use this idea that for hexagonal column, the solution is very smooth, and for the wavelengths without absorption, you can use little amounts of the discretization steps to find the solution. But if you go to different shapes, for example, like plates, you have to use enough discretizations. Here's the comparison of backscattering of our physical optics solutions. We extended to the small particles with the DDA solution, so it goes well. So here is the relay scattering, and here is the geometrical optics regime. So for a very huge particle, they obey the geometrical optics regime, so you have not to have calculated the scattering, you can just multiply it by the size of the particle. But another complicated thing is that you have not only use enough orientation, enough particle sizes, but also you have to use enough particle shapes. If you, for example, use this solution for regular shape, for example, there are 3 different shapes, and we see that the phase functions are completely different. And we average over the 300s different particles and see that the average solution is just smooth. This solution is obtained within the geometrical optics, of course, because the physical optics is very complicated for such a problem. So we see this very good solution with geometrical optics. It can be good. It could be good, but here in the backscattering, if you use the physical optics methods, we see this backscattering enhancement effect. So geometrical optics can take these effects into account. So this is enhancement. The idea of this enhancement is that we can find this trajectories, this kind of trajectories. The idea of these trajectories is that if there is a light going to exact backscattering, for example, like this green one, so always there is a second light that goes in opposite direction. So the same optical beams, the same optical trajectory. So the interferential phenomena just double the intensity. So we see it. So we see it doesn't depend on the shape. So the 3 different shapes is the same amount. It depends on the size, like the interference phenomena. And this is these interferential effects cause this negative polarization effect. So-called negative polarization effect, very interesting. This is a result of such kind of trajectory. But this such kind of trajectory is blue for regular shape. True only for regular shape particle, but if you're going to hexagonal ice column, for example, like this is a geometrical optics solution, this is a physical optics solution. For hexagonal column, there is a very huge backscattering singularity, backscattering peak, and the physical optic just a little bit smooth this peak, but this peak is much higher than this interferential backscattering enhancement. So this is my conclusion. First, if you are solving the problem with for large non-spherical particles, always use enough number of averaging through the orientation. So this is a simple estimation formula. Also, perform averaging of a particle shape. If you are not dealing with the ice crystal, but dealing, for example, with dust particles, so use enough particle shapes. And we calculate the backscattering problem for hexagonal columns, plate, Droxel, bullets, arbitrary shaped convex particles for different wavelengths. For solution up to 100 microns, solution for 1 millimeter in progress. And we found the physical explanation on negative polarization effect. Thank you for your attention.
Thank you for an interesting talk. We have 2 questions. Maxim, is your question?
So I have a question about this huge number of orientations. So if you consider real particles like an atmosphere, so you do some LiDAR measurements or something like that. So would you have enough like averaging in real experiments to sample so much orientations?
I think yes, because otherwise we would observe the oscillation of LiDAR experimental data, but LiDAR experimental data are very stable. So, and you can easily estimate the number of particles that are illuminated by the laser beam, and it's a huge amount. It's maybe not billions, but very close to this.
Okay, thank you.
Other questions? Maybe you could ask them in the chat so we can move to the next talk.
Okay.
It's the time. The next talk is given by Nancy Okeurova on edge effect correction to the physical geometric optics method using the DIVA series for superspheroid non-spherical particles.
Hello, can you see my screen?
Yes, and we hear you very well.
And we can hear, okay, good. All right, I would like to present my research on the edge effect correction to the physical geometric optics method, or PGOM, using a combination of the Debye series for superspheroids to correct the errors for extinction and absorption efficiency of PGOM. Okay, what is the edge effect? The edge effect consists of two parts. We have the above edge effect, which is related to pure tunneling. So we have incident radiation or incident ray, and then some of that radiation from this ray can sneak into the surface of the particle, which contributes to the scattering and absorption by the particle. But PGM doesn't catch this. And we also have another effect called the below edge effect, which is related to anomalous reflection. And that is related to the interference between forward reflection and diffraction. Now, the first question we need to consider is, why do we need to consider the edge effect? We need to calculate the extinction and absorption efficiencies very accurately for remote sensing, rate to transfer, and climate studies. But the problem with PGOM is it doesn't consider the edge effect in calculating the extinction and absorption efficiency. And if you want any chance of improving PGOM, we must add this effect. So we could decrease the size parameter range which PGOM and ITM overlap. We want to use ITM as little as possible and PGOM as much as possible, because ITM is a much slower computational method than PGOM. But first, we have to figure out how to quantify the edge effect efficiency. The way to do that is to analyze the zero-order Debye series at the forward scattering direction. And we're going to break down the extinction efficiency into two parts. The extinction efficiency contribution due to geometric optics, and then adding in the edge effect corrections. Now, for absorption efficiency, it's slightly different. We have to consider the above and the below edge effects separately, because we have to consider what happens around the surface of the particle and what's happening inside the particle. So to break down the contributions for absorption efficiency, we have the geometric optics contribution, then we have the above edge and the below edge effects. But the above edge is the big contributor. The below edge contributes very little. But the major point I want to talk about today is how the edge effect is related to the two-dimensional particle projection. So let's say we have a spheroid. The two-dimensional projection for a spheroid is just an ellipse. And there's nothing you could do with that, because if we want to quantify the edge effect for a hexagonal column, we need a rectangle-like shape. So this is why we want to use superspheroids, because you have a lot of two-dimensional projections to choose from. So the equation for the superspheroid is similar to spheroids, except we have a new parameter called the roundness parameter. We have two different roundness parameters, one in the azimuth direction and one in the zenith direction. But in our case, I want to fix E to be 1 and N to be a positive number, so we can only have axisymmetric particles to work with. The physical meaning behind the edge effect form for spheroids is this new term called the penumbra region, which is the boundary between the illuminated and the shadow region of the particle. Now, the penumbra region is quantified by the projection operator, and Bignon and Fournier and Evans' work calculates the edge effect efficiency for spheroids. And here's the equations and for the extinction efficiency edge correction for spheroids with oriented and randomly oriented spheroids. Now, for absorption efficiency for spheroids, I looked at Dr. B's paper and I noticed something interesting. This new term called the edge strip is where all the edge effects happen. So you have this little wedge, which is the edge strip, and that's where all the above and the below edge effect happens. And if you want to quantify the edge efficiency for spheroids, we have to look for the radius needed. So the edge strip area for the spheroid and the sphere are equal. And then here is the edge effect formula for spheroids. I just used a combination of Biennale's work and Bignon 2014's work. Then this is the most important slide of the whole presentation. How do we quantify the edge effect formula for superspheroids? The idea is, let's say we have a super ellipse, which is a two-dimensional projection of the superspheroid with some area and with these axes. And we have an ellipse with an area, with some area. The idea is we want to adjust this number and this number, these axes for the ellipse, so that the area of both of these shapes are the same. And this is how I did it here. And you also want the aspect ratio not to change at all either. And the most important thing is modifying the projection operator to account for the roundness parameter. This is just like what I did for this, what previous work done for the sphere, except we had this roundness parameter. The first experiment I did was we looked at the edge efficiency and we want to see how the edge efficiency changed with roundness parameter. And as the roundness parameter increases, the edge efficiency increases, partly because the projected area of the particle decreases as the roundness parameter increases. The next thing to consider is we need to understand the tolerance factor in order to quantify the edge efficiency for non-spherical particles. It's just a relationship between the edge effect efficiency for superspheroids and non-spherical particles. We have a sphere, it's a smooth shape, lots of surface weight interactions, but adding roughness to this shape will decrease surface weight interactions, and that will also affect the edge effect efficiency. Now, the tunneling factor formulas for extinction and absorption efficiency were inspired by Liu et al. 2011 paper. He just calculated the tunneling factor to be the shape index, which is the ratio between the actual volume of the particle and the volume based on the projected area. But I noticed something different than what he did. I noticed from some data that for extinction, that the tunneling efficiency is sensitive to the size parameter. So I had to add in that correction. And this number is very small. For absorption, I noticed that the sensitivity, that the tunneling efficiency for absorption is very sensitive to the mostly sensitive refractive index and the geometry of the particle. So combining all this together, we have the new formula for the edge efficiency for the non-spherical particles relating the superspheroid to the actual particle with the time factor. Then the next experiment I did was I took a hexagonal column. I wanted to use a shape that mimics a cylinder. We have to use a roundness parameter 0.01. For hydroxys, we use a roundness parameter of 1, so we have a sphere. I compared my empirical formula with Dr. B's data on the Debye series. So the black is B and Young 2016 paper, and they calculated the Debye series with the invariant embedding technique with the R matrix. Then my formula is in blue. You can see that there are some errors in the lower size parameter. That's not what I care about. What I care about is what's happening here, because that might help me improve PGOM. Because I'm only interested in the moderate size parameters because I can use ITM here, but I would like to use PGOM here. Same thing with the hexagonal column. The next experiment I did was I looked at two shapes that kind of mimic dust particles, the square bipyramid and the triangular bipyramid. And I used the same superspheroid for both of them because their illumination and shadow boundaries are pretty similar. And here are the results. So I looked at the square bipyramid and the triangle bipyramid. The aspect ratio is 1, and the refractive index is typical of a dust particle. And I calculated the absorption efficiencies using PGOM, which is in black, PGOM plus the edge effect, which is in blue, and ITM, which is in red. And you notice that adding the edge effect corrections to PGOM improves the accuracy of the absorption efficiency. However, I had to cut it off at the size parameter 50 because just because you add an edge effect doesn't mean you improve PGOM if the size parameter radius is too low. Then in conclusion, this has a possibility of improving PGOM if we use it in the right size parameter ranges. And it might help decrease the size parameter range where PGOM and ITM overlaps. But I'm also interested in applying this edge effect correction for more complicated shapes like the 8-column aggregate. And last but not least, I would like to thank Dr. Dean and Dr. B for inspiration, and the late Dr. Liu. Thank you very much.
Thank you for an interesting talk. Do we have questions? Right, I guess there's no questions. Maybe the next speaker could already start sharing the screen. The next speaker is Zhang, and his talk will be on air theory revisited with VCRM and physical optics.
Hello.
All right, we can see your screen. Can you put it in the full position? All right, looks good. We can hear you well.
Hello, everyone. My name is Ce Zhang. It's honored to be here to make an presentation. For light scattering by spherical particles, Airy theory has been used for many years, but for Airy theory, there are still some unsolved problems. So today, the title of my presentation are given as Airy theory revisited with VCRM and physical optics. Okay, this is the outline of my presentation. At first, I will introduce the acoustics problem in geometry optics. Then, because the acoustics problem, we turn to Airy theory. Then after there are some problems in area theory, so we proposed our hybrid method combine VCRM and physical optics. At last, I will show you the following research. Okay, from this picture, we can see that the rays in a sphere. According to geometry optics, we can explain where the rainbow is. Because the dispersion of refractive index, we can explain why it's colorful. But according to geometry optics, its intensity or its amplitude at its rainbow angle went to infinity. This is not reasonable in nature. So after that, a scientist, Airy, proposed his Airy theory from diffraction theory. So today, I want to show you it is still worthwhile for us to re-examine the Airy theory. Okay, these slides show the basic diffraction theory of Airy theory. Okay, I will share you how it works. Okay, this is a sphere particle. The rays get into, then reflection outside, then emergent. At this region, the rainbow angle located near this region. In order to explain it by diffraction theory, Airy needed to know its amplitude and phase near this region. So at this time, the Taylor series is used for its scattering angle. At rainbow angle, we have these two formulas, and we define a line. This line V line and the line U line. The line of U is rainbow direction. The two lines is perpendicular with each other. According to mathematics, we can calculate its phase near this line is a cubic function. Here h is a constant. And in Airy's theory, he assumed the amplitude on this virtual line is a constant. Then after has its phase cubic and the constant amplitude, according Huygens linear frame principle, its scattering field can be calculated. This is basic principle, okay? After that, some scientists or scholars research Airy theory. In this paper, he pointed that the amplitude of scattering field is linear to this. Then in Nielsen-Zweig's paper, he pointed that this amplitude should be written in this film. In this paper, he compares the Airy theory and Debye theory. Okay, this is scattering diagram. Near the rainbow angle, the Debye theory and the Airy theory matched well, but as the scattering angle far from the rainbow angle, there are errors. This is order 2, and this is order 3. For higher orders, there are more errors. In this paper, he compared the Airy theory with me theory. He said he must normalize one theory to compare with others. Me theory is correct, has been proved by many people. So it means Airy theory is not right today, even in this day. More importantly, for perpendicular polarization, Airy theory is totally wrong. In Nielsen-Zweig's paper, he pointed that it's totally wrong. This is minimized value by Nielsen-Zweig's theory. However, Airy theory is max value. It's totally reversed. So today we will ask ourselves why Airy theory. Airy is a great scientist. Why his theory suffers so much is whether maybe it's ray model or diffraction procedure. So after thinking a lot, we give our two answers. One is its cubic function is obtained near when v equals 0 only in a tiny small region, okay, in this line, and its constant, its amplitude, its amplitude is a constant and its integration went to infinity. It means it's very long. It's not possible, okay? This is integration. So we will ask ourselves, will there be good method? So we propose our method. We will combine the VCRM and physical optics. We use VCRM to calculate its phase and amplitude numerously on this line. Then, according to physical optics, we can calculate its scattering field. This is our process, okay? Okay, these slides show the basic process of VCRM to calculate the phase and amplitude. This is basic process. Because the complex of VCRM, I don't want to describe it very detailedly. If you want to know about it, you can refer to this paper. Here, I want to say the phase and its amplitude is calculated by numerously, and there is no any hypothesis. And this method, because the flexibility of VCRM and physical optics, our hybrid method can be used to non-spherical particles easily. Okay, these slides show the phase and amplitude on the vertical line we calculated. Okay, in this, the parameters of wave and particle is given here. The black line is the phase calculated by VCRM. The red line is Airy's phase. It's sure when V equals 0, they are matched well, but as V increase, there are errors. It's phase, okay? Its amplitude, the black line is the phase calculated by VCRM. The red line is Airy's amplitude. Yes, it's got a good approximation. It's mapped well for perpendicular polarization. Okay, the phase in parallel polarization, the black line is the phase calculated by VCRM. It's no longer a cubic function anymore. There is a phase shift of half-wave loss. This phase shift has been referred in Van der Horst book, but we first calculated. Okay, this is its amplitude. Its phase at this point close to 0. So, and here it's went to very large. So the Airy's assumption not very well. Okay, these two pictures shows why Airy theory fails in parallel polarization. Okay, after have the phase and the amplitude on vertical line, we can calculate its scattering field. We compare 4 methods. The black line is the best theory. The red line is Airy theory. The blue line is geometry optics. The green line is our hybrid method. According to simulation results, no matter perpendicular polarization or parallel polarization, our method matched very well. Okay. As we have mentioned before, our hybrid method can be used to non-spherical particles. These pictures is the result calculated by VCRM and experiment result. Yes, it looked very well, but if we look detailedly, okay, this picture is its result in 2-dimensional. Okay, it still exists caustics problem. The red line is experiment result. The black line is experiment result. The red line is VCRM in 2-dimensional. The green line is VCRM in 3-dimensional. This line is our, okay. The blue line is our hybrid method, okay. It works, it fixes the caustics problem eventually. Okay, in the following, we plan to extend our hybrid method from 2D to from 2D to 3D, its integration might be a problem. Okay, thanks for your attention.
All right, thank you. All right, do you have questions on the talk?
I have a question.
Okay.
Okay, can you go back to slide 11, please?
Okay, thank you for your question. 11.
Well, you haven't heard it yet.
11.
Slide 11. Where's slide 11? Is this 11? No.
Okay.
No, the one with the integral in it was an integral. I thought it was 11. No, it's further down. It has an integral. You had an infinite integral.
Okay, I know. Okay, this.
You had an from minus infinity to yeah, that one. Okay.
Yeah.
Isn't that is okay? I see. There's an I in here. I didn't see the I, so it's not a divergent integral. I'm sorry. So question canceled.
This is relevant with Aries function.
Right.
Yes.
No, I see the I in there. I didn't see the I before because I thought it looked like it was a divergent integral to me.
Okay. Okay.
So it's okay.
Okay, thanks.
Thank you.
Are there any other questions?
Yes, could you comment again on your plans on the spheroidal case, the last example you talked about?
Yes. Is this?
Yeah, in that case, could you expand again what you're doing in that case?
Okay, thanks for your question. In fact, the blue line is the result we calculated at its equatorial plane. Okay, but we will calculate its scattering in 3-dimensional. This is theta. Okay. There is another direction, phi. Okay. We will get yes, this like this. Yes. This result is only on this line. Same, yeah. We will use our hybrid method to compute its scattering field like this. This is our plan, and its caustics will be solved.
Perhaps I can explain.
Okay, so thank you.
This figure. Have you?
You need to modify things in the region of the caustic, so it becomes interesting when you combine the two. When you combine the area caustic and caustic together, it becomes a very interesting problem.
Okay. I have method. We can use VCM to locate where the caustics locate. Yes, we have method.
Thank you.
All right, let's move on to the last talk of the session, given by Lindsay Walter on near-field radiative heat transfer between particles modeled by the discrete system Green's function method.
Okay.
Thank you, Anne, and I will start sharing my screen. Can you see it?
Yes.
Great.
See, and we hear you.
Okay, so good morning, good afternoon, good evening. My name is Lindsay Walter, and I am a PhD student in the Department of Mechanical Engineering at the University of Utah. And today I will be discussing our research on near-field radiative heat transfer between particles which we model by the discrete system Green's function method. So we'll start off with a little background on near-field thermal radiation. Shown here is a body at temperature T, which is greater than 300 Kelvin, and this body will emit thermal radiation. Shown here are propagating modes into the far field. And if we zoom in on the surface of this body, we will see that there are also exponentially decaying evanescent modes near the surface. And at the room temperature around 300 Kelvin, the length scale of these evanescent modes is about 10 microns. And so these modes do not contribute to far field radiative transport, but if we bring another body within reach of these evanescent modes, we can open up additional pathways for radiative transfer. So the formalism used to describe, The formalism used to describe this regime is fluctuational electrodynamics. And within fluctuational electrodynamics, we begin with Maxwell's equations. We'll focus here on non-magnetic systems with no charge. And then to Maxwell's equations, we append a stochastic thermal source current J to describe thermal effects. We define this stochastic thermal source through its autocorrelation function and then relate it to temperature via the fluctuation dissipation theorem. I'll now talk a little bit about prior work within the field of near-field radiative heat transfer with special interest in orienting our current work within the field as it relates to current limitations and knowledge gaps. So back in 2014, our group developed the thermal discrete dipole approximation for modeling arbitrary geometries and arbitrary materials within near field transfer. And this is a volume integral approach similar to the DDA of light scattering, except with the addition of thermal effects. And so while this method was successful in modeling near field radiative heat transfer, it also had a limitation. The main limitation was that it formulated the system into a stochastic and a nonlinear system of equations, and which necessitated the inversion of a large interaction matrix A and demanded high computational memory loads. So our first contribution of the day is a reformulation of the thermal discrete dipole approximation into a deterministic and linear form, which may support iterative solvers in the future. And we call our new method the discrete system Green's function method, or DSGF. Shown here is other prior work in near field transfer between three-dimensional geometries. And although there have been models developed for arbitrary geometries, as you can see here, there has been this overwhelming focus on perfect, highly symmetric geometries. So this brings us to our second contribution that we will address today. So we are addressing this knowledge gap of a focus on highly symmetric, perfect geometries. And we today will apply our DSGF model to the study of distorted geometries and the effect of distortion on near-field radiative transfer between particles. So without further ado, I'll now present our discrete system Green's function method. So shown here is a system of thermal objects, which is embedded in a non-emitting, non-absorbing background reference medium. These thermal objects are defined by their temperature and dielectric function. We then discretize our system into a cubic lattice of subvolumes, which we define with constant parameters. From there, we can calculate our discrete system Green's function for every subvolume, and then calculate the heat dissipated at every point in our system. So in order to show the difference between our old formulation, the thermal discrete dipole approximation, and our new formulation, the discrete system Green's function method, we will focus more deeply on the wave equation for the system. So in both methods, we define a wave equation valid with the within the domain of the background reference medium, and another wave equation in the domain of the thermal objects. We then combine these two wave equations into one, which is valid over all real space. And the way in which we combine these two equations into one is the main difference between the old and new formulations. So in our old formulation, the main wave equation contains scattering information on the left-hand side and both scattering information and stochastic thermal information on the right-hand side within this equivalent source current density. In our new formulation, we completely separate out the scattering information from the stochastic thermal information with the definition of a new equivalent source current density, which contains purely thermal information. And while this may seem like a small change, it will have significant ramifications in our final system setup. So from our wave equation, we can define our electric fields via the volume integral equations, which basically is just the convolution of a Green's function with a source current. And so in our old formulation, the TDDA, we have the free space Green's function convoluted with a source current that contains a mixture of both scattering and thermal information. In our new formulation, we define a system Green's function and convolute that with a stochastic thermal source current. So in this way, we can transform our nonlinear stochastic system of equations into a deterministic and linear one. So we can, which have the potential for iterative solver use in the future. And I just wanted to highlight some works that have published similar, self-similar Green's functions equations as shown here, but with different applications. So now we then verified our new method against the analytical solution for 3 silicon dioxide spheres of 500 nanometer radius and variable separation distance. And these spheres were embedded in vacuum. So we plotted the total radiative conductance versus the separation distance of the spheres. The total radiative conductance is in units of nanowatts per Kelvin. So here is the results for the analytical solution. The top curve is the total radiative conductance between the first and second sphere, and the bottom curve is the total radiative conductance between the first and third sphere. We then modeled the same systems with our DSGF method, and the results are shown here. As you can see, there is good agreement between the two solutions, and so we conclude that our method is verified. We then applied our DSGF method to the study of irregularly shaped particles. We modeled these particles and the particle distortion through the Gaussian random sphere formulation. We considered only 2 realizations, one of mildly distorted particles and one of highly distorted particles. And these particles had average radii of about 35 to 50 nanometers, again, modeling silicon dioxide particles. Shown here is the heat dissipation in each of the subvolumes of the 2 systems considered. On the left-hand side, we have the mildly distorted spheres, and on the right-hand side, we have the highly distorted sphere systems. And they're just 2 different perspectives. So the blue color scheme is negative heat dissipation, which represents cooling, and the red color scheme is positive heat dissipation or heating. The main thing to note is that most of the heat transfer occurs within subvolumes of closest separation distance. We then plotted the normalized total conductance. So that just means the total conductance of our distorted sphere systems normalized by that of comparable perfect sphere systems. Again, plotting that for variable separation distance. And these are our results for both the mild distortion particles and high distortion particles. The main trend that we can see is that there's only about like a 10 to 20% decrease in the total conductance for our distorted particle systems. And then to understand more of the underlying physical mechanisms which are driving this change in radiative transfer, we focus on one point of the highly distorted particle systems and expand that point into its spectrum. So right here, we're plotting the spectral conductance versus frequency. The blue curve is for comparable perfect spheres, and the dashed orange curve is for the highly distorted sphere systems. So the main thing to note is that the largest deviation from the perfect sphere behavior occurs within the surface phonon polariton resonance modes. The trends that we see are damping and broadening at these resonances. At other frequencies, such as this material resonance of silicon dioxide, there is negligible change. And so to understand a little bit more of what's happening, we went to the literature and found similar effects in this paper by Bies and Graffet, not for distorted particle systems, but for a nanoparticle above a flat and then a roughened surface. We're plotting, or Bies and Graffet plotted the imaginary part of the P polarized reflection coefficient, which is directly comparable to our spectral radiative conductance. So the solid line shown here is for a particle above a flat surface, and then the dashed line is for a particle above a roughened surface. And again, we see similar trends of damping and broadening. So these authors attributed these effects to roughness-induced scattering from the surface phonon polariton resonances into nearby frequencies. And we believe that similar effects are at play within our distorted particle systems. And then finally, just to summarize our contributions, we addressed the limitation of a nonlinear and stochastic setup within the old formulation of the thermal discrete dipole approximation. And our solution was to reformulate this into a linear and deterministic setup through the definition of a discrete system Green's function. Secondly, we addressed the knowledge gap, which begged the question, what is the effect of geometric distortion on near-field radiative heat transfer between particles? And we began looking into this knowledge gap through a preliminary analysis of distorted particles, only two specific realizations, using our DSGF method. So there's still plenty of work to be done within this knowledge gap. So we haven't done orientation or even ensemble averaging yet. So that's exciting that there's still lots to look at. So thank you for your time, and I'm open to any questions you may have.
Thank you very much. It seems that we have some questions. Alexei, I think you were first.
Yes, thank you for the interesting talk. So am I right to understand that, for example, if I want to increase the heat transfer, I should have a sharp resonance, right? And I can attain one with, for example, periodic corrugation.
That I guess so. Yes. So that would be like a are you talking about like a periodic system?
Right.
Like a flat surface with some.
I mean, if we're talking about some stochastic systems and random geometry, we would also always have some spoiled resonances, like widening and low quality factor. But if I go to purely periodic systems, I may have some sharp resonances, and in this case, am I right to understand that in this case I will always have increased heat transfer?
It seems from our results that the more symmetries that are there, the higher heat transfer that you will have, except just to note that we're looking at polar materials which support these surface phonon polaritons. So not all materials will support these resonances.
Okay.
Does that answer your question?
Yeah, I think, yeah. Thank you.
Mm-hmm.
And we also have a question from Maxime.
Yeah, so, well, I have a question about computational complexity. So what it will be in terms of number of dipoles for your new method?
Right. So in our verification, we used about 4,000 subvolumes for the entire system. So we had convergence at around 2,000 subvolumes per sphere for those perfect sphere verification. And then for our distorted particle systems, we used about 10,000 and 16,000 subvolumes total. So like between 5 and 8 subvolumes per particle.
But I mean, have you estimated how the complexity scales with increasing number of dipoles? So is it like quadratic in number of dipoles or even larger power?
Yes, it's so are you talking about computational memory requirements?
Well, memory and speed both.
Yeah. So the computational memory requirement scale same as the DDA, so 3n squared. And the time it takes, in our new formulation, we're solving a complete matrix equation. So there's 3 matrices there. So the time for computation will increase, but the memory will decrease once iterative solvers are implemented.
Okay, thank you.
We also have a question from Barry.
Lindsay, I love your slides. They are great. They're the color and the information was perfect. My question is, isn't there some relationship here with radiosity? The radiothermal, when you're transferring energy from materials, from objects, you use view factors and you have radiosity. Isn't there something comparable here?
So in the near field regime, we can't use view factors. We have to solve the full set of Maxwell's equations to account for these evanescent modes.
Yeah, yours is much more finer than I think a radiosity calculation would be. But excellent work. Thank you.
Thank you, Barry.
All right, thank you, everybody. This session is now over. The next session will start in 18 minutes.
Alex, should we start?
Yeah, dear colleagues, it seems that we don't have the session chair, so I will start. Okay, the first speaker today is Professor Yang with his talk about Professor Kuan Yu contributions. So please, Professor Yang, you can start.
Okay, so in this presentation, I'm going to briefly summarize Professor Kuan Yu's contributions to light scattering, radiative transfer, and remote sensing. On March 20th this year, we lost one of the greatest atmospheric physicists of the last half century, Professor Kuan Yu. He was a distinguished professor in the Department of Atmospheric and Oceanic Sciences and the University of California, Los Angeles, where he also served as the department chair for 4 years. He was the founding director of a Joint Institute for Regional Earth System and Science Engineering at UCLA. Before joining UCLA, Dr. Liao was a professor at the University of Utah for 22 years. He received a bachelor degree at National Taiwan University and received a PhD from New York University. You can see he had a fast track through PhD program. Just took about 3 years. His contributions have been recognized by many awards and honors. He was elected a member of the U.S. National Academy of Engineering, member of Academia Sinica, the former member of Chinese Academy of Sciences. He shared the Nobel Peace Prize bestowed on IPCC report, and he received Rossby Research Medal by American Meteorological Society, AMS. This medal is the most prestigious AMS award. He received a Roger Revere Medal from the American Geophysical Union, International Radiation Commission Gold Medal, COSPAR William Nuremberg Medal, and Charlie Medal. And he was elected fellow of AGU, AMS, the Optical Society of America. He was well known for his book, Introduction to Atmospheric Radiation, as praised by Warren Wiscombe, the former chief scientist of DOE ARM program. Dr. Liao was a pioneer researcher who demonstrated that atmospheric radiation should no longer be considered to the fringes of meteorology, but instead should take a central place in the new world of climate science. Academician Kondratev of the Russian Academy of Sciences wrote, Dr. Liao's monograph is unconditionally useful and timely, successfully filling a gap in publications on radiation of the atmosphere. It will quickly find our readership among specialists in atmospheric physics. The first edition was published in 1980, and then second edition 2002. You can see this book has been highly cited, and also this book has been translated into Chinese, Russian, Japanese, Arabic. So he also published a book, Radiation Cloud Physics, the Process in the Atmosphere, Theory, Observation, Modeling. In this book, he integrates the radio transfer and cloud physics in a coherent manner and bridged the gap between cloud radiation and climate process. The text also presents important topics in radiation, cloud physics, thermodynamic equilibrium, and simple climate models. In the area of light scattering research, the work by Neil and James Hansen may be the first start that systematically compares the geometric optics method and the Lorentz method. So they showed in and size parameter of about 100, the two methods converge. And also they show no matter how big the particle size is, in the case of water droplets, geometric optics method cannot simulate the backscattering peak, the glory peak. In the early 1970s, he was the first who pursued the study of cirrus cloud related properties by considering long-spherical ice crystals. So he assumed the ice crystals to be horizontally along cylinders. In the 1980s, he pioneered the study of scattering of polarized light by non-spherical ice crystals by means of principle of geometric optics. There are some works before his work, 2 decades, 3 decades, but these two studies didn't consider polarization. And also for the first time, he exactly considered diffraction by hexagonal ice crystal. And in middle 1990s, we started develop the physical geometric optics method. This work was inspired by Kerry Moinoni's work. He used Kirchhoff approximation to map the near field to far field. So in our work, so we map the near field on the surface or inside the particle to far field. As you can see, this is a comparison between the physical geometric optics solution and the T-metric solution. You can see they are quite consistent. And so this this figure is taken from a review article, invited review article. As you can see, the co-authors included Professor Liao and Dr. Mishanko. Sadly, they are not with us anymore. And so here is extinction, single scattering bezel, and symmetry factor. You can see by combining these two methods, we can cover the entire size parameter range. And we spent, Dr. Liao and I spent about 7 years. We summarized our work in this book, Light Scattering by Ice Crystals, Fundamentals and Applications, which was published by Cambridge University. Dr. Michael Mishanko published a book review. In the review, he said the book by Liao and Yang is a comprehensive account of light scattering by atmospheric ice crystals, and is unique in its combination of breadth and depth of content. It is a must for all graduate students and experts specializing in atmospheric radiation, remote sensing, and climate research. Liao discovered the principle of depolarization of a linear polarized laser beam to differentiate spherical water droplets and non-spherical ice crystals. This work established the basis for cloud phase detection using ground-based airborne and spaceborne lidars. Liao developed a 1D radiation precipitation climate model to investigate the potential links between the perturbed cloud particle size distributions and the precipitation produced by greenhouse warming and air pollution. And his discovered link cloud particle size and precipitation in climate change is now referred to as the second indirect climate forcing in aerosol cloud feedbacks. So this was the first report on the second indirect effect of aerosol cloud interaction on precipitation. In the early 1970s, Liao, for the first time, numerically implemented the discrete ordinates method developed by Chandrasekhar. You can see here is the paper he published in 1973. And also, for the first time, he derived the analytic eigenvalue solution to the delta 4-stream approximation for radiative transfer. He provided a systematically independent development of the solution and a wide range of accuracy checks, include the delta adjustment for this approximation. And also he worked with his former student, Chang Fu, who is now a professor at the University of Washington. So they revealed the mathematical necessary and sufficient conditions for the correct K-distribution method. So they also developed a very known Fresnel radiative transfer model. This model unified the treatments of solar and thermal infrared radiation, including the multiple scattering, which is widely used in the atmospheric science and the climate research community. You can see the impact of this paper. This paper has cited more than 1,000 times. In the last 5 years before his passing, Professor Liao made important contributions to understanding of the impact of 3D radiative transfer in mountain snow surface hydrology. And you can see the illustration of 3D radiative transfer over a mountain region. And they demonstrate the impact on climate simulations. And also they started the snow albedo effect, considered the contamination of soot, dust on snow. So they show that the impact of the soot dust contamination is important. Service to the science community. Liao was actively engaged in service to the scientific community throughout his career. He served on numerous national, international committees. To list just a few, he served as the chair of Section 12, Special Fields and Interdisciplinary Engineering, National Academy of Engineering, chair of the AGU and Atmospheric Sciences Section Fellow Committees, chair of AGU, Roger Revere Medal Committee. Then editors for various journals. One thing I want to emphasize, he was a long-term associate editor for a Journal of Quantitative Spectroscopy and Radiative Transfer. A large portion of Liao's legacy is reflected by the number and the quality of his graduate students he trained. In total, he guided the completion of 32 PhD dissertations, in addition to many master theses. Liao also mentored many early career researchers who worked with him as visiting scholars. With his passion for science and a nonstop pursuit of excellence in 3 key areas of university faculty, namely teaching, research, service, Liao was indeed a role model for his students and visitors. On many occasions, Liao encouraged early career researchers by reciting an ancient Chinese poem. The setting sun means on the first mountains to disappear. The Yellow River flows into the sea to see 1,000 miles further, or send another story. The passing of Dr. Liao is a blow to atmospheric science. A great atmospheric scientist is gone. He was a true expert in many research areas, most significantly in atmospheric radiation. His remarkable scientific insight led to paradigm-shifting contributions to atmospheric sciences, which manifested his great creativity, Dr. Neal's effort in teaching and mentoring students and young scientists exemplify his selflessness and generosity. It is with great sorrow for us to face that Dr. Neal departed from us, but his books and legacy will live on. As tribute to Dr. Neal for his extraordinary accomplishments in scientific research, his dedication to service for the science community, his integrity and generosity and kindness towards others. We borrowed some words from Mrs. Margaret Dirac's speech and the dedication ceremony of the Paul Dirac Science Library. It is customary to praise those who are not with us anymore, often quite undeservedly, but not in this case. No praise will exaggerate or to be too glowing. Thank you.
Thank you very much for your talk. I think we don't have questions for this talk, so since it's a memory talk, so thank you very much, and we will go on. So the next speaker is Kixing Zhang. Could you please share your screen?
Oh, okay. Thanks for the share. Can you hear me?
Yeah.
And I have shared the screen. Oh. Wait a moment. Can you see the full screen?
No, could you make the presentation? Yeah. Presentation mode.
Oh, is it right now?
We can see your right panel, but I think you can present as this.
Okay, so you can see my notes. Okay.
Yeah. Yeah, but you can continue this. So please, the stage is yours.
Okay. Dear colleagues, I'm Qin Zhang from the State Key Laboratory of Fire Science and the University of Science and Technology of China. And it is a great pleasure to give this talk in this conference. Yeah, I can see many big names on the Zoom attendance. The title is more different from the original title in the agenda. Yeah, I want to talk this title. This is a recent work we just published on the JQST. The work was finished by our group. The other authors are Jia Liu and Jie Nuo. They are the two PhD students graduate in our group, and Jia Liu is in the Hebei University, and Jie Nuo is now in the Chinese Academy of Science. As we all know that the soot aerosols is emitted from the combustion. It is to say that it's from the incomplete combustion. It is an interesting particle that in the combustion community, many scientists are trying to find how the soot are formed in the flame. It is still a mystery. Yeah. In the 2008 the science paper I have published, to say that the radical approach to soot formation, it is still a great scientific problem. Yeah. On other aspects, when it emits to atmosphere, the soot and or the black carbon or the iron soot, they're all the same technologies. Yeah. It's one of the most important answer projects short-lived climate forces that contribute to global warming. And the effect, the uncertainty on this effect remains high. Yeah, you can see this picture. The optical property of soot aerosols is important for climate modeling and remote sensing studies. Yeah. However, large uncertainties remains in the optical properties due to the morphological complexity and the variability. Yeah, we can see the pictures. The biomaterials are most fresh soot particles, and the belows are the soot particles in the atmosphere. They get internal mixed with other particles such as sulfate or organic coatings. So many researches are developed, include other groups and the different multi-models to describe the morphology of the soot particles. Yeah. The simplification of soot models depends on the internal use. Yeah. In kite modeling, we care about the absorption cross-section, asymmetry parameters, and a single scattering albedo. And in remote sensing and optical characterization studies, we need more detailed models for retrieval of aerosol properties. The optical parameters we care about are scattering metric elements, the LIDAR depolarization ratio, and the absorption and strong exponent. Yeah. And today we're talking about the scattering matrix. The scattering matrix elements supply more constraints for the verification of models of the aerosols, and they contain all the information that can be retrieved by the elastic light scattering. Yeah. Here's the equations. Yeah. They have 6 independent elements, were usually similar to the these 3 elements. The F1 we call usually are the phase functions, and the F12 we call these the degree of linear polarizations. And F22 can be used to evaluate the total length float. Yeah. Why the F22 is important? Because it's in LIDAR observations, when it's in backscattering in the 180 degrees, yeah, the F22 can be converted to the LDR. Yeah, they have these equations. In this talk, yeah, I want to present the work of the laboratory measurements and modeling of scattering matrices with soot aerosols. This is the work we wanted to do many years ago, but we just finished in the not years. Yeah, why? We know that there are many papers are studying the optical properties of soot aerosols. However, when we try to find a experimental measurement results of scattering matrix of soot aerosols, we can't find few. Yeah, it's very limited for these results, and all the models are compared with other models. Yeah, I think that is a problem. Yeah, why we need a well-designed laboratory experiment for soot aerosol? Because I think we cannot compare the models with the field observation results directly. This is not the case for dust. In dust, you can compare the model results with the dust storm observations. Sometimes, yeah, we compare the results with the wildfire smoke. I think that is the case that we can get the observation of soot aerosols, but it is different scenarios. For example, we can get the models. Yeah, we can get the LDR modeling results, and we just compare to the LDR modeling results for fire smokers. But in fire smokes, it contains brown carbon, soot, and other particles. Soot is less than 10% in most wildfire smokes. That is proved by many, not many, just 1 or 2 papers. And sometimes we do the samples in the wildfire smoke, but we don't publish. But there was 1 or 2 papers have proved that soot is less than 10% in the most verified smoke. Other particles are mostly brown carbon or sometimes fly ash or dust. This is the paper by Yu Pengfei. Yeah, it's published in Science. Yeah, they prove that 5% of BC particles in the plume can elevate the smoke to the high altitude. Yeah, it's just only 5%. Yeah, and this is a paper by China. Yeah, in 2017. Yeah, they found just 2% of soot particles in the verified smokes. So when you get model a fractal model results, yeah, when you compare it with the field observations, the field observations is averaged by the other spherical particles. So we just don't compare it. Yeah. So the aim of this study is to evaluate the ability of the ideal fractal egress model to produce the scattering matrix of soot aerosols under well-controlled laboratory experiments. So we know what we measure. Yeah. So we can model it. Yeah. And the second point is to provide measurement data of scattering matrix elements or soot aerosols for phasor verification. Yeah, I think it's useful for modeling. This is the scattering matrix measurement setup. Yeah, we designed this setup using the polarization modulation and dual harmonic locking detection. This setup is first the principle of this kind of measurement is first established in 1960s by University in Texas, by Dr. Perry. They use this principle to measure the non-spherical particles like salt, sea salt. Yeah. Of course, this is the same principle with the apertures in Amsterdam and Canada. They're also the same principle. Yeah. We do some modification here. It can measure in two wavelengths by alternating the delta lasers. Yeah, it in 532 nanometers. It is the same wavelength for most LiDAR, and it's a more short wavelength for comparison. Yeah, with the help of the rotator table, the scanning angles from 5.2 degree to 175 degrees are covered by the reliability of the measured scattering matrix depends on whether the experiments satisfy single scattering conditions, because it is important for modeling. Yes, for modeling, we just to when we modeling a bulk of the particles, we just use the integrals. So we want to the measurements satisfy the single scattering conditions. We use a simple Beer law to check it. Yeah, when the extinction coefficient is less than 1, the 0.1, we can make sure that this scattering is in the scattering in the stream are single scattering. Yeah. Before measurement for samples, we do calibration test with the water droplets, because the water droplets is a spherical particles, and we know the refractive index. Yeah. The below is the measurement results and the modeling results. Of course, we model it with the mean theory. Yeah, it matches perfectly. Very best fit is the geometry radius and the geometry deviation from the minimization of the measurement results and the calculation results. So through this, we can retrieve refractive index and size distribution parameters simultaneously. I think it is powerful for the particle characterization. We can develop it for an instrument. Yeah. So we can see that the lines are the modeling results with mean-theory. The dots are the measurement results. Yeah. As you can see in the last slide, it just matches perfectly. And what we want to do is that we find a model of the non-spherical particles we can to match all the 6 elements of the matrix. Yeah, that's our goal. But I think it is a tough task now. In our study, the soot particles we collected and re-isolated. We use 2 kinds of liquid fuel commonly used in fire science and energy science, the toluene and the unheptane. Yeah. It's not just directly measured in the plume. Yeah. We first the profile are combusted in the chamber, and the soot particles are deposited to the chamber wall. And the samples we collected use a brush from the chamber wall. So, and in the last step, we re-isolated by commercial particle disperse. We use the RG 1000 type as a commercial disperser manufactured by Panis. So after the re-isolation, we use a fast particle analyzer to measure the electron mobility diameters. The measurement range is from 5 nanometers to 1000 nanometers. Yeah, we can see that the toluene soot has bigger diameters than the unheptane soot, but almost the same, and then show the same log normal distribution. Yeah. Why we use the DMS to get a electrical mobility diameters? We think this instrument can get more particles. It is more representative than the SEM images. We will explain it later. Yeah. So the DMS can just get the mobility diameters. When we want to calculate the net scatterings. We want to know the volume equivalent diameters. So we want to the conversion from the mobility diameter to the volume equivalent diameters. Yeah. With such literatures, we find the dynamic shape factors for most of the suits. Yeah. So we summarize it and get a line of this with change of the diameters. So we get the dynamic shape factors. Of course, we still get the need to know the value of ratios. Yeah. These ratios are almost in the range of 0.6 to 1.2. Yeah. So we just select 4 constant parameters. Yeah. So use these equations, so we can just get different conversion factors C on the different electronegative mobility diameters. Yeah. So finally, yeah, we want to get a graph that's a relationship between the mobility diameters and the volume equivalent diameters. Yeah. Here we use the constant value of C. We just for 1.6 to 3.23. Yeah. We just use these constant values, and also we use the variations, the 4 variables, and from version 1 to version 4. The variation is that this is varied with the electromobility diameters. Yeah, but the C value is constant, is just a line. Yeah, that's different. Yeah. So overall, so we can get the volume equivalent diameters from the mobility diameters. Yeah, and this is contains all the particles in the scattering streams. Yeah, in the streams of the aerosols. So now we get the size distributions, and another important one is that we want to reconstruct the morphological parameters of the fractal-like particles. Yeah, so we developed a pipeline of the most morphological characterization and fractal acceleration from the SEM-TM images. Yeah, we'll go faster. Yeah. This is the morphological characterization from the TM images. Yeah, we get the monomer size distribution of the two kinds of aerosols. They have a slight difference, yeah, but almost they are fitted by the log normal distributions. Yeah. And so we use two kinds of settings. One is for the model dispersed or the monomers, and one is for the poly dispersed. We want to comprise of the two kinds of monomers. And from the TM image processing, we want to get the determination of the parameter, two important parameters, the fractal dimension and the prior factor. So we use these equations. We get the n, and we get other parameters. So the slope is the fractal dimensions, and the bias is just the prefix k. So we get just more than 1,000 particles to get these graphs. So we get the statistics of the fractal parameters. This is the typical values. Yeah. Why we have the range? Because we have many images. Yeah. So we can get several images. So that we can it's in a range. Yeah. So, and this is why we don't use the n to get the size distributions, because this is not so representative. Yeah. So we use the DMS particles to make the size distributions, and we use the TM images for morphological characterization. I think this is more reasonable. Yeah. Faster. Yeah. So this is the measurement results for the two samples. We can see that two samples have similar angular distributions. Yeah. In the same wavelengths, they have not so much difference. Yeah. And this is the samples in the two different wavelengths. We can see that the phase function is different, and in the degree of linear polarization, they're also the same shape. That is the common shape for this kind of particles. Yeah, the small particles. And the F22 is just the long is just to can serve as the long field. Yeah. We can see that in the backscattering, from side scattering backscattering, it just deviates from the one. It's just for the value of 0.8. Yeah, it's just a quite value, different value from the calculation we can see later. Yeah. Yeah, besides soot, yeah, these years we have measured other particles, yeah, for especially for dust or smoldering particles. Yeah, we can see that they have different patterns. We can use this to distinguish from the different type of particles. We'll go because the time is limited. We can not say much about this. Yeah.
2 minutes.
Okay. The second, we can see the modeling. Yeah, no, we know the size distribution parameters, and we know the morphological size distribution. So we can model the results. Yeah, we can just see the model results. That's The first is the size distribution, the influence of size distribution. We can see that using these settings, we can get the best results of the phase function. But all the size distributions cannot fit all the other elements. Yeah. These settings can mean that it contains more large particles in the aerosol streams. And the influence of the fractal parameter and the prefactors is that the fractal dimension has little influence on simulation results. Yeah, they just better performance in reproducing the F11. They all failed to reproduce the other elements. Yeah, and the influence of refractive index. Yeah, is the same result that of course they can fit the phase function, but also failed to fit other parameters. Yeah. But we know that we keep the range of the value of the refractive index. Yeah, it from 1.5 to 2. And at last, we compare the results of the monomer polar dispersity. Yeah, we can see that the monomer polar dispersity have no influence on the reproduction of the elements. Yeah, so we can see in other papers published in the JKSRT. Yeah, they also do this almost the similar works, but they just measure the exact backscattering LDR measurements. They get the same values. Yeah, for 1.5, 0.84. Yeah. And for R values, well, the same wavelengths, we get the values just, we can see that it's just 0.8. The same values. They are different from the calculation results. And they also do the calculation, they use the same models of in our papers. Yeah, but they just do for the single particles, they didn't account for the size distributions. Yeah, so you can see that, yeah, when the calculation results can agree with the measurement results. Yeah, it's just for the 0.84. Yeah, they can just get this effects, but this is not reasonable. It is not a reasonable reflecting pursuit. So they think this strongly suggests that the morphological models used in the study are in need of physical refinement in order to better implement the laboratory measurement experiment measurements. Yeah, even for the best particles, the fractal algorithms is failed to reproduce the LDR. Okay, let's get the conclude that. Yeah, the first thing is what I want to emphasize that the compare between the pseudo modeling and biodiversity modelization results not suggest. So the laboratory measurement of pseudo aerosols are important. Yeah, and this second point is that we finished the complete Laxton metrics for pseudo particles. Yeah, and the third point is that it is obvious that the ideal fractal aggregates formed by multispheres or polysphere monomers in point contact cannot simultaneously reproduce all the angular behavior of all measured elements, and which need morphological complexity models to reproduce this results. Yeah, and even for bare pseudo particles, yeah, if we want to reproduce the particles intermixed with other particles, it's more complicated. Yeah, so that's why we want to talk. Yeah. So thank you.
Okay, thank you for your talk. Let's take a short question from Jacek, please.
Thank you very much for this on this very interesting subject. When I looked quickly at your values, you have very large values for the prefactor in excess of 2 and sometimes even 3, and relatively low values for the DF factor. Now the latter, the DF around 2 tells me that they are fresh particles, and that is of course consistent with your experiment. But in real life, what you have is that soot will age and it will have condensation on it and the shape changes then. So to summarize my question, do you think that aging of soot will reduce your prefactor values? Can you comment on that, on why you have such large values?
Okay, I think what we measure is not aged particles. It is just fresh particles deposited to the chamber wall. So it's not the aged particles. And why the prefactor is so large? I think it's just to depends on the processing, the processing way. Yeah, you know that we have some parameters we need to get from the experience values. These values are influence the K values. I think that's the. And we also do other calculations, and you can search the literature that different K prefactors are also shown in the literatures. Yeah, I think that's maybe we can talk later. Yeah, I think those that's not. It cannot say that this is aged particles. This is just to conclude that this is the fresh particles, but with large K, prefix K.
Thank you.
Okay, thank you very much once again. So could you please stop sharing your screen? And our next speaker is Zhen Wang.
Okay, I'm here.
Yes, you can start sharing your screen, please.
Okay. Can you see my screen?
Yes, that's great.
Okay, thank you.
The stage is yours, please.
My name is Zhen Wang. Can I start? Yeah.
Yes.
My name is Zhen Wang. I'm from the Nanjing University of Information Science and Technology. And so the presentation title here is the impacts of the laser beam divergence on the light multiple scattering polarization return from the water clouds. As we all know, the multiple scattering in the water cloud can depolarize the light signal partially, and it can also create interesting multifold polarization patterns. But multiple scattering distribution is highly dependent on the light transceiver configuration, such as the photon wheel, receiver photon wheel, and the laser beam, and etc. But we found the laser beam divergence effects are rarely studied. So this is our study. But we found when the divergence is comparable to the receiver photon wheel, the laser divergence can selectively redistribute the multiple scattering, so it might change the polarization patterns and the light polarization signals. To conduct this study, we use our 3D Monte Carlo radiative transfer model Muscat. This is a useful tool for the passive and active polarization observation simulation. If you are interested in our model feature, model algorithm, model performance, you can read our 2017 and 2019 papers, and also can see our website. So we do not want to talk too much about it. We only give some necessary about the light polarized radiative transfer the simulation. The Monte Carlo simulation is decomposed into the three parts. The first part is the light emission from the light transmitters, and the second part is the light tracing in the water cloud, and the third part is light recording to the light receiver. We only to consider the later beam divergence. So we have introduced the Gaussian laser beam, and its probability density function is given here. We use this function to sample the emitting directions and setting the polarization states using the following questions. These following equations. This can maintain the each directions can have the same polarization states. We have simulated two kinds of the LiDAR signal. The first one is the range resolved Stokes vectors, and the second one is the CCD measurements. We will talk later. This is a range resolved Stokes of the total integrated signal over the whole receive photon wheel, just like the caliposol LiDAR measurements. We have used a very simple water cloud. It is a one-dimensional uniform water cloud, which put at the distance of the 1 kilometers from the black surface with the water cloud geometrical thickness depth is the 300 meters, and the optical thickness is the 4. Effect radius is the 8 micron. And here the LiDAR is the vertical pointing to the water cloud, and we have considered the coaxial LiDAR observation systems. The LiDAR divergence and the received photon wheel are listed in these tables. And you can see that here, the G is denote the ground space LiDAR, and the S is denote the space-bound LiDARs. And you can see the ground space LiDARs have the big photon wheels than the space LiDARs. This is because we want to have this. We want to have the same size of the photon wheel, footprint, lighter footprint on the water cloud. So we have the similar kind of the multiple scattering. And here we consider the laser divergence is less than the less than the 1 miniradians. And first, let's look at the results for the zero laser divergence. As you can see, the first row is the ground space LiDAR results, and second row is space-bound LiDAR results. The first column is the LiDAR return, and the second column is the multiple secondary fractions, and the third and the fourth columns denote the linear and the circular polarization degrees. As you can see, as we increase FOV, the LiDAR return and the multi-secondary fraction increase, but the polarization decrease. This can be easily explained because the more multiple secondary, the more stronger the depolarization would be. And this is show the reasonable of our model, our simulation results. And now we will look at the laser beam divergence effects. To estimate this effect, we have calculated the difference of the polarization degrees relative to the zero divergence case. And we found the ground space LiDAR. For the ground space LiDARs, the difference is very small, and it can be safely ignored. So we will not talk about again. This is also can be easy to understand because the ground space LiDAR is very close to the water cloud. So they have very small laser spots on the water cloud. So they do not have the significant multiple secondary effects. And this is not the case for the space-bound LiDARs. LiDARs such as for this small photon wheel case, the difference can exceed 0.2, but this difference can decrease as the photon wheel increase. And the most interesting things as we found is that the laser divergence can slow down and can speed up the depolarize, can slow down and speed up the depolarize according to the divergence value. As you can see, this difference is the positive. The positive is this means the laser divergence can slow down the depolarize when the divergence is less than the photon wave. But when the divergence is greater than the photon wave, the different things happens. We can find that this difference becomes negative. This becomes a negative. This means it's a speed up. This can speed up the depolarization. They can speed up the depolarization significantly. And we can also find the weakest depolarize at the divergence equal to the photon wave. This can be explained by the multiple scattering. As we can see, the multiple scattering refraction for the larger divergence is a large 2. So this is due to the multiple scattering, and for other cases also the same. You can see this green current is also can be seen, and the similar result can be obtained from the other case. We will look at the second kind of the light simulation. This is the FOV, photon wave resolved signals. This is FOV resource signals of the total integrated signals over the whole range of the cloud depths. This is just like the CCD measurements. And we have used the same water clouds as before. The only difference is we divided the photon wave into the two-dimensional beams in the azimuth angle and the polar angles. And the ground space light have very small divergence. We only consider the space-bound light results. The first 4 corners is for the linear polarized light, and the second 4 columns is for the circular polarizing light results. As you can see, the light return, the energy is spread from the center to the larger polar angles when we increase the divergence. And you can also see the multifold structure and the vortex structure in the zero divergence. As the divergence increase, this structures is dimming, and from the center to the larger polar angle as we increase the divergence. And you can also see the polarization preserving structure, and this can also see in the VC. This can be explained by the volumetrics. For rotational symmetry,
2 minutes.
We can find that the volumetric is reduced to the azimuth independent. Azimuth dependent and have the following structures, and we found this, and we can get the Stokes mathematical expressions, and we can find that this Stokes is the function of the volumetrics. Is the function of the volumetric elements, and we can find the ratio dimming is due to the elements with the cosine and sine term, and the polarization prism is azimuth independent. So this is caused by the term without the cosine and sine terms, and the cosine and sine terms is these 3 terms. we can find these written results is approach to the zero for the larger divergence, and this one is different. They became a large positive value, and this becomes a larger negative values. We can find this ratio dimming is due to the multiple secondary, and this is due to the single secondary, because we found these three elements does not change when we excluding the single secondary contribution, but this one is changed greatly, and they are close together. What does this mean? This means the CCD measurements cannot provide more information than the MFOV light provide, because the MFOV polarized light can only provide these two elements. They cannot provide these three elements, but these three elements became to the zero for the large divergence. But only these two terms have non-zero values, and we even can conclude that we cannot provide more information than the single photo wheel LiDAR, because this curve it become flat for the larger divergence. This means they do not show the dependence of the polar angles. So I think I do not have enough time to talk about the change in the Muller matrix, but this can be explained by our newly proposed double planar small angle scattering approximations. If you are interested, could read our 2020 papers. And for the divergent case, this work is still ongoing. So I will conclude my result. Give some conclusion here this is some conclusion, important conclusion given here, and this is our published paper. And this work is published in the 2021 paper. And thanks for your attention. Thank you.
Thank you very much for your talk. Dear colleagues, are there any questions? Well, I don't see any raised hands, so you can still write your questions in the chat, and we are going to move further. So, Jean, could you please stop sharing your screen?
Stop. I cannot find.
Yeah,
okay,
great. So the next speaker is Jarmo Moilanen. Are you here?
Yes, I am here.
Yes, so you can start demonstrating your presentation.
Okay.
Great, the stage is yours, please.
Wait a minute. Do you see my presentation?
Yes.
Okay. So I am Jarmo Moilanen, and I'm in Finnish Geospatial Research Institute. And I'm talking about the ice crystal halos, which is most common natural light phenomena in the sky. It's more common than rainbows or auroras. So you can see them about 150 to 200 times in a year. And they are formed by light refracted and reflected in airborne ice crystals. These crystals are usually hexagonal, as most of the ice crystals in atmospheres are. And the light can refract or reflect from the ice crystals, causing different kind of ray paths which produce colored or white rings, arcs, and spots on the sky. The light source is usually sun, but this can be seen also around the moon and also like around the street lamps if there is ice crystals on the ground level, like here in north in winter times, or in sometimes in mountain region in lower latitudes. Usually the halos which are colored are refracted, of course, and white halos are usually result of reflections. The halos can be seen in ice crystal clouds, which are in high clouds, or in ground level diamond dust, or as called also in ice fog. But diamond dust is the ice fog which has much more higher transparency than the ice fog. Halos has been there all the time, and there is some petroglyphs from prehistoric times where you can think that there is a halo drawn in these petroglyphs. But first mention of halos is over 4,000 years old from Sumerian, Babylonian cuneiform tables. There is mention of the two most common circular halos, 22-degree halo and 46-degree halos. The oldest known halo observation in literature is dated in 1233. This was in Hereford in United Kingdom. Some of scientists, well-known scientists like Descartes, Huygens, and Mariotte has been study halos already in 17th century. Mariotte was the first who got the origin of halos right, and he was the one who noticed that they are produced by ice crystals. Halos were later researched by names like Wegener and Tricker, and in early 1900 there was some studies where halos was studied because they were thought that halos can be used for weather forecast. But after that proved to be not so fruitful, then the halo science got some kind of sleepy mode until in late 1980s, first Monte Carlo based halo simulations was programmed, and Butler and Rankley made several findings using their Monte Carlo simulations and explained some halos which wasn't explained by that time. Although this halo research is old business, there has still lots of new halos found in this century also. In some of them have been found in just recently. And now we know over 100 halo species or forms, and most of them About 40 of them has been found in the recent 3 decades. So there is lots of to find. Halo displays are usually around sun, as on the right one. This is typical halo display where is only random oriented crystals, and there is this 22-degree halo, the inner one, and then there is the 40-60 halo, the larger one. Halos can be also see around every kind of bright light spot, and also in street lights can produce nice halos. Usually the street lights produce this kind of halo pillars you can see in gold clay image where ice crystals can be seen above the around the observer. There is frequently observed halos. There is 9 different halos species in this category, and these halos Can you hear me now?
Yes, now we can hear you.
Yeah, the host was muted me for some reason. Okay, there is nine different halo species which are frequently observed, and these can be seen almost over 90% of the halo displays. And in almost all halo occurrences, these have been present. And these are formed by hexagonal ice crystals, which have 3 different crystal orientation. One is random orientation, then is plate orientation, and column orientation. Plate orientation is orientation where the basal face of the hexagonal ice crystal is horizontal, and column orientation is where this basal face is vertical. And these halos are formed by quite simple ray paths. Here is the typical halo display which has only these frequently observed halos. There is random orientation which produces this 22-degree halo. There is also 46-degree halo, which is very faint here. Plate orientation produces parhelia, both sides of the sun, and the parhelic circle, which is going around the whole sky and make a full loop here. And then there is column orientation, which produces this 22-degree tangent arcs and 46-degree infolateral arcs here. Then there is gray halos. These need other orientation for ice crystals, so-called Barry orientation and Lovitz orientation, and some other orientation is maybe needed to explain some rarest halos. These halos, not all have complex ray paths, but some of these has ray paths where the light is bouncing inside the crystal several times, up to 10 times internal reflection inside the crystal before the light goes out. These rare halos are usually accompanied by the bright and large or big halo displays. Then there is also rare halos which are produced by other halos. When there is really bright parhelia, then you may see parhelia of parhelia. This is multiple scattering, and there is four multiple scattering halos known today. 3 of them have been found last decade. Some of ice crystals may have pyramid faces, and these produce also own set of rare halos. Some of them are not so rare, but they are that kind of halos that only halo enthusiasts and observers usually see and photograph. There is halos which are not possible to explain using so-called classical halo theory, which is about these hexagonal crystals and simple ray paths. And that's the field we are working right now. But it's so complex, I don't go there.
You have about 2 minutes left.
Excuse me?
You have about 2 minutes left.
Okay. Some halos are spread all over the sky. This is from same display. This is sun side, and this is the opposite of sun side. There is helium, which is opposite to the sun. This display did have 20 different halo species, lots of rare halos. How we study this? We use this Monte Carlo halo simulation. Here is a simulation, and here is a halo display, which is simulated here. So there is some differences between the intensities, and these are the things we use to see try to find out by using different kind of crystal parameters in simulations. Ice crystal sampling is therefore very important part. So we collect samples when it is possible, and this is used in diamond dust ground level halo displays. And they are photographed in microscope. During this ice crystal sampling, we take also photos of halos, but we use very bright spotlight, so we are not relied on sun or the moon. We can produce our own sun. These displays are sometimes very strange looking, and there is halo which we cannot explain at the moment, and some other halos which are very rare. Ice crystals we collect in Petri dishes, which is filled with pure gasoline to prevent them smelting. So this kind of sample is very good. There is clean ice crystals. So the next step is automated all-sky halo cameras. There has been one prototype to use. We have used, and it gives a lot of more material for statistical analysis and to find out how common some kind of ice crystals are in cloud levels. And image processing is very important part today, since we can spot something using some kind of filters and stacking images. So we can get much more information from these halos. There is also lots of open questions, like some exotic ice crystals, we don't know how they produce halos. Maybe some other minerals are producing halos in Earth atmospheres. Also ice could be iced, or ice is in Earth atmosphere. There is some hint of that. There is also this kind of problems that some halos are seen only in artificial ice crystal clouds from key resource snow cones. We have also observed electromagnetic fields that can change the halos, orientation of ice crystals. And there has been a halo observed also in Mars. And there is lots of theoretical predicted halos which are not documented yet. So, thank you.
Thank you very much for your talk. Maybe we can have one short question.
Yes.
I don't see any hands, so I can ask one. Are there any Sorry, I see a question from Barry. So please.
Question. When you do your Monte Carlo, does it ever come up with unpredictable results?
We have seen lots of unpredicted halos in some simulation. Or should I say halos, we are not predicted other ways, but from simulation. We have found several halos after we have seen that this kind of halo is possible because the simulation has shown us that, okay, there should be a halo. We have found several of these halos in recent years. So, yes.
Great, thank you.
Okay, thank you very much once again for your talk. Could you please stop sharing your screen? Yes, great. So the last speaker in the session is Bastian van Diedenhoven. Bastian?
Yes, I'm here. Apparently, I cannot share my desktop.
Okay, and did you send us a backup presentation?
Let me, I have to change my, this is very annoying. I did not send a backup presentation. I have to leave I have to leave and join back in, then I can share. So give me 1 minute.
Yeah, we can wait for a couple of minutes, sure.
Thanks.
Colleagues, maybe you have any questions to previous speakers, so you can ask them. Jarmo, are you here?
Yes, I am.
Are there any laboratory setups to see halos? Some artificial setups?
Well, we can say the spotlight halos are artificial halos, but the laboratory have to be outside. So,
okay.
There has been some laboratory simulation studies with halos also.
Are you seeing my screen now?
Okay. Thank you, Jarmo. Yes, we see your screen, so please, the stage is yours.
Okay, thank you. Sorry for the
no problem.
Confusion. So I'm Bastian van Diedenhoven. I used to be at NASA GIS and Columbia University, but I recently moved to ESRAN, Netherlands Institute for Space Research. And so this talk is about retrieval of aerosol water fraction, high growth scopicity, and dry size distributions using multi-angle polarimetry. And of course, I acknowledge my co-authors at ESRAN, at GIS, and at Langley. And so this talk is certainly standing on the shoulders of giants, especially the giant that was Michael Mashenko, who of course wrote this paper and showed that we really need multi-angle polarimetry to not only get the optical depth of aerosol, but also have information about the size distribution and the refractive index. And we need that not only to quantify the direct aerosol effect, but also the indirect aerosol effect. So that's the influence on clouds. And so if we look at the fraction of aerosols that are acting as CCN, it really depends on the high growth scopicity of the aerosol. So on the type of aerosol, basically. And it also depends on the size distribution. So we really need to constrain these things to know the fraction of aerosol acting as a CCN, and also know when the sizes and the types are changing. And so if we have a look at the size distribution of aerosol, so this is a dry size distribution with an effective radius of 0.15 micron, a variance of 0.15, and this has a refractive index of 1.55. If we now expose this to humidification, it will grow following the Kaplan-Köhler curve. And so now basically what is seen is that the size distribution shifted, so the effective radius is increased, the variance stays the same, but also it's the composition is changed. So it's now 67% water, and therefore also the refractive index goes down towards the water value. So if we look at this as a function of volume water fraction in the aerosol, we see that the refractive index scales linearly with the water fraction. And any mixing rule that you will apply will give you basically the same result as shown here. And also the effective radius increases in a very characteristic way with the volume water fraction. So now if we look at the dry refractive index of many different types of aerosols, we see that there's not much variation in the dry refractive index, and they're all around 1.54 or so. And so this is a paper from Schingler et al. So we can actually use this to have a very simple retrieval of the water fraction by using the retrieved wet refractive index and assuming this dry refractive index to be around 1.54, and use this very simple equation to derive the water fraction. So this is certainly not new. It's used before and also applied to aeronets, for instance, by Greg Schuster et al. And also others. But here we can apply it to advanced multi-angle polarimetry, mainly the research scanning polarimeter, RSP, which of course is an airborne version of the APS instrument, which was on Glory. During these recent missions, there was also very advanced, large, Langley large in situ probes mounted on these aircraft. And so in the rest of the talk, I make the assumption that the variation I see in aerosol properties within the selected daily time ranges are due to the variation in humidification. And so now if we apply this very simple retrieval on the retrieved refractive index using this data, then we can see in the Campex mission near the Philippines, we see a water fraction ranging from 0 to almost 1, and there's a kind of a peak around 0.5. And during the Activate missions, we had somewhat a lower volume water fraction. But of course, what is very striking is this large peak at 0. So this is very dry aerosol. And it's because the refractive index that we retrieved is around 1.55 or sometimes even higher. So is this an artifact of the retrieval or is this real? And so we can look at in situ data for these campaigns, and we see basically the same. So we see in Campex is a little bit higher water fraction, not as high as in the retrieval, but certainly higher than during the Activate campaigns. But also we see this very large peak at 0, which in the in situ measurements are from aerosols that did not grow after humidification, or sometimes even shrank after humidification. So these are all the retrievals and the measurements together. But if we take daily averages, then we plot them against each other, then we get this. So there's a nice correlation between them, and the median absolute mean absolute difference is 0.13, so which is about the accuracy that we expect. So there seems to really be something here in this retrieval. Also, if we look at the effective radius that we retrieve as a function of this retrieved water fraction, then we see it increases very much as we expect from the theory I just explained. So this is just one day of measurements in Chempex, and I actually chose this day because I was in the aircraft operating the RSP at the time. And so we can also use this to retrieve the dry effective radius, because we know the wet effective radius and we know the water fraction, and we can use this model to derive the dry effective radius. And that is shown here. So the blue bars are for the wet effective radius that is retrieved using polarimetry, and the colored bars are then the dry values that I deduced. And of course, especially during the activate, there's not much difference between the two distributions, because we had this large amount of aerosol, which basically was dry already. And now again, we can compare these to the in situ measurements shown below here. Well, the retrieved dry effective radius are in the same range, I must say, as the in situ measurements. The in situ measurements are a little bit lower in all cases. Excuse me. But this is also very difficult, actually, a measurement to make in the in situ measurements. So we might expect some differences also because of the different the different types of measurements made. Excuse me. So if we look a little bit further, not only to the effective radius, but also the effective variance, we can see that the effective variance also increases in our retrievals. And if we plot the retrieved effective radius, variance against the effective radius, we see that there is a very strong correlation and almost a linear correlation. So what's going on here? So now let's go back to our simple model, but now make it a little bit more realistic. And we assume that a part of the aerosol distribution is hydrophobic. So this part will basically not grow as it's exposed to water vapor. So if we expose this to water vapor, we see that the effective radius shifts just like we saw before. So the bulk is growing. However, part of the aerosols basically stay put, and this is increasing the effective variance. And if we increase the hydrophobic fraction, then we see that the effective radius is the same, but also the effective variance increases even more. So again, looking at this as a function of a volume water fraction, we see that the effective radius is not so dependent on this hydrophobic fraction. However, the effective variance increases with water fraction, and it's also dependent on this hydrophobic fraction that is assumed. And now if we plot them against each other, so this is the absolute change in effective variance plotted against the relative change in effective radius, then we see that the slope in here is dependent on the hydrophobic fraction. So we can use this in a retrieval. So we can select data per region or a day and determine the slope of the variance over the radius. And using this way, we can constrain the hydrophobic fraction using this model slope. And we can even estimate the kappa value, so the hygroscopicity parameter, by assuming a maximum value and applying this equation right here. So that is done here. So these are daily retrievals. So we get one retrieval per day. So there's not much data here, but you can see some variation. And in general, you can see that the hydrophobic fraction is really high. That's retrieved here, and especially it's highest in the Activate Winter campaign and lowest in the Chempex campaign. And the derived kappa values are basically in the inverse. So the highest values we see during Campex and the lowest values during the Activate winter campaign. And
sorry, yeah, about 3-4 minutes.
Okay. This we can compare to the in situ measurements of the kappa value. So these are kappa values derived from the growth functions that are retrieved or are measured in situ. And so here you see a similar thing going on. So with the highest kappa values retrieved during Campex and the lowest kappa values retrieved during Activate. And again, you see this large peak at 0. So again, these are aerosols that are basically not growing after humidification. And mind you, these are 1 Hz observations right here, while these are daily average values. Although you can see the same variation in these 2 data sets. So, so I must note that the retrieved and measured kappa values are really in this range from 0 to 0.2 or so, where you have a really high sensitivity of the fraction of aerosol acting as CCN to this kappa value. And there's also a very high sensitivity to the effective radius in this region. So we really need to constrain these two to really get a better handle on the CCN activity of aerosols. And as I showed you, we probably can using this multi-angle polarimetry. So I come to my conclusion. So I show that the aerosol water fraction can be retrieved from the refractive index. It compares well with the in situ. We can infer a dry effective radius, which also compares reasonably well with the in situ. And there are many cases in the in situ measurements and our retrieval with a 0 water fraction. And also we can see this increase of variance that all point to a dominance basically of the hydrophobic aerosols. And this has potential for application to the PACE SPEX1 polarimeter, which will be launched in about 2 years. So we can improve the CCN estimation using the retrieved number concentration, the dry size distributions, and probably also this kappa value. And when combined with the also polarimetric droplet number concentrations from the PACE HARP instruments, this really will improve the constraints on the aerosol cloud interactions that we so much need for climate research. And I'm thinking maybe it's good to consider a direct retrieval of the bimodal fine mode, where we assume a hydrophobic fraction and a water uptake, and we can actually retrieve it directly from the level 1 measurements. So that was my talk. Thank you for your attention.
Thank you very much for the interesting talk, and we have a question from Jacek.
Hey, Bastian, really fantastic talk. What came up to me when you showed those pictures of retrieved hydroscopy, I'm sorry, my pronunciation is not that good. What came up to me is it possible to look at, different aerosol species that have each their own value for this hydroscopy, and maybe make a weighted average to see which one would fit what you retrieve, and therefore, in addition to retrieving that it's bimodal, even say something about which aerosols you're seeing there?
Yes, that's a good idea, good suggestion. During these campaigns, we also have the HSRL instrument, which makes some classification of the aerosols. And of course, we have the in situ measurements, which also classify the mass fractions of different species But I do must say, for these flights, there is a limited amount of data. So I think for satellite data, we can use regions, and really we get much more data from the satellite measurements to look into these issues. I'm also waiting for the rest of the Activate campaigns, which allows me to add a lot of more data to this, and hopefully also see some more variation in aerosol species. So thank you. Yes.
Yeah, without saying, you have said that many times in the past, and I agree completely with that, that one of the challenging things ahead of us when using polarimeters is to actually be able to distinguish between different aerosol species, and especially when they are externally mixed. And so this is very exciting, because this provides one way to actually help solve this problem.
Yes, thank you.
Okay, any other questions? Maybe I have a short one. Could you return to any of wet effective radius plots? Yeah, I wonder, no, yeah, like this.
This one?
No.
Oh,
yeah, like this.
This one?
No, previous. Yes.
Okay.
Yeah. Maybe I missed something, or I don't know. Do you have a physical model for this dependency?
Yeah, so the effective radius increases because of water uptake. So
I mean some theoretical model which predicts this red line.
Yes. Oh, sorry. Yes. So that's I don't have the equation written out, but basically that's the Köhler curve, or the kappa Köhler curve, which is a parameterization basically of water uptake from by aerosols, but it can also be applied to supersaturated conditions. So it is basically the same as used to estimate the CCN activity of aerosols.
I see. Okay, thank you. Okay, now I think let's thank all the speakers of the session once again, and we are going to meet at the last session of the ELS of this ELS conference in 18 minutes. So thank you very much, and see you in 18 minutes. This is the end of the session. Thank you.
Hello, everybody. Welcome to the last session of the conference, session 16. If the first speaker is here, Mengao, you could maybe share your screen already.
Yes, let me try.
So the first speaker, Mengao, will be talking about accelerating multi-angle polarimetric carousel and ocean retrievals for NASA space mission.
Thank you, Anne. Can you see it?
Yes, we can see and hear you.
Great, thank you. So thank you, Anne, for the introduction. My name is Mingao from NASA Ocean Ecology Lab. So today I will talk about a remote sensing algorithm. So we use a multi-angle polarimetric measurement to retrieve both aerosol and ocean color properties. And I will also talk about how we accelerate our retrievals through deep learning. So in support of operational processing for NASA PACE project. So first of all, I want to thank NASA PACE project for the support, and also everyone who have been involved in the Maple algorithm development for the last 5 years. And especially I want to thank Peng Zhai for developing the RT code, which is at the core of our retrieval algorithm, and also Wanderley Martin's HARP team for providing data for testing. So as we all know about, aerosols are important. They can modify Earth's energy balance, impact air quality. They're also important for ocean color remote sensing. So for ocean color remote sensing, we want to get this water-leaving reflectance near the ocean surface. So in order to do that, we have to remove all the contribution in the atmosphere from the remote sensing measurement. And aerosols are one of the very important components there. But the task is not easy because aerosols are often very complex, and they're also highly variable in space and time. So here's a multi-angle polarimeters, or we simply call it a map. They can measure the Stokes vector from several different angles, and also they can derive this degree of linear polarization. For this quantity is often highly accurate, so the measurement uncertainty can be as small as 0.01 or even smaller. So with that, the map measurement provides rich information for aerosol characteristics that include aerosol optical properties and also size and refractive index. So Michael's work also pioneered in the polarized remote sensing. So we have learned a lot from Polder, ASP, or APS, or its airborne version RSP. And there are several new missions with the polarimeter will be launched in the next several years. So that's Maya, 3MI, and also polarimeter for PACE. There's one CubeSat mission is launched last year. We also provide proxy data for PACE. So some more information about the PACE. So PACE includes 3 instruments. The main instrument is called the ocean color instrument, or OCI. It's hyperspectral, and also cover several short-wave infrared band. And there are 2 parameters that compensate to each other. The SPEX1 instrument from ISRON is hyperspectral, measures 5 wing angles with a narrow swath about 100 kilometers. For HARP2 is from UMBC. It measures 4 bands, but with 60 angles at 670 and 10 angles at all the other 3 bands. And so it have a wide swath, so with a nether swath about 1,500 kilometers. So HARP2 really pose a really large computer challenge to process this large amount of data. So there are several aerosol retrieval algorithms available to PACE instrument. So GRASP from Oleg's team has already been used by the HARP team, and remote timing is developed by ISRON. So for the specs for the specs instrument, MAP is from STEM's team from NASA Langley. It's planned for both polarimeters. So Maple is the one we are working on. It's more ocean focused. It have a flexible ocean biotic models So we want to use it for both open water and also closed waters. Our recent work is to accelerate the code and to address the computer challenge of the wide swaths from HARP data. And this new algorithm, we call it FastMaple. So more details about the data products from PACE map data, you can get it from PACE website. So here's how it works. So we based on our original Maple algorithm. So it's the RT code is based on a coupled and multi ocean system developed by Peng Wang. And for the retrieval part, we use least square optimization. Basically, we get the retrieval parameters iteratively, and we use this Jacobian matrix to determine the updates of the retrieval parameters. So if you look at this the form model, we have 15 parameters. So that includes solar wave geometries, ozone density, also for the aerosol properties, and the wind speed and the chlorophyll A concentration. So except the one on the top, so we still have 11 parameters to retrieve. For FastMaple, what we did is we just replace the Maple algorithm. We replace the form model in the Maple algorithm by neural networks. And for the Jacobian part, we can also derive it analytically. So therefore, it can also represent by neural networks. So in this way, we can really maximize the retrieval speed. Okay, now let's look at this the form model. And this is we use the feed-forward neural network architecture. So there is a simple structure of that. So the input, just the input parameters, the 15 number I just mentioned last slide. So at each layer is a very simple matrix operations with a weight matrix and a bias, a vector. And the output from each layer will be input of next layer. Eventually, the output layer will give you reflectance or degree of linear polarization. And here's an example, like what the weight and the bias look like for the model we have. So we have 3 hidden layers. So the weight matrix and the bias vector is showing here. The total size is only 1 megabias. So we train the model with 20,000 RT simulations for each band, and we can achieve accuracy for reflectance less than 1% and the degree of linear polarization less than 0.003. So our original RT speed is about 10 seconds. And but after we use this neural net, we can achieve about 0.01 second in CPU, or if we use GPU, it can get 1 millisecond. Okay, so this is what it looks like for the Jacobian matrix. For Jacobian matrix, if we look at this form model part here, so Jacobian matrix is just the derivative of the output layer with this input layer. So it can be just derived layer by layer using the chain rule of derivatives. So this process is called automatic differentiation, or AD. That's what I mean here. So with this, we can really speed up the Jacobian matrix calculation. Here is a comparison between this using finite difference and automatic differentiation. Using finite difference, we get average retrieval speed about 3 seconds using this like 1,000 retrieval cases. And using AD, we get retrieval speed about 0.3 seconds, so 10 times faster. If we use GPU, it can be also several times faster. Meanwhile, we can also maintain a high retrieval accuracy after we compare the retrieval result. Okay, so here are some applications. So we can study the retrieval uncertainties and also the retrieval capability for the HARP data. So we did based on synthetic data, we can look at the retrieval uncertainties. So here is for aerosol object depths, the retrieval uncertainty is about 0.01 to 0.03, certainly depend on the aerosol loading, and generally it's increasing. So for a single scalar albedo, it's decreasing with the increase of aerosol loading. So the result the uncertainty about 0.05 to 0.03. Certainly, COS mode have larger uncertainties because we don't have a short-range infrared band. Okay, so with that, with all the retrieved aerosol properties, we can study the water leaving signals. Basically, we just remove the contribution of aerosols from this atmosphere. So we can see the retrieval uncertainty for this water leaving signals is increasing with the increase of aerosol object depths. So the shaded area is a PACE requirement. Basically, what they say is we need aerosol loading less than 0.3 to achieve pace requirement. Okay, so here is the application to the field data. So we don't have many field data, but the ASPO field can be really provide a really nice proxy data for us. So here is an example for RHARP at the three view angles. On the top, we have this true color image, and on the lower part, we have this reflected only at this 670 band. And there's some very thin cirrus cloud there. It's really hard to see from the top panels, but you can see it from the lower panels. You can see, as indicated by A and B, two clouds there. It's actually have different locations if you look at it from different angles. It's due to the parallax effect because we collocate all the data on the ground. And this also will make impact on our aerosol retrievals. So here's some results. On the left, I'm showing you the cost function. That's basically give you the difference between our forward model fitting and measurement. So you can see some regions really show up. That's due to the cloud impact. And the region also long because you can see it from many different locations. On the right, there is a retrieved aerosol optic depth and water leaving signals. So what do we see is basically it's uniform, but there are some regions impacted by the cirrus cloud there. And if we compare with HSRL, the latter aerosol optic depth product, you can see basically they agree to each other, but there are some peaks due to the cloud impact. So what we really need to do is to remove the angles with the impact by cloud. And that means we need a multi-angle cloud mask. And this is the work we are currently is doing. Okay, so I want to summarize here. So to have demonstrate the neural network and also this automatic differentiation. They are useful approach to improve the multi-angle parameter retrieval speed and accuracy. So with that, our fast maple algorithm provides an efficient way to retrieve aerosol and ocean color properties for pace HARP data. And there are also a lot of future works. And the one thing is that we also look at the cloud mask on this multi-angle data. And also we are also incorporating more sophisticated aerosol models and also instrument uncertainty models. So I will stop here. Thank you for your attention.
Thank you for an interesting talk. We have time for one question, and I see that there is one hand. Go ahead.
Hi, I hope that's me, Jacek.
Yes.
Thank you, Gao, for a fantastic presentation. I noticed, in the beginning of the talk, you said that you intend to apply this retrieval algorithm, or that it's possible to apply it to both coastal and open oceans. But when you specify your parameters, for the ocean, you have just one parameter, and that is the chlorophyll concentration. And that works probably quite good over the open ocean. But for coastal regions, we know that, there are many other things that cause this relationship with chlorophyll concentration to break, like, for instance, sediments that come from the river. Can you comment on that? Do you plan to take that also into account in the future? Or is there another way that you get around this?
Yes. Yeah. So thank you, Jacek, for the really nice question. So that's I didn't really talk about that part. So for our original maple algorithm, that's using the online with transfer calculation, we have a more sophisticated biotic model for coast waters. So basically, we have 7 parameters to specify for the coastal environment. And for this for the fast maple, we only use the single parameter model. Right now, it's just our first step. So we want to see whether this whole neural net concept works. That we are still learning it. And the next step will be incorporate more complex either ocean models or aerosol models, because that involve you need a bigger training data sets. So that's more challenging. But we do plan to work in that direction. Thank you.
So in that case, then your total parameter number would increase from 14 to 20 if you take also the more complex ocean found near coasts into account?
Yeah, that will depend how we parameterize the coast water system. I know you also have a biotic model for the ocean system, and the Peng team is also working in that direction to say like what is the optimized number of parameters we should use. But yeah, I would like to have more discussions. Thank you about that.
Thank you.
Thank you.
All right, let's go to the next speaker, who is Anthony Davis. You can start sharing your screen. And the talk will be on how do cloud images form? Two intertwined diffusion processes.
Okay, I'm looking for my application here. Maybe I'll just go to it. Can you see my screen?
Not yet. You have to select your specific screen, specific window.
Oh, gotta go to Open System Preferences. Not able to quit now. Fuck. Oh. So you can't see my screen, right?
No.
Oh.
And the share screen button, does it work?
I know where it is. It's telling me. Okay, maybe this way.
Yeah, great.
Good. Okay, thank you. Apologies. Okay, so okay, thank you for listening. I'll be asking a really basic question here. You look at a cloud. Why does it look the way it looks? And the answer we find in going down a rather interesting rabbit hole in statistical physics, which is sort of my background. I'd like to first of all acknowledge my co-authors, and foremost Linda Forster, who is my postdoc over the last few years, and also Dave Diner and Bernard Meyer. How do we get to the next slide? My usual buttons aren't working. Okay. So okay, so it's a very basic question, but it came to us for a reason, because we're developing a way of looking at clouds in remote sensing in full three-dimensional reality, and it's basically a cloud tomography, and we're moving from airborne to space-based, and for that we had to kind of revisit the whole idea of, what part of the cloud do we see? And for that, and we quickly discovered that there's a part of the cloud we call the veiled core, which we really does not influence the details of the images we measure. And after that, it gets into diffusion. So let's move on. Anybody who's, been following cloud remote sensing, you've, I'm sure, know about MODIS, the sensor on the Terra satellite, which has been working for more than 20 years and counting. Since there's so many pixels of cloudy pixels that come to us so fast, the retrieval of cloud properties has to be extremely fast and simple. And it's basically a matter of looking at two wavelengths and retrieving two important cloud properties, namely their optical thickness and the size of the cloud particles. So it's two unknowns, two observed questions, and it the forward model is a plane parallel, simple radio transfer model, very tractable. So it will work for stratus clouds, but not at all for anything with three-dimensional shape like a convective 3D cloud. So the principles of cloud tomography are basically an optimization, but all of a sudden we have a huge number of unknowns. Basically, the cloud extinction field is on a 3D grid, and our forward model, of course, has now become the three-dimensional radio transfer model. And the forward model is iterative with a propagation step and a scattering step and repeat. But the optimization is also iterative. So this is what people thought was a completely crazy idea. There's no way we can do this, iterate on an iteration. But there is a solution. There is a solution that came to us, and I have to acknowledge here Aviad Levis, who was a student at Technion, a PhD student at Technion at the time. He basically looked at that three-dimensional radio transfer problem and realized that the propagation step can in fact be linearized. So we have Jacobians for the first step, not for the second step or the full problem, but that's all right because we don't have to solve the full problem all the time. And it's what we call in inversion theory surrogate step model. But anyway, he was able to solve in finite time on a laptop problems with tens of thousands of unknowns, more unknowns for bigger clouds, and you need, of course, a cluster for that. But it's anyway, he demonstrated on LES clouds. We got an example here of how well it works, and he moved on from a monochromatic with given microphysics to a polychromatic and even with polarimetry. But what that demonstration was for something that looks like an airborne sensor. In fact, it was applied to real airborne data, where the pixels are small, 20 to 60 meters, let's say, and we want to be able to do this with spaceborne instruments, which have much bigger pixels. Now, think back at the forward model we're using. It's a deterministic three-dimensional radio transfer model where the voxels, the cells, have to be optically thin and uniform, not happening at 250 to 500 meters. So we have to rethink the forward problem and the inverse problem for that matter. And that's where this veiled core comes in. So we concocted a nice toy model, if you want, based on a fractal and a fractal outer structure and a fractal inner structure that mimics a three-dimensional 3D cloud, except that it's in 2D, so we can see what's going on. And so we call this our Koch cloud, given that the fractal, the outer fractal is a Koch fractal. And we ask ourselves, if we take a part of the cloud, which is deep inside, deep being 5 optical depths, and we change it in a way that's consistent with the turbulence going on there, but and we look at it in multi-angle, all the multi-angles we see from MISR at the MISR resolution. Do we see anything happening inside the cloud? And the answer is no. It's in the noise. That's the figure at the bottom there. The difference between the two clouds, if you want, is in the noise. So that part of the cloud is not something we should attempt to retrieve. This is another way of looking at it. There's that manipulated area, and Linda has plotted basically the error in that pixel and that angle as a function of optical depth to that core. And the larger the distance, of course, the smaller the difference in the images. And that's the paper here. I learn more. Okay, so here's a simple experiment where we, in tomography, we want to uncover the structure of the cloud. So, it's what the radiance that's coming out of the cloud corresponds to something that's going on inside the cloud. That's the name of the game. And so here's a simple experiment. We take a kind of a rectangle that's moving inside the cloud, deeper and deeper, and it's a plane parallel cloud otherwise. And we want to see what kind of image we get as a function of two things: depth and opacity relative to the rest of the cloud. And you can see that the deeper the object goes, the quicker it disappears into the noise, and the more opaque the cloud, of course, the longer it is visible. But even an object which is ridiculously opaque disappears at about optical depth 5, which is where we found the veil core, remember. Okay, so what's going on? It's basically a matter of loss of directional memory. To retrieve your cloud features, your cloud structure, I should say, from the features in the imagery, you need to remember where the light comes from to some extent, and it has to get to you. Okay, so it's really a matter of diffusion, and a diffusion, not a usual diffusion in space right away. It's a diffusion in direction space. So so that's what's happening. You're losing your directional memory on direction space. And once you get to the veiled core, then you get into a real diffusion, or let's say standard diffusion, where the light, if you want, is random walking all over the place inside the veiled core, coming out even more diffuse than it went in. So here's the, let's look at the diffusion in direction space first. So to the right there, you have basically what's going on is we're just looking at the directional properties of the light after 0, 1, 2, 3, up to 10 scatterings. And you see that basically it's, if you remember your diffusion theory on, that's like you've got a Gaussian curve that gets wider and wider and flatter. Well, that's exactly what's going on here. The phase function is the distribution of steps across the sphere, but when you iterate that once, 2, 3, up to 10 times, the effective directionality of the light is going away. You end up with a quasi-isotropic light, and there's a characteristic scale for this, which is in the jargon, it's a Markov process with finite memory, finite time scale, which is over there. Basically, after 6 to 7 steps, you've lost your memory of direction. Oops. This has ramifications in physical space, because at the same time you're walking in space, you don't lose your memory right away, so you're drifting, and the drift distance for that characteristic scale is exactly 5 optical depths. So that explains how far the light gets into the cloud before losing its directional memory. Now, now that you're in the veiled core, you've got your standard random walk, the diffusion limit, if you want, of the three-dimensional radio transfer equation. In the left-hand corner there, we see that if you have any absorption, that even makes the veiled core bigger, because the light, it gets dark very quickly. We understand phenomenologically and theoretically how the light translates, let's say, is transported horizontally on the veiled core, depending on, it arrives at some place and it comes out somewhere else, and we know how to quantify that due to previous studies. And but the question is, how does that affect the image of the cloud? And the answer is, it affects basically only the large-scale gradient. it's controlled by the opacity of the veil core, which is basically the opacity of the cloud, the amount of water in the cloud. And so here we're taking our Koch cloud and just pumping up the optical depth, starting from very low and to very high. So okay, so here is the reflected light going up and up and up and up, sharper and sharper features, and the transmitted light is going down, 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 and more flat. So we've figured out that if you take the sum, basically the total transmitted light here and the total reflected light, it follows, and take the ratio, it is a function that is linear in the opacity. So this is interesting because it's a quick and easy way of initializing your tomography. You need to know the outer shape of the cloud. That can be done by, cloud masking, multi-angle cloud masking. And by the way, this can be proven for simple shapes like this analytically. Okay.
You start wrapping up. You're out of time.
Yeah. Okay. Almost done. So here's a case study where we go to a more realistic LES cloud and do the same exercise of pumping up the opacity of the cloud. And for the middle case here is the natural opacity of the cloud, and it turns out to be a nice kind of balance between the what's happening in the veiled core and what's happening outside. And it's also the most diffuse image, if you want, the most washed out. If you're in the optically thin version, it looks like X-rays. Basically, this is basically an X-ray vision. It's just the integrated opacity of the cloud, optical depth, column by column, and this is basically a single scattering limit of it. And if you pump up the volume, then the light does not travel very far, and you can pick up all these sharp features, relatively sharp features. Okay, so you have to make these two diffusions work together, so there's an interface, and we demonstrated that with a 1D model. We've got a project here to do it in full 3D, well, let you look up the paper if you want the details. And so here's a summary. I think I hope to convince you that in an opaque 3D cloud, there's that veiled core and the outer shell outside of it, and that difference makes a huge difference in cloud image formation, and informs how to proceed in cloud tomography. Any questions?
Thank you for the talk. Unfortunately, we don't have time for the discussion right here. If anybody has questions, then please post them in the chat. And for the next speaker, who is Pengwang Chai, was asked to be played as a recording.
Yeah, I will be available after the talk. I will be available for questions.
Yeah, that's fine. So the talk will be on radiative transfer for coupled atmosphere and ocean systems in ultraviolet, challenges and applications. I suppose the tech team will start playing the recording.
Hello, everyone. My name is Pengwang Chai. And it's my pleasure to present you this topic of radiative transfer for coupled atmosphere and ocean systems in ultraviolet. My co-authors are listed here.
Sorry, I can't
Why
see
do we care radiative transfer
please,
in the
would
UV
you
region?
stop it, please?
UV is quite important for ozone retrievals. Brown carbon aerosol shows enhanced absorption in the UV, which is similar to CDOM, color dissolved organic matter. And the phytoplankton has these MAAs, which shows varying degrees of absorption in the UV, which make it difficult to model ocean radiative transfer in UV properly.
Hello,
Here I'm showing the
Hello, could you
curve
restart the slide?
AY. And it's my pleasure to. Why do we care radiative transfer in the UV region? UV is quite important for ozone retrieval. Brown carbon aerosol shows enhanced absorption in the UV, which is similar to CDOM, color dissolved organic matter. And the phytoplankton has these MAAs, which shows varying degrees of absorption in the UV, which make it difficult to model ocean radiative transfer in UV properly. Here I'm showing the curve AY, which is stands for yellow matter. Yellow matter is another name for CDOM. The two different parameterizations, MG 2009 and MAG 2007, applicable to different waters. For two different chlorophyll concentration, you see the separation of this different CDOM absorption would lead to differences in the radiance field. The right-hand side shows the brown carbon aerosol shows enhanced absorption in the UV, which is quite similar to the CDOM absorption. These similarities make it difficult to separate these two for a sensor measurement at the top of the atmosphere. Another challenge of modeling ocean radiative transfer in the UV is the lack of basic knowledge about pure water absorption. Here I'm presenting three curves, IOCCG, D, and MSCF. They're showing significant differences in the UV. And this difference would lead to, we need to consider this when we try to interpret the ocean color measurement in the UV. Another gap is the inelastic scattering in the UV, particularly Raman scattering by water molecules. Here I showed the figure which shows the range of excitation wavelengths which all contribute to a excitation field showing by this arrow. The mean frequency shift is around 3000 wave number between the excitation and the emission wavelengths. And another feature of Raman scattering is that the inelastic scattering depolarized the scattered field more than elastic scattering. The inelastic scattering has been studied in the visible region, but it has not been studied in the UV. The main topics of today's presentation is to study the impact of UV pure water absorption uncertainty to the top of atmosphere and the top of the ocean radiance field. Also, I will study the contribution of Raman scattering to the TOA and the TOO radiance field in the UV. The tool that I used to study this is a successive order of scattering radiative transfer package that I have been developing in years. It can handle atmosphere-ocean coupling and polarization exactly. And it can also take in flexible atmosphere and ocean scattering properties. It can handle spherical shell effect using the pseudo-spherical treatment. I also consider the gas absorption using high-chain molecular scattering database using ARTS to simulate and calculate its absorption coefficients, and those are reading to the radiative transfer package to perform the simulation. Ozone and NO2 absorption data from these two sources. Another feature, I jump to the last one, it's the inelastic scattering, Raman scattering and fluorescence being modeled in this package. Here I show the result of top of atmosphere readings field for these different cases using different water absorption data and different parameterization of CDOM absorption. As you can see for this case, which is for chlorophyll equal to 0.003 milligram per cubic meter, the difference is significant. In the right-hand side, I calculate the percentage difference of all cases with respect to the case using MCF data, which is the lowest of all. So you can see because the MCF data absorption is the lowest, means the readings field is highest. So I'm showing a negative 6% to some higher percentage difference in the visible. So here the cases for chlorophyll equal to 0.1 milligram per cubic meter. The differences between different curve is smaller. As you can see, the percentage difference is ranging from -2 to 1%. So the preliminary conclusion here is that for relatively turbid water, the impact of water absorption uncertainty is less. For a sensor at the top of the ocean, here the differences between different cases much larger. They range the difference between -25% to 10% for a clear water measurement. For chlorophyll equal to 0.1 milligram per cubic meter, the difference is reduced to -15% to 5% in the visible. Another subject I wanted to cover it's a inelastic scattering in the vector radiative transfer. Here I'm showing the radiative transfer equation. I want to emphasize this source function due to inelastic scattering. R means Raman, Y means yellow matter, C means chlorophyll A. The format of these source functions are similar. I just wanted to show the Raman scattering source function. In addition to the solid angle integration you normally see in a multiple scattering source function, here I wanted to emphasize the integration of excitation wavelengths. So namely, I need to evaluate the radiation field in all the excitation wavelengths and then calculate this source function and then rerun the radiative transfer simulation again in the excitation wavelengths to get the total field. This could be done iteratively. Here I'm showing the TOA sensor for chlorophyll equal to 0.03 milligram per cubic meter for elastic and inelastic scattering contributions. Two different parameterization of CDOM absorption it's included. Also right hand side you see 0.1 milligram per cubic meter. The percentage contribution of inelastic scattering for a clear water of 0.03 milligram per cubic meter, it ranges between 1% to 3%. And for 0.1 milligram per cubic meter, the contribution are ranging from 1 to 2%. This is for a TOA sensor. So even though these are small percentage differences, but considering it's a systematic difference when you're running the radiative transfer, so this got to be taken care of. For a top of ocean sensor, you see this different curve. The separation is much larger. So their percentage ranging between 10% to 20%, depending on the wavelength, and also depends on the chlorophyll concentration. In summary, today I present a sensitivity study to examine the effect of choice of water absorption coefficient spectra to TOA and TO reference reflectance. The main difference ranging between 2 to 6% for a clear water of chlorophyll equal to 0.03 milligram per cubic meter, and if for a larger chlorophyll values, the percentage difference between 1 to 2%. For TOO sensor, these differences are much larger. It could range between 10 to 20% in the UV range. Another subject is the inelastic scattering, which contribute to the total signal by 1 to 2% at the TOA. And for the TOO sensor, the range is much larger. It ranges from 10 to 20% even. For visible, ranging between 350 to 550 range wavelength range. Thank you for your attention, and I'm ready for any questions you folks might have. Thank you.
Thank you for the talk. Do we have any questions?
Could you show my title slides, because it was not showing? Sorry. I think Jessica has a question, by the way.
I'm sorry, I don't have a question except for saying that it's a wonderful presentation. I forgot to lower my hand.
Thank you.
Yeah, just a minute, we will show the first slide.
Thank you, guys, and I just wanted to... Hello, everyone. My name is Peng Wang Zhai, and it's my pleasure to present you this topic of radiative transfer. Why do we...
I think that's enough.
Okay, just quit, sorry. Yeah. Thank you. Just quit, yeah.
Thank you. So, I'm sorry for technical issues.
I'm quite annoyed by the Microsoft technologies. It's not following up.
Yes, do we have the speaker for the next one?
It seems that we don't have the fourth speaker. So I suppose that we can move further, because I don't think there might be people who can connect to our session, to a particular talk.
Yeah, given that it's the last 3 talks of the conference, I think we can just proceed.
Right.
Great. So the next talk then will be given by Dongren on performance of cloud 3D solvers in anvil-like ice cloud shortwave radiation closure at the top of the atmosphere over the equatorial Western Pacific Ocean.
Yeah, okay. My name is Tong Ren. I'm a postdoc in Dr. Ping Yang's group in Texas A&M University. Today, I'm happy to present our recent study of the performance of two ECMWF cloud 3D solvers in the radiation closure at the top of the atmosphere. So the conventional one-dimensional radiation scheme assume that the clouds are prime parallel homogeneous. So we only calculate the radiation fluxes at the vertical direction. So the horizontal radiated exchanges between the cloud sky and the clear sky is ignored. However, the resolution of the general circulation model has become increasingly finer. So you can see from the couple of the model intercomparison phase 5, the resolution increases from 1 kilometer to the recent high resolution experiment of the CMIP6 at around 25 kilometer. So the ratio of the vertical extent to the horizontal extent of cloud rises. So maybe making the ignorance of the horizontal exchanges problematic. So there are a number of approaches that has been suggested to deal the cloud horizontal variability. So you can see in the upper panel shows the radar retrieval of ice water content. In a conventional way, the clouds is treated as a prime parallel homogeneous clouds. So you can see just at each level, just to take the mean of the optical thickness, and they run the radiative calculations. And there is a method called the triple cloud method. And in each level, they divided the level by 3 parts. So in addition to the clear sky part, they divided the cloudy portion by the optically thinner and a thicker portion to do the calculation to account for the cloud horizontal variability. This is called the triple cloud method. However, in this triple cloud solver, the horizontal radiated transfer is also ignored. So in a recent study by Hogan and Shank, they suggested a computational faster treatment of the cloud horizontal radiated transfer. The effects of the literal radiated exchanges between cloudy sky and clear sky on the vertical radiation fluxes. You can see for real clouds at low solar elevation, the incident sunlight will be intercepted by the cloud size. So there is a literal radiation exchanges between the clear sky and the cloudy sky. So the contribution of this horizontal radiation exchanges on the extinction of incident solar radiation is treated by linearization of the literal exchange rate, which is assumed to proportional to a so-called normalized cloud parameter length. And the diffusive horizontal radiation changes is linearized in a similar way. And they call this the speedy algorithm for radiation transfers through cloud size. And both the triple cloud and the Spartacus solver has not been extensively tested. So in this study, we test the performance of these two solvers. So we focus on the equatorial Western Pacific Ocean region. You can see the tropical deep convective system is captured by the MODIS as shown in the upper left panel, which is two-color composite. And in the upper right panel, you can see shows the distribution of the MODIS retrieved cloud effective radiant. And you can see the thin cirrus at the edges of the convective system shows the smallest particle sizes. And in the lower panel, it shows the distribution of cloud optical thickness. So you can see within the system, those isolated deep convective cores shows the largest cloud optical thickness. And we used the European Center for Medium Range Weather Forecast Radiation Scheme, the ECRAD 1.40 for the study. And we run the 3 solvers, the conventional homogeneous solver, the triple cloud solver, and the Spartacus solver. So for the Spartacus run, we turn on both the triple clouds and the Spartacus, which means that it's not only allow the radiative transfer between clear sky and the cloudy region, it also allow the horizontal radiative exchanges between the optically thicker and the thinner region. So we compare the result with the unfiltered shortwave irradiance at the top of atmosphere with the collocated near median aqua cloud and the Earth's radiant energy system cirrus level 2 footprints. And the cloud properties are taken from the MODIS collection 6 retrievals. and we take over each footprint. And the cloud fraction for each cirrus footprint is calculated by dividing the number of the cloudy pixels, cloudy modest pixels by the total pixel over the footprint. And the atmospheric conditions were taken from the 5th generation of ECMWF reanalysis. The surface albedo is from the cirrus data. And we used the 1 month data in July 2008 for this study. And in addition to the cloud internal variability, previous studies suggest that the cloud top variability also contributes to cloud 3D effects. So to quantify the cloud top variability, previous study has used the cloud brightness temperature gradient. So as shown in this study, Varnay and Marshak 2004, because in the long wave, the cloud 3D effect is less significant. So they use the cloud brightness temperature gradient to decided whether a selected pixel is a illuminated pixel or shadowed pixel. So you can see, depending on the position of the sun, for each selected pixel, they first find the pixels in front of and behind this pixel. Okay, if for example, for this pixel, this one, they find the brightness temperatures over the pixels in front of and behind this pixel. If its brightness temperature shows a decrease along the incident solar radiation, so in other words, the cloud top height shows an increase along the direction of the incident radiation. So this is it forms a slope that faces to the sun. So then they identify this pixel as an illuminated pixel. So otherwise, in the opposite, they mark the pixel as the shadowed pixel. So inspired by this approach, for all the cirrus footprint selected in this study, we calculate the cloud top gradient along the horizontal direction of the incident sunlight. So in the upper right panel, you can see we here shows the cloud top height retrievals from MODIS Clagrange 6 co-located within a cirrus footprint in this study. So you can see it shows an increase from the northwest portion to the southeastern portion. So the cloud top height is as low as 8 kilometers and as high as 14 kilometers here. And we first calculate the cloud top height gradient along the eastward direction, as shown in panel B, and also along the north direction as shown in panel C. And then once given the direction of the incident sunlight, we can calculate this gradient along this direction. So you can see in the panel D, those positive values in this distribution are the cloud pixels that are illuminated by the sun. And the negative values shown in this panel D are over the regions that are away from sun, in other words, the shadowed region. So after get this distribution, and then we take the standard deviation of this distribution to quantify the cloud top variability. And we call this index the directional heterogeneity index, which is the standard deviation of the cloud top height gradient along the incident sunlight direction within each cirrus footprint. You can see if we take a logarithmic of this quantity, that make a more normal distribution. The upper two panels shows the sample distribution of the cloud particle size and the cloud optical thickness of those samples. You can see the effect gradient does not show a binomial feature, but the cloud optical thickness shows the binomial feature. We therefore think that the thin theorists contribute to a few samples in this study, and we further assume all the samples consist of the ambulite cloud and a deep convective cores. We assume the cloud optical thickness is a mixture of two Gaussian distribution, and we run a R package to separate these two types of cloud. And things for the optical thickness for deep convective cores, the optical thickness can reach the upper limit of the lookup table, so we are not used it in this study. And we focus on ambulite cloud shows in this distribution. And here are the results. So this shows the observation by the cirrus sensor, the cirrus unfiltered shortwave irradiance at top of atmosphere. And this the axis shows the radiation calculations from the three solvers in the ECRAD, the homogeneous, triple clouds, and the Spartacus. So you can see the ECRAD substantially overestimate the shortwave irradiance, presumably due to the overcast assumption of the MODIS 1 kilometer cloudy pixel. And compare the panels A and B, you see the root mean square error reduced by 10 OR per square meter suggests the triple cloud solver effectively reduced the cloud albedo overestimation. And compare the panels B and C. You can see if we're switching using the triple cloud solver to Spartacus solver, it's further reduced RMSE a little bit, so suggesting a further small reduction of cloud albedo overestimation. So this shows the result that scatter plots of the percentage error of each solver versus, so upper three panels, they versus the cloud internal variability. So this is square root of F sigma is the fractional standard deviation of clouds that define as the ratio of standard deviation of optical thickness to the mean of the optical thickness. That has been frequently used to quantify the cloud internal variability. So the lower panels is using the index we define, the directional heterogeneity index that used to quantify the cloud top variability. You can see in the upper panels, the percentage error. So if it's positive, it means the overestimation shows a weak correlation with the cloud internal variability. And the cloud albedo overestimation shows a weak negative correlation with the cloud top variability. So this result strongly agree with old study 2 decades ago by Varney and Davis. And they run the Monte Carlo 3D simulation and found that the cloud internal variability tends to move the radiation from optically thicker region to optically thin region, resulting in a decreased cloud albedo. So if this is not taken into account, then this will result in overestimate of cloud albedo. And the cloud top variability tend to move the radiance from optically thinner region to optically thicker region, resulting in enhanced cloud albedo. So and also you can see if we use the triple cloud solver, and those overestimation is reduced. However, if we use the Spartacus solver, it does not show differences in the correlation coefficient between panels E and F, suggests that the Spartacus solver is not very sensitive to the cloud top variability. And here shows the absolute percentage error, shows y-axis between the triple cloud solver and the homogeneous solver versus the cloud internal variability. You can see the improvement of triple clouds solver increase with increased cloud internal variability. And here shows the sample distribution of the absolute percentage error between the Spartacus and the triple cloud solver. So the dashed vertical line here marks the one standard deviation and below the mean. So in other words, those the samples to the left are the samples where the Spartacus solver outperforms the triple cloud solver. And the right panel plot all these samples with the y-axis as the cloud internal variability and the x-axis as the cloud top variability. So the red dots are the samples to the left of this dashed line. So you can see the Spartacus solver outperforms triple cloud solver when the cloud has a strong internal variability. However, it does not appear that it has a correlation with the x-axis. It does not show strong dependence on the cloud top variability, suggesting that the improvement is due in part to along the horizontal radiation exchanges between the optical thicker and the thinner cloudy region. Okay, here are some take-home messages. I will stop here. And thank you for your attention. And also good night to our friends who have now gone to bed in the Eastern Hemisphere. Thank you.
Thank you for this interesting talk. Do we have any questions? Questions, comments? If not, I think we'll just move on to the last talk of the session. And it would be, do we have the speaker here? Can start sharing the screen.
Yes, can you hear me?
Yes, so the next speaker will be Yuan Wang And the talk will be on assessing light absorbing aerosol optical properties and radiative forcing by combining laboratory results, satellite data, and numerical models.
All right, thank you. Let me share my screen here. Can you see it? Hello, can you see my screen?
We can see it.
Okay.
We can hear it.
Thanks. Yeah, thanks for the opportunity to share with you about our recent research, which is about the large-scale assessment of black carbon radiative forcing. So we try to use latest field campaign observations to constrain the model and to improve our assessment. Yeah, I'm Yuan Wang from Caltech, and I would like to acknowledge my co-author listed here. So I think we all know that the black carbon is the second largest positive radiative forcing in the Earth system, right after the carbon dioxide. And the magnitude of black carbon radiative forcing is estimated to be about 1/3 of the CO2 forcing. But if you look at the latest IPCC assessment report, you may notice there's a huge uncertainty with this black carbon radiative forcing from fossil fuel combustion. The range here can be up to 0.5 watt per meter square. So such a huge uncertainty, mainly caused by the black carbon, like a lifetime, the optical property, and how we treat the black carbon in the numerical models. I think in the lab, we have some good understanding about the black carbon evolution and the aging process, which is the major uncertainty source for the black carbon radiative forcing assessment. And back to 2008, John et al. Shows this black carbon change in the lab. So what they did here is to expose the fresh soot into the sulfuric acid vapor. So you can see here in about only 12 seconds, the morphology of the fresh soot gets changed significantly, and it becomes more compacted from the previous aggregated shape. And because of this morphology change, the density of the black carbon become much larger here. And another interesting thing is if you look at the supersaturation required to activate the aerosol particle into the cloud droplet, the supersaturation here is largely reduced for the aged soot, which means the hygroscopicity of the black carbon is also largely increased. So for the optical property of the aged black carbon, they did some additional experiments, and what they found is when the fresh soot get aged and coated by some other coating materials like sulfuric acid or sulfate, so the coating here will give you this lensing effect. Essentially, it will enhance absorption, and meanwhile, the scattering property also can be enhanced. And if you further heat the particle and to remove the coating here, the optical properties largely remain the same. So this is what we learned from the laboratory work. And how about in situ conditions? And more recently, we conduct two chamber experiment. So we deploy a smoke chamber into two places, Houston, US, and Beijing, China, the two most polluted cities in each country. And we assess this macrophysical and optical property change by soot particle after we emit the fresh soot into the ambient atmosphere. And what we found is that actually in the two places, the aging process of the fresh soot shows quite similarities. they all experience this compacting first and then additional coating. So in this process, we see the diameter of the particle get increased. And more importantly, in the second stage, when you have more coatings, the absorption capability of the particles can be enhanced. So we use a core shell ME code to calculate the mass absorption cross section MAC for the bicarbonate particles. And we found in both Houston and Beijing, the MAC can be enhanced by 2.4 times. And but there's also a huge difference between Beijing and Houston in terms of the aging life scales. So you may notice here for Houston, the whole aging process take about 18 hours, but for Beijing it's only 4.6 hours, simply because Beijing is more polluted than Houston. And in this paper, we did some simple back of envelope calculation about the black carbon radial forcing. And we show this aging process can give you a 0.45 watt per meter square forcing enhancement. But the caveat here is we do not consider the lifetime change of the BC during the aging process in this simple framework. So the next step is to put this aging process in a more comprehensive global climate models. So the model we use here is the NCAR CSM2, the latest climate model. And in this model, they have 4 aerosol size bin, and each bin have a different aerosol chemical species. And the fresh BC was first put into this primary carbon mode, and later on it will be converted to the accumulation mode when some criteria are met. So the important parameters here is called aging monolayer. It tells you like how much, how thick the coating should be if you want to move your black carbon from primary carbon mode to the accumulation mode. So later on, we will work on these parameters extensively. And here are some other description of this model regarding the aerosol optical property calculation. And if we look at the BC mass absorption cross section simulated in the model, you can see there's a highly heterogeneous distribution of the MAC. But one thing we can do here is to calculate the absorption enhancement factor as a function of the MAC in the accumulation mode divided by the MAC in the fresh mode. And the calculation here tells us globally there's about 2 to 3 times enhancement of the MAC in the aged BC mode, which is quite consistent with what we found from the in situ observation. But the climate model for a long time suffered from this a bias, huge bias in the chemical composition simulation of the aerosols. For example, here I'm showing you like this is the EC versus OC ratio. In Beijing, this number is way too high compared with what we observed. And in Houston, the opposite happens. So this EC versus OC ratio is way too low compared with the observations. So we have to come up with some adjustments when we try to compare the time scale, aging time scale between the model and observation. And here is our adjustment approach to first overcome this bias in the chemical simulation in the model. So this is what we observed. As I mentioned before, Beijing used much shorter time to age the BC, while Houston take much longer time. So if you have the unadjusted calculation from the model, you will get opposite comparison simply because the model put too much coating in the Houston and too small coating in Beijing. And so we applied this time scale adjustment, and we found now the comparison is more reasonable. And also, using this comparison, we can determine the monolayer numbers, as I mentioned before, in the aging parameterization of the global climate models. So from here, we conclude that the monolayer 3 is a more reasonable number compared with 8, which is the default number used in the current NCAR's CSM model. So what does this aging parameters means for the BC radial forcing? So here we can do a sensitivity experiment with 8 monolayer versus 3 monolayer. So 8 monolayer means you need much longer time to age the BC. And because of that, your BC burden will enhance mainly in the downwind region of the BC source. And the AOD is increased, and the BC direct radial forcing is also increased accordingly. And if you look at the clear sky BC radial forcing, it globally is also an enhancement, but the spatial pattern is quite different, mainly because of the surface albedo influence here. And like I mentioned before, the model has huge bias in simulating the other chemical composition like sulfate, nitrate, organics. And here we did a sensitivity experiment by changing the sulfate concentration in the model simulation. We double the SO2 emission here. We found there's two opposing contrasting effect here on BC radial forcing. So first, if we increase the SO2, the BC aging process will be more significant, and the hygroscopicity of the particle will also enhance, which will largely reduce the BC lifetime and the BC concentration. So the removal of BC become much easier because of the more sulfate in the atmosphere. So that will give us a negative impact of the BC radial forcing. But meanwhile, like I mentioned before, there's a significant lensing effect on the BC particles because of the more coating there. And so the net effect on the BC direct forcing is still positive, which means the lensing effect is still more pronounced than the BC lifetime effect by the enhanced sulfate. And here is the net direct radial forcing in the clear sky, which largely resemble the all sky BC radial forcing. So more recently, we look at the BC radial forcing during the severe haze events. We want to understand when the severe haze happened, how the bright carbon particles change the TOA radial forcing. So what we found is actually, so when there's a rapid haze development, the BC first can catalyze the chemistries which foster the aerosol formation through the aqueous chemistry, make the aerosol grow much bigger. So the coating is become very thick during the severe haze development. But the large absorption by the BC was largely canceled out by the also enhanced scattering and TOA. So you can see this is a light haze, is a moderate haze, is a severe haze. The TOA number for the radial forcing just changed very insignificantly. But when the severe haze development, the absorption in the atmosphere is still quite significant. And along with this much strong cooling near the surface. So such a heating in the atmosphere and cooling on the surface will largely enhance the atmospheric stability and further provide a positive feedback to the haze development. So here's my conclusion. And we think the black carbon aging process in the models can be constrained by the smoke chamber experiment. And our calibrated model shows that the coating can result in net enhancement in BC forcing, even there's a reduction of BC lifetime. and the BC direct radial forcing can change by up to 26% due to the uncertainty in the BC aging parameterization and coating aerosol mass. And during the rapid haze development, the TOA aerosol radial forcing remain unchanged, while the atmospheric heating is pretty significant. And the result I just mentioned above are summarized in those two papers. And I'm going to stop here and take your questions. Thank you.
All right, thank you. Do we have any questions? Patrick, is that a question?
Yes, I have now a question, if I may.
Yes, if it's a quick one.
Thank you very much for this presentation. It shows, how important it is indeed to take black carbon into account and that they are variable in the atmosphere. If my understanding is correct from your slides, what you're doing is you're changing the amount of coat, but are you also changing the shape of the aggregates? We know from observations that they collapse a little bit with aging, and that in itself shows also an impact on radiation.
Right, yeah, that's a good question. For the current climate model we are using, they assume all spheric shape for all aerosols in 4 different mode. Yeah, I'm with you. Like the shape from the fractional shape to the more compacted shape. There must be some change in the optical properties as well. So far, yeah, this model cannot handle the question from the morphology change.
Thank you. And one other quick question. When you showed quickly results. Oh, I'm sorry.
Yeah, we actually do have one more talk.
Okay, so let me ask on offline.
Okay, so if you could post it in the chat if possible. Okay, so one of the speakers, Evgeny Kasyanov, who was scheduled to speak at 8:35, is now ready for his presentation. So we will run his recording, and the talk is entitled 2 Decades of Ground-Based Multi-Sensor AOD Measurements at US Continental Site, Acquisition and Merger. Right.
Our research is motivated by previous studies on aerosol climatology derived from multi-sensor satellite observations. Similar to previous studies, long-term records of aerosol optical depths provided by several instruments with different design and operation will be considered in our presentation. Also, development of integrated AOD products will be highlighted as well. I would like to start our presentation with acknowledgement of my colleagues for the valuable contributions. Moreover, we appreciate all of organizers, session chairs, and participants who work together to keep this memorial conference running. Climate change assessment requires multi-year AOD products with high quality and extended coverage. Typically, such assessment includes AOD products provided by several and probably different satellite and ground-based instruments. AOD products provided by these instruments frequently have gaps, and duration of these gaps can be substantial. Moreover, AOD products from these instruments often have different temporal resolution and accuracy. To illustrate, we include descriptive examples from papers published by Michael and his colleagues. The first example will illustrate diversities between several AUD products in terms of spatial variability. The second example will demonstrate distinctions related to temporal changes and will highlight challenges associated with development of integrated products. It should be emphasized that influential papers published by Michael and his colleagues motivated many observational studies with focus on development of improved AOD climatology. Our study is one of them. Let us start with AOD distributions obtained from respective satellite observations during summer. We can see that spatial distributions of respective AODs are quite diverse. For example, AODs provided by advanced MODIS and MISE retrievals may have substantial differences, and they can exceed uncertainties required for accurate assessment of aerosol forcing. Let us continue with time series of global mean AODs over ocean. Time series considered here are quite diverse, and difference between them is time dependent. For example, there is a substantial spread between derived AODs in 2002. In contrast, spread is moderate at the end of 2005. The obtained differences are likely associated with well-known issues such as inappropriate retrieval assumptions or unsuitable calibrations. These issues are discussed by Michael and his colleagues. They also highlighted challenges associated with development of integrated AOD products from satellite observations. Development of integrated AOD products represents a great challenge for ground-based observations as well. Typically, AOD measurements are provided by several well-known networks, including AeroNet and Skynet. In our presentation, we consider multi-year time series of AOD available from collocated instruments deployed at US continental site. It should be stated that extensive data on cloud and radiative properties are available as well. Time series of AOD are provided for more than 2 decades by ground-based instruments deployed at SGP site. Different design and operation of these instruments defines instrument-dependent quality and resolution of respective AOD products. These products collectively provide an opportunity to obtain integrated or combined AODs with extended coverage and high quality. We consider this opportunity in our presentation. This slide provides basic information regarding design, data quality, and temporal resolution of ground-based instruments considered here. It should be recognized that sun photometry is part of AeroNet. AOD records generated by first 3 instruments include quality control information. We used only good data as indicated by QC assessment. AOD products provided by sun photometer are controlled by AeroNet established data quality. We used the most recent version, version 3, in our analysis. Temporal resolution of AOD records is instrument dependent. It can be high for the first 3 instruments and relatively coarse for sun photometer. To develop integrated AOD product, 2 challenges should be addressed. They are associated with different temporal resolution, data quality, and uncertainties of combined AOD and its practical applications. To address these challenges, we use approach with three main components. The first one represents collection of respective AOD records provided by ground-based instruments. The second component defines AOD with good quality and harmonized temporal resolution. Finally, we calculate combined AOD and its variability. And our calculations are complemented by traditional assessment of respective AODs. Let us consider temporal changes of daily averaged AODs. We use different colors to specify combined AOD and its four components. For example, we use green and light blue colors for combined AOD and AOD measured by sun photometer. All AODs considered here exhibit well-defined seasonal changes with large and small AOD values during summer and winter respectively. On average, large values exceed small values substantially, more than 2 times. Time series of respective AODs have gaps which are likely associated with instrument-dependent data quality issues and required upgrades and replacements of instruments. Duration of these gaps is instrument-dependent and can be substantial, from several weeks up to several months. For example, AOD record from one instrument, specified here by dark red color, has the longest duration of gaps, up to several months. Number of gaps and duration define temporal coverage of AOD records, and next slide will illustrate that. Well, there are two figures related to temporal coverage. The first one on the left side includes number of days where combined AOD and its four components have good daily average values. These numbers define temporal coverages of respective AOD records and combined AOD as well. Similar to previous slide, we use different colors to specify them. This plot illustrates two main points. First, coverage of combined AOD is comparable with those obtained for two instruments identified by red and blue colors. Second, temporal coverage of combined AOD is substantially greater than coverage obtained for other two instruments, specified by dark red and light blue colors. Relative difference is about 80 and 40% for these two instruments respectively. Several factors such as number of gaps and duration have an impact on diversity demonstrated here. The second plot on the right side includes normalized frequency and cumulative distribution function of standard deviation calculated for combined AOD. As demonstrated, standard deviation does not exceed prescribed uncertainties about 0.02 of respective AODs for majority of cases, about 90% of time. Also, we demonstrated the standard deviation can be used for selection of favorable cases where all respective AODs are in a good agreement. We generate integrated dataset with user-friendly data format and public access. Our dataset takes advantage of respective AODs, the long periods, and high temporal resolution. Our dataset allows a potential customer to analyze variability of respective and combined AODs at different temporal scales required for user-specified applications. and our initial development performed for selected continental site combines respective AUDs obtained at 2 wavelengths. Anticipated extension will include additional wavelengths and locations. We expect that our dataset will be useful for climate-related projects. For example, AUDs obtained at high temporal scales are critical for process-oriented studies and radiative closure experiments. There are 2 final slides. Terms acquisition and merger have a strong connection with financial activities, art, and music. To illustrate, we shall mention famous British rock band and cover of well-known album. This cover has a simple and bold design to represent multi-track recording. The latter allows one to record all of instruments and vocals separately and to correct each individual track if necessary. Cover highlighted by our previous slide could be modified slightly to represent 3 major terms considered in our presentation: acquisition, merger, and integrated product. The modified cover can represent main goals of the ELS conference: to bring together participants from Europe, Asia, America, and to discuss theoretical advances, measurements, and applications of diverse aspects of light scattering. Thank you for your all efforts to keep this memorial conference running.
Anna?
All right. Do we have any quick questions for the speaker? Jacek, it's a question, or is it a forgotten hand?
I'm sorry, I should have lowered my my hand. My apologies.
No worries. Well, I think it's time then for the closing ceremony.
Yes, thank you very much, and thank you all the speakers. Okay, now we come to the closing ceremony, and I'm going to show you a few slides, and I'm going to share our plans for the next year. So thank you very much, and thank you, colleagues, for joining us for this closing ceremony. And I want to thank all the participants who gave talks, who were listening to the talks. And here are some statistics. We have in total 182 participants with 92 speakers, and during these 5 very intensive days, maybe too intensive in comparison with offline conferences. We had only 4 no-shows, which I think is a great result, and it shows very good relations in this scattering community. We had 18 sessions and 3 pitch sessions among them, with 44 pitch talks, and it was our first experience to organize such pitches. And now, despite issues that we faced, I think now we know a formula for good pitch presentations and pitch sessions, so we can share with anyone who is interested. And of course, we should remember that this edition of the ELS was dedicated to Michael's scientific legacy and we all will be keeping him, and we all in mind, and we all in our hearts for his personality, and in our minds for his great scientific achievements. And I think it was very successful because during this session we had 113 participants at a time, and during the third 3 days we had about 70-80 participants and about 40-50 participants during the Thursday and Friday. So I would like to also recall the awards that were given during this conference. Won the Health Award to Professor Gerard Guzbe, Michael Mishenko Award to Professor Thomas Reed, Peter Waterman Award to Dr. Alexander Moskalinsky and Dr. Anna Virki, and Richard Goody Award to Dr. Bin-Kyang Sang and Dr. Bin-Ki Yi. And here you are. These are photos that we took on Wednesday, and when at the moment when most of participants were online. So here are the pictures, and we will share you these screenshots in a letter which we will send you shortly. And also I would like to thank our technical team and and my colleagues. These are students, IT engineers, and our event manager Anastasia Koptsova, who helped all of us to organize such a great event. So and I thank to all of you because without your active participation we wouldn't have such discussions and such a big interest in all of the talks. So the next event, as was previously discussed even with Michael, we hope that we will overcome the epidemic, and we will meet together offline in St. Petersburg, the Northern Venice. This is one of the top interesting European cities for tourists, and our university, the ITMO University, is located in the historical center, and I hope we will be able to organize everything and to show you the city. So again, thank you very much, and I hope to see all of you in a year in St. Petersburg. So if someone wants to say something, to share impressions, you can do it now, or you can send us a letter if you want if you have an advice to us, if you want to share your ideas, please send us messages. So thank you very much.
Alex,
okay, this is it.
I would like to say, I don't know, my voice is coming in a different way, but I would like to celebrate this event. This was extraordinary event thanks to you, your local organizing committee, as well as the 6 people, including Maxim, Matt, Matthew, Libby, and Anne. You did really a great thing, because apparently everybody was hungry for the science of light scattering, and everybody stayed here and all over the world. This was one of the best conferences, I can say, I attended, and you did it very nicely from bottom up. From, the new generation is bringing the new ideas up there, and probably you are going to use a similar platform next year. Even if everybody comes there, still there will be more people willing to attend. So without taking too much time, thank you very much.
Thank you, Pinar.
So I also would like to say a few words. So Pinar is always emphasizing that 6 people are like an organization committee, but I would like to say that although we were all involved and did our share of work, but most of the work, the major part was done by Alexei, surely, and by his IT staff that he showed. So I really can't even estimate how much work was involved to keep it all smooth and running. And I mean, starting from the first website, which looked very professional from the start, and how it all worked during the conference with all the, I mean, all the technical issues which I mean must appear, but they were quickly solved, and that shows the proficiency. So I really want to applaud to Alexei and his colleagues, and maybe I know that Anastasia is probably available as always hidden as ELS team now. So if she can turn on the camera so we can applause her like in person. You did a great job, all of you. Thank you very much.
Thank you very much.
Okay, see you.
Thank you. Bye bye.